Hey there, night owls. Tonight we're cracking open the most visible mystery written on every single human body, skin colour. And here's the kicker. That difference between the palest Scandinavian and the darkest Sudanese? It all comes down to about 15 genes. That's it. 15 tiny molecular switches out of 20,000, and suddenly humans look like we're different species. Spoiler alert, we're not. Here's what blows my mind. Every single person alive right now, all 8 billion of us, descended from dark-skinned Africans who lived 300,000 years ago. Light skin. That's one of the newest evolutionary adaptations humans ever developed. Newer than farming, newer than cities. We're talking mutations that happened so recently in evolutionary terms, they're practically still warm. So before we dive in, smash that like button if you're ready for some serious science, and drop a comment. Where in the world are you watching from right now? I'm genuinely curious who's on this journey with me. Now dim those lights, get comfortable, and let's talk about the evolutionary masterpiece you're wearing right now. Because your skin isn't just wrapping paper for your skeleton. It's a molecular time capsule that tells the story of where your ancestors lived, what problems they faced, and how they survived under different suns across thousands of generations. Tonight, we're reading that ancient text together. Let's roll. So let's rewind the clock about 300,000 years. Picture the East African savanna, blazing sun, scattered acacia trees, and our earliest anatomically modern human ancestors going about their business. And here's something absolutely crucial to understand. Every single one of them, without exception, had dark brown skin. Not sort of brownish, not tan, dark. Packed with melanin like a molecular fortress specifically engineered for one purpose: survival under an equatorial sun that does not mess around. Now, before we go any further, we need to talk about what melanin actually is, because calling it skin pigment is like calling your liver that blob near your stomach. Melanin is a complex polymer, basically a sophisticated biological molecule that your body manufactures in specialized cells called melanocytes. These little factories sit at the base of your epidermis, churning out melanin and packaging it into tiny bundles that get distributed to surrounding skin cells. The more melanin you produce, the darker your skin. Simple enough, right? Except melanin isn't just sitting there making you look good for the gram. It has a very specific job, and that job is keeping you alive. Here's where it gets interesting. The sun doesn't just provide light and warmth and those nice golden hour photo opportunities. It's also bombarding Earth with ultraviolet radiation, specifically UVA and UVB rays, though there's also UVC, which fortunately gets filtered out by the ozone layer before it can turn us all into crispy critters. UVA penetrates deep into your skin and ages you prematurely, which is annoying but not immediately fatal. Think of it as nature's very aggressive anti-aging reminder that you should probably reapply that sunscreen. UVB though? UVB is a molecular wrecking ball. It slams into your DNA and causes mutations, breaks chemical bonds, generally wreaks havoc at the cellular level. Too much UVB exposure, and you're looking at skin cancer somewhere down the line. Melanoma, basal cell carcinoma, squamous cell carcinoma. Take your pick from the menu of things that will definitely ruin your day. But here's the thing. Skin cancer, while serious, typically develops later in life, often after people have already reproduced. From an evolutionary perspective, something that kills you after you've had kids doesn't create strong selective pressure. Evolution is brutally practical that way. It cares about whether you successfully pass on your genes, not whether you live to a ripe old age. Harsh, but that's the game. So while skin cancer was certainly a problem for our ancestors, it wasn't the primary evolutionary force driving the development of dark skin. The real evolutionary pressure came from something much more immediate and devastating: the destruction of folate. Folate, also known as vitamin B9, is one of those nutrients that doesn't get nearly enough credit for keeping you alive. It's essential for DNA synthesis, cell division, and, here's the critical part, fetal development. When a woman is pregnant, folate is absolutely crucial for the developing embryo's neural tube formation. The neural tube eventually becomes the baby's brain and spinal cord. Without sufficient folate, you get neural tube defects, spina bifida, and encephaly, conditions that are either fatal or severely debilitating. And here's the problem. UV radiation destroys folate, just straight up breaks it down. A light-skinned person standing in equatorial African sunlight can lose up to 50% of their folate levels in an hour. 1 hour. That's not a gentle evolutionary pressure. That's a biological catastrophe waiting to happen. So imagine you're an early human living in East Africa 300,000 years ago. You need to be outside. There's no work from home option here. No shade structures, no SPF 50 sunscreen, no wide-brimmed hats from your favourite boutique. You're out there hunting, gathering, tracking animals across open grassland in full sun for 10, 12, maybe 14 hours a day. If you don't have protection from UV radiation, your folate levels plummet. Women with depleted folate have pregnancy complications. Babies are born with severe defects. Those genetic lines don't survive. It's brutal, but evolution doesn't do participation trophies. Enter melanin, the molecular hero of this story. Dark skin, really dark skin, the kind produced by high concentrations of eumelanin, absorbs and scatters UV radiation before it can penetrate to the living layers of your skin. It's like having a built-in hazmat suit specifically designed for solar radiation. And the beautiful thing? It's not an all-or-nothing system. Melanin doesn't block 100% of UV rays, which would be a problem for a different reason we'll get to in a moment. It blocks just enough to protect your folate, while still allowing some UVB through to trigger vitamin D synthesis. It's a perfect evolutionary calibration, tuned over thousands of generations to the specific intensity of equatorial sunlight. Think about that for a second. Your dark-skinned African ancestor could spend all day under a sun that would absolutely wreck a light-skinned person, and they'd be fine. Their folate levels stayed stable, their babies developed normally. They could hunt during the hottest part of the day, which is actually when many animals are resting and easier to track. They had a biological advantage that was so powerful, so essential, that for 240,000 years, let that number sink in, 240,000 years, dark skin remained universal among humans. There was zero evolutionary pressure to change it. Dark skin was evolutionary perfection for the environment where humans evolved. But here's where we need to pause and address something important, because there's often confusion about what evolutionary perfection means. It doesn't mean superior in some cosmic sense. It doesn't mean dark skin is inherently better than light skin as a general principle. Evolution doesn't do better or worse. It does well adapted to specific conditions, or poorly adapted to specific conditions. Dark skin was perfectly adapted to equatorial Africa, where the UV index regularly hits 10 or 11, levels that are classified as extreme by modern standards. Your melanin-rich skin wasn't just useful in that environment, it was mandatory. Light skin in that environment would have been an evolutionary death sentence. And this is where we need to talk about vitamin D, because it's the other half of this molecular balancing act. Vitamin D isn't actually a vitamin in the traditional sense. It's a hormone that your body synthesizes when UVB radiation hits a cholesterol compound in your skin. This hormone is absolutely essential. It regulates calcium absorption, bone development, immune function, and about 36 other critical processes. Without enough vitamin D, children develop rickets, soft, deformed bones that don't support body weight properly. Adults develop osteomalacia, a painful softening of the bones. But here's the thing. In equatorial Africa, you don't need much UVB penetration to make plenty of vitamin D. The sun is so intense that even heavily melanated skin allows through enough UVB to keep vitamin D production humming along nicely. So there you have it. Dark skin protecting folate, while still permitting just enough UV through for vitamin D synthesis. It's an elegant solution to a complex problem, and it worked flawlessly for 250,000 years. Every human being on Earth from roughly 300,000 years ago to about 60,000 years ago had dark skin. Every single one. This wasn't one race among many. This was what humans looked like, period. Light skin hadn't been invented yet. Now let's talk about what happened when some of these dark-skinned humans decided to leave home. And by leave home, I mean embark on one of the most consequential migrations in the history of any species on this planet. Somewhere between 100,000 and 60,000 years ago, the dates are still being refined as we dig up more archaeological evidence, groups of humans began moving out of Africa. Not all at once, not in some organized exodus with a leader and a plan. These were small groups, maybe a few dozen to a few hundred individuals, gradually pushing into new territories over many generations. Why did they leave? Well, that's the million-dollar question, isn't it? Humans had been doing just fine in Africa for hundreds of thousands of years. They had food sources they understood, territories they knew, ecosystems they were adapted to. So what would possess you to pack up and wander into completely unknown terrain, away from everything familiar? The honest answer is we don't know for certain. We can't interview these ancient migrants and ask them what they were thinking. But we can make some educated guesses based on what we know about human behaviour and what the archaeological and climate records tell us. Climate change was almost certainly a factor. Between 150,000 and 70,000 years ago, Earth was going through some dramatic climate fluctuations. Ice ages advancing and retreating, sea levels rising and falling by hundreds of feet, rainfall patterns shifting. The Sahara, which is a massive desert today, went through multiple cycles of green Sahara periods where it was actually covered in grassland and lakes. Imagine that, the Sahara with rivers and vegetation and game animals. Then the climate would flip, and the whole region would dry out again, turning back into the inhospitable sand sea we know today. These climate swings would have pushed human populations around, opened up new migration routes, and closed off old ones. Population pressure might have played a role too. Archaeological evidence suggests human populations were growing during this period. More people means more competition for resources. If your local area is getting crowded, and there's a whole empty continent to the north that looks promising, well, some adventurous souls might decide to see what's out there. It's the same impulse that drove humans to cross the Bering Land Bridge into the Americas, to sail across the Pacific to tiny islands, to basically spread to every habitable corner of the planet. Humans are curious. We explore. It's hardwired into us. There's also evidence that these early migrations followed specific routes that were newly accessible. One major route appears to have been along the coastline, out of East Africa, across the southern end of the Red Sea when sea levels were low enough to expose land bridges or shallow crossings, then hugging the Arabian Peninsula coast, then along the southern coast of Asia, eventually reaching Australia by about 65,000 years ago. This coastal route had serious advantages. Seafood is extraordinarily rich in protein and omega-3 fatty acids, which are excellent for brain development. Good news if you're trying to evolve bigger, more complex brains. Coastal areas have relatively stable climates compared to inland regions. You don't get those extreme temperature swings, and perhaps most importantly, you can literally follow the shoreline without getting lost. Can't overstate how useful that is when you don't have maps, compasses, or GPS navigation. Keep the water on your right is a navigation strategy that works surprisingly well, though it does require you to remember which direction you're travelling. The archaeological evidence for this coastal route is actually pretty sparse, which makes sense when you think about it. These people were living at sea level 60,000 years ago, and sea levels have risen hundreds of feet since then. Most of their campsites, tools and remains are now underwater on the continental shelf. We're essentially trying to reconstruct a migration path where most of the evidence is buried under 100 feet of ocean. Not exactly ideal research conditions. But the genetic evidence is solid, and the handful of archaeological sites that were located far enough inland to survive the sea level changes tell a consistent story. Humans moving along coastlines, eating shellfish, living in temporary camps, gradually pushing eastward. Another major route went north through the Nile Valley and into the Middle East. The Nile, conveniently, is basically a 4,000-mile-long highway of water and resources cutting straight through what would otherwise be absolutely barren desert. You've got reliable fresh water, which is nice if you enjoy not dying of thirst. You've got fish, birds, vegetation along the riverbanks. You've got papyrus reeds for making boats and shelters. Follow the river north, and eventually you hit the Nile Delta and the Mediterranean coast. From there, you can branch east into the Levant, modern-day Israel, Lebanon, Syria, Jordan. From the Levant, you can go further east into Mesopotamia, following the Tigris and Euphrates rivers, or you can head west along the North African coast toward what's now Libya, Tunisia, Algeria. Or you can push northeast into Anatolia, modern Turkey, and from there into Europe proper, or across the Caucasus into Central Asia. These routes weren't highways with rest stops and tourist information centres. They were dangerous, unpredictable, and full of challenges these migrants had never encountered before. New predators, lions and hyenas they might recognise from Africa, but also European cave bears, which were significantly larger and more aggressive than anything they'd dealt with before. Cave bears, by the way, could weigh up to 1,500 pounds and stood 10 feet tall on their hind legs. Encountering one of those in a narrow valley must have been absolutely terrifying. New prey animals with different behaviours and migration patterns. New plants, some edible, some poisonous, and you had to figure out which was which through trial and error, which is a polite way of saying some people definitely ate the wrong berries and died horribly. New diseases they had no immunity to. New climates requiring different survival strategies. And let's talk about climate for a moment, because the weather these migrants encountered would have been utterly alien to people whose ancestors had lived for hundreds of thousands of years near the equator. Imagine experiencing your first winter. You're from a region where temperature barely fluctuates, where it might get coolish at night but never what you'd call cold. Then you migrate north, and suddenly the temperature drops 20, 30, 40 degrees. Water starts falling from the sky in frozen chunks. Snow, which you have no concept for because it doesn't exist where you're from. Rivers freeze solid. You can walk on water, which must have been simultaneously terrifying and fascinating. Animals disappear or hibernate. Plant growth stops entirely. The days get shorter and shorter until the sun is barely up for a few hours. If you don't have serious cold weather survival skills, clothing made from animal hides, controlled fire, insulated shelters, you die. And these migrants had to figure all of this out on the fly, without instruction manuals or YouTube tutorials. Just trial and error, with the emphasis on error for the groups that didn't make it. These migrants probably didn't plan to colonize new continents. They were likely just following game animals, or looking for better foraging grounds, or fleeing conflicts with neighbouring groups, or simply wandering to see what was over the next hill. But generation by generation they pushed further and further from Africa. And here's the thing nobody tells you about this migration. These humans had absolutely no idea they were carrying an adaptation that was about to become a serious liability. Remember, they had dark skin perfectly calibrated for intense equatorial sunlight. That skin served them beautifully as they moved through Arabia, through the Middle East, even into southern Europe and southern Asia. But as generations passed and populations pushed further north, they were entering territories where the rules of the game were fundamentally different. Let's talk about what happens to sunlight as you move away from the equator. At the equator, the sun is almost directly overhead for much of the year. Sunlight travels through a relatively thin slice of atmosphere before hitting the ground. UV radiation is intense and consistent. But as you move north or south toward the poles, the angle changes. The sun sits lower in the sky. Sunlight has to travel through a much thicker slice of atmosphere, which scatters and absorbs UV radiation. The further you get from the equator, the weaker the UV radiation becomes. And here's the real kicker. In northern latitudes, there are entire months during winter where the sun barely rises above the horizon. The days are short, the angle is extreme, and UVB radiation is basically non-existent. Now, if you're a dark-skinned human who just spent the last several thousand years migrating north into, say, northern Europe, you're about to encounter a problem your ancestors never had to deal with. Your melanin-rich skin, which was perfect for blocking excessive UV in Africa, is now blocking the weak UVB radiation you desperately need to synthesize vitamin D. Remember, vitamin D production requires UVB to hit that cholesterol compound in your skin, but your melanin is absorbing and scattering most of that UVB before it can do its job. In equatorial Africa, this wasn't a problem because there was so much UVB that even after melanin blocked most of it, plenty still got through. But in northern latitudes, especially during winter, there's barely any UVB to begin with. Your dark skin is blocking something that's already scarce, and that's where the trouble starts. Vitamin D deficiency is not a minor inconvenience. It's not like being a little tired or having a minor headache that goes away if you drink some water. Severe vitamin D deficiency causes rickets in children and osteomalacia in adults, and both conditions are absolutely brutal. Rickets manifests as soft, bendable bones, and yes, I mean bendable like rubber, not bendable like has some flexibility. Children with rickets develop bowed legs because their leg bones literally cannot support their body weight. Imagine your shin bones bending outward like someone sat on a foam tube. They get deformed rib cages where the rib joints swell up and create these visible bumps along the chest, giving it an appearance doctors rather cheerfully call a rachitic rosary, because nothing says festive jewellery like deformed skeletal. Structure. Their skulls remain soft and misshapen, creating a squared-off appearance. Their spines curve. They're short because their bones aren't growing properly. They're weak because their muscles can't function correctly without adequate calcium. And they're in constant pain because, surprise, having soft bendy bones pressing on nerves and ligaments hurts. Osteomalacia causes similar problems in adults. bone pain that feels like deep aching throughout your entire skeleton, muscle weakness so severe that climbing stairs becomes a major undertaking, difficulty walking without a shuffling gait. Adults with osteomalacia have bones that literally bend and fracture under normal stress. You could break a rib just from coughing too hard, fracture your vertebrae from lifting something slightly heavy. It's not a condition that inspires confidence in your body's structural integrity. But here's the evolutionary sledgehammer, the thing that really cranks up the selective pressure to 11. Women with childhood rickets who survive to adulthood often develop severely deformed pelvises. Their pelvic bones don't grow correctly, which means the pelvic opening, that rather important passageway through which babies need to exit the womb, ends up too narrow, misshapen, or blocked by inward projecting bone spurs. In medical terms, this is called a contracted pelvis. In practical terms, it means that when these women get pregnant and try to give birth, the baby literally cannot fit through the birth canal. The baby's head is stuck. And before modern medicine, before cesarean sections, before forceps delivery, before any of the interventions we take for granted today, this was a death sentence for both mother and child. The mother would labour for hours, sometimes days, with the baby trapped. Eventually, either the mother would die from exhaustion, hemorrhage, or infection, or the baby would die from lack of oxygen, or both would die. It's one of the most horrific ways to die, and it was completely preventable with adequate vitamin D. Think about the evolutionary pressure that creates, not might have some trouble reproducing pressure. Not your offspring will be slightly less fit pressure. Complete, absolute, you don't pass on your genes at all pressure. A woman with severe rickets in childhood reaches reproductive age, gets pregnant, which, let's be honest, in a hunter-gatherer society without birth control was basically inevitable if you were healthy enough to be sexually active, and then she can't. Deliver the baby. She dies. The baby dies. That's it. Game over. Her genes don't continue. This is natural selection at its most brutal and uncompromising. If your genes produce dark skin in a low UV environment, leading to vitamin D deficiency, leading to rickets, leading to obstructed labour, those genes are done. Finished. Deleted from the gene pool. Think about the evolutionary pressure that creates. A woman with severe vitamin D deficiency in childhood develops rickets. Her bones deform. She reaches adulthood, gets pregnant, which, in a hunter-gatherer society without contraception, was pretty much inevitable if you were healthy enough to reproduce. And then she can't deliver the baby. She dies in childbirth. The baby dies. That genetic line ends. This isn't a slow, subtle, selective pressure. This is immediate, brutal, and absolute. If you can't make enough vitamin D, you don't reproduce successfully. End of story. So here's the situation these ancient northern migrants found themselves in. They had dark skin optimized for intense UV exposure, but they were now living in places with weak, seasonal UV exposure. They needed vitamin D, but their skin was blocking the very radiation required to make it. They were, to put it mildly, in trouble. And they didn't have the option of just taking vitamin D supplements or drinking fortified milk. Unfortunately for them, the vitamin supplement industry wouldn't exist for another 60,000 years or so. They couldn't exactly order cod liver oil capsules from ancient Amazon Prime. But here's where evolution gets interesting. These populations didn't just die out. They adapted. And the way they adapted was through random genetic mutations that, purely by chance, solved the vitamin D crisis. We'll get into the specific genetics later, but here's the short version. Occasionally, a child would be born with a mutation that reduced melanin production. That child would have lighter skin than their parents. In Africa, this would have been a disadvantage. Less UV protection, higher risk of folate depletion, higher risk of skin cancer from excessive sun exposure. But in northern latitudes, suddenly lighter skin was an advantage. Less melanin meant more UVB penetration. More UVB penetration meant better vitamin D synthesis. Better vitamin D meant healthier bones, successful pregnancies, surviving children. Those lighter-skinned individuals had more surviving offspring, who inherited the lighter skin mutation, who had more surviving offspring, and within a relatively short time, maybe a few thousand years, which is nothing in evolutionary terms, entire. Populations had shifted from dark-skinned to light-skinned. This wasn't a conscious decision. Nobody sat down and thought, you know what, I think I'll evolve lighter skin. Evolution doesn't work that way. It was pure natural selection. The people who happened to have the right mutations in the right environment survived and reproduced more successfully than those who didn't. The population's genetic makeup shifted. And here's the wild part. This happened independently in multiple human populations. Europeans developed light skin through one set of genetic mutations. East Asians developed light skin through a completely different set of mutations. Convergent evolution, different populations, same environmental pressure, same solution, different genetic paths to get there. But we're getting ahead of ourselves. Right now, we're still in that transitional period where humans are migrating out of Africa, spreading across Europe and Asia, and still mostly dark-skinned. They don't know yet that their skin colour is going to be a problem. They're just trying to survive, find food, avoid predators, raise children, and figure out how to live in these strange new places where winter exists, which, let me tell you, must have been absolutely baffling to people whose ancestors had lived for hundreds of thousands of years near the equator where temperature barely changes. Imagine experiencing snow for the first time in your genetic lineage. Imagine trying to explain to your children what's happening when water starts falling from the sky in frozen white chunks. No, it's not dangerous, I think. Let's just see what happens. These migrants were carrying with them the genetic legacy of 240,000 years of equatorial adaptation. Their bodies were fine-tuned machines for a specific environment, and now they were operating in radically different conditions. It's like taking a Formula One race car designed for smooth tracks and trying to drive it through a muddy field. It'll still move, but you're going to encounter some serious problems. Their dark skin, which had been an unqualified blessing in Africa, was about to become one of the most intense selective pressures in human evolution. The populations that could adapt quickly would thrive. The ones that couldn't would struggle, shrink, and potentially disappear entirely. And here's something that often gets overlooked in these discussions. This migration wasn't a single event. It wasn't one group leaving Africa and spreading everywhere like water flowing across a flat surface. The archaeological and genetic evidence suggests multiple waves of migration over tens of thousands of years, with complex patterns of movement, replacement, and intermixing that we're still trying to untangle. Some groups left Africa and thrived, establishing populations that persisted for thousands of years. Some groups left and died out after a few generations, leaving behind only faint genetic traces and scattered archaeological remains. Some groups left, established populations, and then got replaced by later waves of migrants who either outcompeted them or absorbed them through interbreeding. Some groups left Africa, then came back, then left again in later generations. The human story is messy, complicated, and full of dead ends and false starts, not a neat linear progression from point A to point B to point C. We know, for example, that early modern humans reached the Levant around 100,000 years ago. There's archaeological evidence of human occupation at sites like Skull Cave and Kafsa Cave in Israel, dating to roughly that period. But that population seems to have died out or retreated back to Africa. Maybe the climate shifted and made the region inhospitable. Maybe they got outcompeted by Neanderthals, who'd been living in the region much longer and were better adapted to local conditions. Maybe disease wiped them out. Maybe they just had bad luck with rainfall and food availability for a few critical generations. We don't know. What we do know is that modern human presence in the Levant disappears from the archaeological record for tens of thousands of years. Then, around 60,000 to 70,000 years ago, another wave of humans left Africa, and this time they made it stick. These were the successful migrants, the ones whose descendants eventually spread across the entire world. They pushed through the Middle East, fanned out across Asia, reached Australia by island hopping through Southeast Asia, which required boat technology and navigation skills we're not entirely sure how they developed, moved into Europe where they encountered and eventually replaced the Neanderthals, crossed into the Americas via the Bering Land Bridge, and basically colonized every habitable continent except Antarctica. These were the ancestors of everyone alive today outside of Africa, and crucially for our story, they were still dark-skinned. The genetic evidence is absolutely fascinating on this point. When scientists analyze DNA from ancient human remains, which they can do now with increasingly sophisticated techniques, they can actually look at specific genes that control skin pigmentation and make pretty accurate determinations about what color skin that person probably had. They can identify which versions of genes like SLC24A5, SLC45A2-TYR, and others that person carried, and from that infer their skin tone with reasonable confidence. And what they've found completely upends some common assumptions about when and where light skin evolved. A famous example is Cheddar Man, a skeleton found in Gough's Cave in Somerset, England, dating to about 10,000 years ago. For decades, he was depicted in museum reconstructions as a light-skinned European, because that seemed obvious, right? He was found in England. British people are generally light-skinned. Therefore, this ancient British person must have been light-skinned. Logical enough. Except when scientists finally analysed his DNA in 2018, they discovered he had dark brown to black skin, dark curly hair, and blue eyes, a combination that seems bizarre and contradictory to modern sensibilities, but makes perfect evolutionary sense. When you understand the timeline, his ancestors had been in Europe for several thousand years, long enough for the genes controlling eye colour to mutate toward lighter pigmentation. Blue eyes actually evolved relatively quickly, because they don't have the same survival implications as skin colour, but not long enough for skin colour to change significantly. He was living proof that humans in Europe were still quite dark-skinned as recently as 10,000 years ago, right in the middle of what we think of as European territory. Other examples abound. La Braña Uno, a skeleton from Spain dating to about 7,000 years ago, also had dark skin and blue eyes. The Lochbour man from Luxembourg, about 8,000 years old, same pattern. These weren't isolated cases. They represent what seems to have been the norm for European populations during this period. Dark skin, but with some genes for light-coloured eyes and hair already spreading through the population. It's like evolution was working on these traits one at a time, gradually shifting the population toward lighter pigmentation, but not all at once. This tells us something important. The evolution of light skin happened relatively recently in human history. It wasn't some ancient change that happened hundreds of thousands of years ago. It happened within the last 30,000 years or so, with the bulk of the change occurring in the last 10,000 to 20,000 years. In evolutionary terms, that's yesterday. Light skin is brand new. It's one of the most recent significant evolutionary changes in the human species. You, if you're of European or East Asian descent, are carrying genetic mutations that your ancestors didn't have just a few hundred generations ago. Your 300th generation grandparents probably had significantly darker skin than you do. And this is where we need to confront a deeply uncomfortable truth that has massive implications for how we think about human diversity. The visible differences in skin colour that we use to categorise people into races are incredibly superficial and incredibly recent. We're talking about changes that happened so recently that, from a biological perspective, they barely register. The genetic difference between the darkest-skinned person and the lightest-skinned person on Earth comes down to maybe 15 genes out of roughly 20,000 total genes in the human genome. That's 0.075% of your genome. The genes that code for skin colour represent a tiny, tiny fraction of what makes you human. And yet these tiny genetic differences have been used throughout history to justify everything from slavery to genocide to apartheid to employment discrimination. But we're not there yet in our story. Right now, we're still in the phase where humans are migrating, struggling, adapting, and figuring out how to survive in new environments. They don't know that their descendants will develop light skin. They don't know that skin colour will become a marker of geographic ancestry. They don't know that thousands of years in the future, people will construct elaborate social hierarchies based on melanin content. They're just trying to not die of rickets. And here's something kind of darkly amusing when you think about it. These ancient humans probably had no idea what was killing them. They didn't know about UV radiation or folate or vitamin D or melanin or biochemistry or molecular biology or any of the concepts we're casually discussing here. They just knew that for some mysterious reason, a lot of children were being born with weak, deformed bones. A lot of women were dying in childbirth, screaming in agony as they tried unsuccessfully to deliver babies that wouldn't come. A lot of kids couldn't walk properly, couldn't grow to normal height, suffered from constant pain that nobody could explain or treat. And nobody could figure out why this was happening. Why us? Why now? Why are our children suffering when our grandparents' generation seemed fine? They probably blamed evil spirits, curses from angry gods, punishment for breaking tribal taboos, malevolent supernatural forces targeting their community. Maybe they performed rituals, made sacrifices, tried to appease whatever forces they thought were responsible. Maybe they blamed specific individuals. Women who gave birth to affected children might have been ostracized or accused of wrongdoing. The shaman or healer probably tried every remedy they knew: herbal poultices, ritual dances, appeals to the spirits, and watched helplessly as nothing worked. Because how do you fix a problem you can't see, can't understand, and don't even have the conceptual framework to think about correctly? They had no framework for understanding that the problem was literally in their skin, that the same pigmentation that protected their ancestors in Africa was now creating a deadly deficiency thousands of miles away. They couldn't see UV radiation. They had no instruments to measure it. They couldn't test their vitamin D levels. They couldn't do bone density scans or biochemical assays. They just knew something was profoundly wrong, and they were powerless to fix it. Imagine the frustration, the grief, the desperate confusion of watching your children suffer and die from a condition you don't understand and can't treat. It must have been absolutely devastating. Some groups probably didn't survive. If the vitamin D deficiency was severe enough, if the rickets rate was high enough, if too many women were dying in childbirth, the population would simply collapse. Not enough births to replace deaths. The group shrinks, becomes vulnerable to external threats, and eventually disappears. We don't have their stories because they didn't make it. We don't have their genes because they didn't pass them on. They're ghost populations in the archaeological record, maybe a few skeletal remains showing severe bone deformities, a handful of artifacts, and then nothing. The genetic line ends. But some groups got lucky. Not through wisdom or planning or any kind of conscious intervention, just blind, random genetic luck. Except evolution could fix it. Slowly, randomly, brutally, but effectively. Mutations happened. Lighter-skinned babies were born. Those babies survived better than their darker-skinned siblings. The frequency of light-skinned genes increased in the population. Over thousands of years, the population shifted from dark to light. Problem solved, at least for that particular environmental challenge. Of course, this created a whole new set of problems when those light-skinned populations later migrated to high UV areas, but that's a story for later. The point is, skin colour isn't a fixed characteristic of humans. It's a highly adaptive trait that responds to local UV conditions through natural selection. Humans aren't supposed to be any particular colour. We're supposed to be whatever colour maximises survival and reproduction in our specific environment. In equatorial Africa, dark skin is optimal. In northern Europe, light skin is optimal. In between, you get intermediate skin tones that represent a compromise between folate protection and vitamin D synthesis. It's not about better or worse, it's about matching your biology to your latitude. And this is why the migration out of Africa is such a crucial chapter in human history. It's the moment when humans stopped being a single, relatively uniform population, adapted to one type of environment, and became multiple populations adapting to radically different environments. It's when genetic diversity really started to explode. It's when the evolutionary pressures that would eventually create visible differences in appearance kicked into high gear. Everything that happened after, the development of light skin, the evolution of different eye colours and hair colours and facial features, the genetic adaptations to high altitude or extreme cold or different diets, all of that stems from this initial migration when a small number of dark-skinned Africans decided to see what was beyond the horizon. They had no idea what they were starting. They had no idea their descendants would spread across the entire planet. They had no idea their skin colour would change. They certainly had no idea that 60,000 years later, scientists would be digging up their bones, analysing their DNA, and writing long educational videos about the evolutionary pressures they experienced. They were just people, trying to survive, trying to feed their families, trying to make sense of the world around them. And in the process, they kicked off one of the most remarkable adaptive radiations in the history of any species. So that's where we are in the story. Humans have left Africa in multiple waves over tens of thousands of years. They're spreading across the globe, encountering environments radically different from the African savanna where they evolved. They're dealing with new predators, new prey, new plants, new diseases, new climates that range from tropical rainforests to Arctic tundra. And most importantly for our narrative, they're encountering very different levels of UV radiation. Some populations are settling in regions with intense sun, southern India, Southeast Asia, northern Australia, where their dark skin continues to serve them well. But other populations are pushing into northern Europe, northern Asia, high-altitude regions, places where the sun is weak, the winter days are short, and UVB radiation is scarce for months at a time. And their bodies are about to undergo one of the most rapid and dramatic evolutionary changes in human history. Their skin is about to transform from dark to light in some populations, while remaining dark in others. This transformation will be driven by nothing more complicated than survival. The simple, brutal, elegant logic of natural selection operating on random genetic mutations. The populations that happen to produce children with mutations that reduce melanin production will find those children survive better, reproduce more successfully, and gradually shift the entire population's genetic makeup toward lighter skin. The populations that don't produce those mutations, or produce them but don't experience enough selective pressure for them to spread, will remain dark-skinned. And here's what's remarkable. This is going to happen independently in multiple populations. Europeans will develop light skin through one set of genetic mutations. East Asians will develop light skin through a completely different set of mutations. They'll arrive at the same solution, reduce melanin to allow more UVB penetration, through different genetic pathways. It's like two engineers solving the same problem with different tools. The result looks similar, but the mechanism is different. That's convergent evolution in action, and it's powerful evidence that skin color is purely an environmental adaptation, not some inherent characteristic that defines populations, but we're getting ahead of ourselves. The next chapter of this story is going to dive deep into the molecular mechanisms of how this transformation happened. We'll look at the specific genes involved, SLC24A5, SLC45A2, TYR and others, and examine exactly what happens when a single letter in your DNA changes from an A to a G or a C to a T. We'll explore the shocking speed at which these changes occurred in some populations. We'll investigate why different populations evolved light skin through different genetic routes. We'll look at the exceptions, populations that stayed dark-skinned despite living at high latitudes, or populations that have intermediate skin tones that represent a compromise between different selective pressures. But for now, just sit with this image. Hundreds of generations of dark-skinned humans, perfectly adapted to African sunlight, walking into northern winters completely unprepared for the molecular crisis their bodies were about to face. They couldn't see the problem. They couldn't understand it. They couldn't deliberately solve it. But evolution could, and evolution did, through the merciless filtering of natural selection acting on random genetic variation. The mutations that solved the vitamin D crisis spread like wildfire through these populations. The mutations that didn't solve it disappeared along with the people who carried them. Your skin, if you're of European or East Asian descent, is lighter than your ancestors' skin was 20,000 years ago. That's not ancient history in evolutionary terms. That's practically yesterday. Your 600th generation grandmother probably had noticeably darker skin than you do. Your 1000th generation grandfather almost certainly did. These changes happened within recorded human history, within the time frame of agriculture and civilization and written language. Light skin is new. It's recent. It's one of the most dramatic examples of rapid evolutionary change in a large mammal species that we know of. And it happened because groups of dark-skinned humans, through nothing more than curiosity and circumstance, and the endless human drive to see what's over the horizon, walked into environments where their perfectly evolved skin became a liability, instead of an asset. Evolution was about to write a new chapter on their skin. And that chapter, with all its molecular complexity, its surprising speed, its multiple independent origins, and its profound implications for how we think about human diversity, is still being written today. The story of skin color is still unfolding. People continue to migrate, populations continue to mix, new selective pressures emerge, old adaptations persist or fade. And all of it, every bit of it, can be traced back to those first brave or foolish or desperate groups of dark-skinned Africans who decided to leave the only home humanity had ever known and venture into the unknown. They couldn't have imagined where their journey would lead. They couldn't have predicted how their descendants' bodies would change. But they took the first step, and everything else followed from that single decision to explore. Now let's talk about what happens when you take a human body specifically engineered for equatorial conditions and drop it into northern Europe. Because this is where the story gets really interesting, and by interesting, I mean potentially catastrophic for entire populations. the migrants who pushed north into what's now Scandinavia, the British Isles, northern France, Germany, Poland, and Russia were walking into an environmental trap that their biology was completely unprepared to handle. And the thing is, the trap wasn't immediately obvious. It took years, sometimes decades, for the full consequences to become apparent. You couldn't just arrive in Sweden and instantly know you were in trouble. The disaster was slow motion, multi-generational, and utterly mystifying to the people experiencing it. Let's start with the physics, because understanding why northern latitudes are so different requires understanding what happens to sunlight as you move away from the equator. At the equator, the sun rises nearly straight up, passes almost directly overhead at noon, and sets nearly straight down. The path sunlight takes through the atmosphere is relatively short, maybe 30 or 40 miles of air between the sun and your skin. At 60 degrees north, which is roughly where Stockholm, Oslo and St. Petersburg sit, the geometry is completely different. The sun never gets that high in the sky. Even at the summer solstice, when the sun is at its peak, it's still coming in at an angle, and in winter, forget about it. The sun barely clears the horizon. At noon in Stockholm in December, the sun sits about 6 degrees above the horizon. For comparison, your thumb at arm's length covers about 2 degrees of sky, so the winter sun in Stockholm is sitting maybe 3 thumb widths above the horizon at its highest point. That's not very high. And when sunlight comes in at such a low angle, it has to travel through a much, much thicker slice of atmosphere before reaching the ground. Instead of 40 miles of air, you're looking at 200, 300, maybe 400 miles, depending on the angle. And as that light travels through all that extra atmosphere, something happens. The atmosphere scatters and absorbs it. Particularly UV radiation, which is exactly what we care about for vitamin D synthesis. UVB rays are relatively short wavelength high-energy photons, which means they interact strongly with molecules in the atmosphere. Ozone, oxygen, nitrogen, water vapor, dust particles, all of it. Every interaction is a chance for that UVB photon to get absorbed or scattered away in some random direction. By the time the remaining sunlight reaches the ground in northern latitudes during winter, most of the UVB has been filtered out. What you're left with is mostly visible light and some UVA, which is nice for seeing where you're going but useless for making vitamin D. But it gets worse, because we're not just talking about angle, we're also talking about day length. At 60 degrees north latitude, winter days are brutally short. In Stockholm on the winter solstice, December 21st, the sun rises around 8:47 a.m. and sets around 2:46 p.m. That's less than 6 hours of daylight. Less than 6 hours of weak low-angle sunlight that's already been stripped of most of its UVB radiation. Compare that to the equator, where you get roughly 12 hours of daylight year-round, and the sun is much more directly overhead, and UVB radiation is intense. The difference is staggering. A person standing outside in Nairobi at noon is getting absolutely blasted with UVB. A person standing outside in Stockholm in January is getting essentially nothing, UV-wise. You could stand there naked for hours, not recommended for other reasons, mostly involving hypothermia, and you still wouldn't synthesize meaningful amounts of vitamin D. Now imagine you're a dark-skinned human who just migrated to this environment over the course of several generations. Your great-great-grandparents started the journey in East Africa. Your great-grandparents made it to the Middle East. Your grandparents pushed into Central Europe, and you were born in what's now northern Germany or southern Scandinavia. You have dark skin packed with melanin, which is still doing its job of blocking UV radiation, except now there's barely any UV radiation to block. Your skin is like a really effective umbrella in a place where it almost never rains. The protection is still there, but the thing you're being protected from isn't the problem anymore. The problem is that you need some of that UVB to penetrate your skin, and your melanin is blocking the little bit that makes it through the atmosphere. Let's put some numbers on this to make it concrete. A light-skinned person in northern Europe during summer might need about 10 to 15 minutes of midday sun exposure on their arms and legs to produce adequate vitamin D. Not a huge ask. But a very dark-skinned person in the same location might need 2, 3, 4 times longer to produce the same amount, 30 minutes, an hour, maybe more, because their melanin is absorbing and scattering most of the UVB before it can trigger vitamin D. Synthesis. And that's during summer. During winter, when UVB levels are so low that vitamin D synthesis essentially stops regardless of skin colour, everyone is running on stored vitamin D from the summer months. If you're light-skinned and manage to build up decent stores during the summer, you might make it through winter okay. If you're dark-skinned and couldn't synthesize enough vitamin D even during the summer months because your melanin was blocking too much, well, you're going into winter already depleted, and winter lasts a long time up there. We're talking 4, 5, 6 months of minimal to zero vitamin D synthesis. That's a long time to run on empty. And here's where the crisis manifests in ways that would have been absolutely devastating to ancient populations. Children are the first victims because they're growing. Their bones are actively developing, mineralizing, lengthening, thickening. That process requires calcium, and calcium absorption requires vitamin D. Without adequate vitamin D, you get rickets, which we've already discussed. But let's go deeper into what that actually looked like in these ancient populations. Picture a settlement of dark-skinned migrants somewhere in northern Europe, maybe 15,000 years ago. They've been there for a few generations. The adults, who grew up in more southern regions with more sun exposure, might be relatively okay. They reached adulthood with reasonably healthy bones. But their children, born and raised in this low UV environment, start showing problems around age 2 or 3. That's when kids start walking, and that's when the mechanical stress on their bones reveals the underlying weakness. A child with rickets doesn't just have weak bones in some abstract sense. Their leg bones bow outward or inward because the bones are literally soft enough to deform under the child's body weight. Every step is bending the bone slightly. Over months and years, the bowing becomes pronounced. The child develops a distinctive waddle-like gait because their leg bones don't point straight down anymore. They curve. It's not subtle. You can see it from across a room. And it's not just the legs. The rib cage develops these bulbous swellings where each rib connects to the sternum. That rachitic rosary doctors named it, in a moment of either extremely dark humour or spectacular insensitivity. The spine curves, creating humped backs or severe forward stooping. The skull bones remain soft and can develop flat spots or asymmetric shapes from the child sleeping on one side. Dental development is delayed, and teeth that do come in are weak and prone to cavities and breaking. These children are in pain, bone pain, muscle pain, joint pain. They tire easily because their muscles can't work properly without adequate calcium regulation. They're short because their bones aren't growing to their genetic potential. They're weak, sickly, and in a hunter-gatherer society that requires mobility, stamina, and physical capability, they're at a severe disadvantage. And remember, this is happening to a significant portion of the children in these northern migrant populations. Not just one unlucky kid. We're talking potentially 30%, 40%, even 50% of children showing some degree of rickets, depending on how severe the vitamin D deficiency is in the population. That's a demographic catastrophe waiting to happen. But the real evolutionary guillotine falls on women, because women with childhood rickets who survive to reproductive age face that pelvic deformity problem we touched on earlier. Let's be really clear about what this means in practical terms. A female child with rickets develops bowed leg bones, but she also develops deformities in her pelvic bones. The pelvis is a complex structure. It's basically a ring of bone that has to serve two competing purposes. It needs to be sturdy enough to support your upper body weight and transfer that load to your legs. But it also needs to have an opening in the middle large enough for a baby to pass through during birth. In a healthy female, this pelvic opening, the birth canal, is roughly oval-shaped and adequately sized for a newborn's head to fit through with some difficulty but not impossibility. It's a tight squeeze even under the best circumstances, which is why human childbirth is so painful and dangerous compared to most other mammals. But it works, usually. In a girl with rickets, the pelvic bones don't develop normally. They can curve inward, narrowing the pelvic opening. They can develop irregular shapes or protrusions. The whole structure can be tilted or asymmetric. By the time this girl reaches adulthood, if she reaches adulthood, which isn't guaranteed given the other health problems associated with rickets, her pelvic opening might be 20%, 30%, even 40% smaller than normal. Or it might be misshapen so that even if the total area is adequate, the geometry is all wrong and a baby's head can't navigate through it. This is called a contracted pelvis, or rachitic pelvis in medical terminology, and it's a death sentence in a world without caesarean sections. Let's walk through what happens. A woman with a contracted pelvis gets pregnant. The pregnancy proceeds normally for 9 months. Vitamin D deficiency during pregnancy has other complications, but let's focus on the birth itself. Labour begins, contractions start. The baby starts moving down into the birth canal. and then the baby's head hits bone. The baby literally cannot fit through the opening. The woman pushes. Nothing happens. She pushes harder. Still nothing. The labor goes on for hours, then a day, then 2 days. The woman is exhausted, in agony, losing blood, possibly developing infections. The baby is stuck in the birth canal, being compressed by contractions, running out of oxygen. There's no way forward, no way back, no surgical intervention available. Eventually, and this is the grim reality, both the mother and baby die. The mother from exhaustion, hemorrhage, infection, or some combination thereof. The baby from oxygen deprivation, or physical trauma from the prolonged compression. It's one of the most horrific ways to die, and it was happening regularly in these northern populations with severe vitamin D deficiency. Think about the evolutionary implications. If 40% of your girls develop rickets, and half of those develop pelvic deformities severe enough to cause obstructed labour, you're looking at 20% of your females dying in their first childbirth. That's not just a tragedy, that's a population bottleneck. Worse, it's a bottleneck that specifically removes women from the gene pool, which means fewer babies being born in the next generation, which means your population is shrinking. And it's not random which women are dying. It's specifically the women with the genetics for dark skin, because their children are the most likely to develop severe rickets in this low UV environment. The genes for dark skin are being actively selected against, filtered out of the population by death. This is natural selection at its most brutal and most efficient. Now, you might be wondering, couldn't these ancient people do something about this? Couldn't they change their behaviour to compensate? And the answer is, they tried, but the options were limited. Let's think about what behavioural adaptations might help. First option, spend more time outside in the sun. Okay, but if you're living at 60 degrees north latitude and it's January and the sun is barely above the horizon for 5 hours a day, you can spend all day outside and still not synthesize meaningful vitamin D. Plus, you're in Ice Age Europe. It's cold, temperatures are well below freezing. Standing outside naked trying to maximize your sun exposure is going to give you hypothermia long before it gives you adequate vitamin D, not a viable strategy. Second option, wear less clothing to expose more skin to what little sun is available. This runs into the same problem, you're going to freeze to death. Humans in northern climates had to wear extensive clothing made from animal hides and furs just to survive the winter. Boots, pants, long tunics, cloaks, hoods, gloves. You couldn't walk around in a bikini maximizing your vitamin D synthesis, because you'd be a popsicle within hours. The climate demanded covering up, which meant less skin exposure, which meant less vitamin D production. It's a catch-22. The very adaptations that let you survive the cold, clothing, shelter, fire, also limit your ability to make vitamin D from sunlight. Third option, dietary sources of vitamin D. This is actually a viable strategy, and some populations did use it effectively, which we'll talk about in more detail later. But for these early migrants, dietary vitamin D would have come from things like fatty fish, fish liver, eggs, and certain organ meats. If you're living near the coast and have access to ocean fish, great. Eat a lot of salmon, mackerel, herring, and you can get significant vitamin D from your diet, potentially enough to compensate for low sun exposure. But if you're living inland, and many of these populations were, your access to fatty fish is limited or non-existent. Freshwater fish have much less vitamin D than ocean fish. Land animals have some vitamin D in their liver and fatty tissues, but not huge amounts. You'd need to eat a lot of liver, and even then, you might not be getting enough. And of course, we're talking about hunter-gatherers and early agriculturalists here. You eat what you can catch or gather or grow. You don't have the luxury of carefully balancing your nutrient intake to ensure optimal vitamin D levels. You eat what's available, which in northern Europe in winter is probably some stored grain, some preserved meat, maybe some roots you dug up before the ground froze, and whatever game you can hunt. Not exactly the Mediterranean diet. So behavioural adaptations could help, but they couldn't fully solve the problem. The only real solution was biological. Change the skin, make it lighter, allow more UVB through. And that's exactly what happened, but it took thousands of years of natural selection to accomplish. In the meantime, multiple generations of people lived through this crisis. They buried children with deformed bones. They watched women die in childbirth from preventable complications. They suffered through bone pain and muscle weakness and stunted growth, and they had no idea why it was happening. no framework for understanding the problem. No conception of vitamins or UV radiation or calcium metabolism. They just knew that life up here in the north was hard in ways it hadn't been for their ancestors. Let's talk about specific geographic regions, because not all of northern latitudes are created equal when it comes to UV radiation, and the differences matter tremendously when you're trying to synthesize vitamin D with dark skin. Scandinavia is absolutely brutal. Stockholm sits at about 59 degrees north. Oslo is 60 degrees north. Tromsø, up in northern Norway, is at 69 degrees north, well inside the Arctic Circle. These are high latitudes where winter days are incredibly short and summer nights barely exist. During winter solstice in Tromsø, the sun doesn't rise above the horizon at all for about 2 months. 0 daylight. Complete darkness except for a bit of twilight around noon. You get the midnight sun in summer, where the sun never fully sets, and you can read a book outside at 2 a.m., which is disorienting in its own right, and probably didn't do wonders for ancient people's sleep schedules. But that extra summer sun doesn't fully compensate for the winter darkness, because vitamin D synthesis is much more effective during midday when the sun is highest. And even during summer in these far northern regions, the sun never gets that high in. The sky. It's always at a relatively low angle, which means UVB has to travel through more atmosphere, which means less UVB reaches the ground. For a dark-skinned person living in Scandinavia 15,000 years ago, vitamin D synthesis would have been extremely challenging. Even during the best summer months with nearly 24 hours of daylight, the UVB intensity is relatively low compared to more southern latitudes. You'd need to spend many hours outside with skin exposed to make adequate vitamin D. And then winter hits, and vitamin D synthesis stops completely for 4, 5, 6 months depending on exactly how far north you are. Your body is living off whatever stores you built up during summer, and if those stores weren't adequate, you're in serious trouble by late winter. The selective pressure to develop lighter skin in Scandinavia was probably the strongest of anywhere in Europe, which is why modern Scandinavians tend to be very light-skinned, often with blonde or red hair and light-coloured eyes, multiple mutations, all working together to maximise UV sensitivity in an extremely challenging environment. The British Isles present a different set of challenges. London is at 51.5 degrees north, Edinburgh is 55.9 degrees north, not as extreme as Scandinavia, but still pretty far north. The latitude alone would create vitamin D challenges, but the British Isles have an additional complication: maritime climate. They're islands in the Atlantic surrounded by ocean, influenced by the Gulf Stream and constant weather systems rolling in from the west. This creates persistent cloud cover. The British Isles are famous, or infamous depending on your perspective, for grey, overcast skies. Ask anyone who's spent time in London or Edinburgh about the weather, and they'll probably mention the constant greyness. It's not that it rains all the time, though it does rain a lot. It's that it's cloudy all the time. Thick, low clouds that block sunlight even when it's not actually precipitating. And here's the problem. Clouds are remarkably effective at blocking UV radiation. A thick, overcast sky can block 50 to 90% of UV rays. So even during summer months when the sun is theoretically high enough and the days are long enough for vitamin D synthesis, if you've got cloud cover, you're not making much vitamin D. Imagine being a dark-skinned migrant in ancient Britain. It's June, the longest days of the year. You spend all day outside working, hunting, gathering, tending crops, whatever your subsistence strategy is. But the sky is grey and overcast, as it often is in Britain even during summer. Your dark skin is blocking what little UVB makes it through the clouds. At the end of the day, you've synthesized maybe 10 to 20% of the vitamin D you would have made on a clear sunny day. String together a few weeks of cloudy weather, not at all unusual in Britain, and you're falling behind on your vitamin D needs even during the prime synthesis season. Then winter comes, with its short days and low sun angle, and you're completely unable to make vitamin D. By February or March, you're severely deficient. Your bones are aching, your muscles are weak, and if you're a growing child, your skeleton is deforming. There's a reason British people have a reputation for being quite pale. It's a genuine adaptive response to a cloudy northern environment where every bit of UVB penetration matters. The selective pressure wasn't just about latitude, it was about cloud cover too. Populations in cloudier environments needed lighter skin than populations at similar latitudes but with clearer skies, because they had to maximise their vitamin D synthesis during those rare clear days, and make the most of whatever weak UVB made it, through the clouds on overcast days. Central Europe, places like Germany, Poland, Czech Republic, northern France, is somewhere in the middle of this spectrum. Latitudes around 48 to 52 degrees north. Berlin is 52.5 degrees north. Paris is 48.9 degrees. Warsaw is 52.2 degrees. These are challenging latitudes for vitamin D synthesis, especially in winter, but not quite as severe as Scandinavia. The climate is continental rather than maritime, which means less constant cloud cover than the British Isles. You get more clear, sunny days, especially in the eastern parts of this region. Summer days are long, not midnight sun territory, but 16 to 17 hours of daylight at the solstice, which is substantial. Winter days are short, maybe 8 hours of daylight, but not the extreme 4 to 6 hour days you get in Scandinavia. For dark-skinned migrants in this region, vitamin D synthesis would have been difficult but not impossible during summer months. You'd need significant sun exposure, multiple hours per day with substantial skin exposure, to build up adequate stores, but it could be done, especially during clear weather. The selective pressure for lighter skin was strong, but not quite as extreme as in Scandinavia or Britain. This might explain why Central Europeans have historically been somewhat less uniformly light-skinned than Scandinavians. There was room for a bit more variation because the vitamin D crisis, while real, wasn't quite as acute. Southern Europe, the Mediterranean region, tells a completely different story. Barcelona is at 41.3 degrees north, Rome is 41.9 degrees, Athens is 38 degrees, Lisbon is 38.7 degrees. These are latitudes where vitamin D synthesis is much, much easier. The sun gets significantly higher in the sky, even in winter. Days don't shorten as dramatically. Athens gets about 9.5 hours of daylight at the winter solstice, compared to less than 6 hours in Stockholm. UVB levels remain reasonable year-round, not great in winter, but not the near-zero levels you see in northern Europe. The climate is Mediterranean, warm, relatively dry, plenty of sunny days. Cloud cover is less persistent. A dark-skinned person living in southern Europe 10,000 years ago would have had a much easier time maintaining adequate vitamin D levels. You could probably synthesize enough during spring, summer and fall to build up sufficient stores to last through the relatively mild winter. The selective pressure for lighter skin was much lower. You'd still benefit from somewhat lighter skin compared to equatorial African skin. The UV levels in Rome aren't the same as the UV levels in Nairobi, but the difference wasn't life or death the way it was in Scandinavia. This is why southern Europeans today have noticeably darker skin on average than northern Europeans. Greeks, Italians, Spaniards, Portuguese, they're not as dark as Africans, but they're significantly darker than Scandinavians or British people. And that makes perfect sense given the UV gradients. They lightened enough to optimize vitamin D synthesis at their latitudes, but they didn't need to lighten as much as populations further north. And here's where it gets really interesting from an evolutionary perspective. You can actually trace migration routes and population mixing by looking at skin color gradients across Europe. There's a fairly smooth gradient from darkest in the Mediterranean to lightest in Scandinavia, with intermediate tones in Central Europe. This gradient reflects both the local selective pressures at each latitude and the historical mixing between populations. When genetic studies look at the specific genes that control skin color in Europeans, they find that the frequency of light skin alleles increases as you go north, exactly what you'd predict if skin color was being selected for based on UV levels. It's a beautiful example of natural selection creating predictable patterns across geography. But here's something interesting that's worth understanding. The relationship between latitude and vitamin D synthesis isn't linear. It's not like each degree of latitude north gives you a proportional decrease in vitamin D production. There are threshold effects. Above about 40 degrees north latitude, vitamin D synthesis from sun exposure essentially stops during winter months. Doesn't matter if you're at 45 degrees north or 60 degrees north. From November through February, you're not making vitamin D from sunlight in either location. The angle is too low, the day length is too short, the UVB levels are too minimal. This is sometimes called the vitamin D winter, and it affects a huge swathe of the human population. Everyone living north of roughly the Mediterranean needs to build up vitamin D stores during summer months, and live off those stores during winter. The difference is that light-skinned people can build up adequate stores during summer, while dark-skinned people in the same location might not be able to synthesize enough, even during summer, to last through winter. And here's where the archaeological evidence becomes absolutely fascinating and heartbreaking. We have actual physical evidence of the vitamin D crisis in ancient skeletal remains from northern Europe. When archaeologists excavate burial sites from the Mesolithic and Neolithic periods, roughly 10,000 to 5,000 years ago, they frequently find bones showing unmistakable signs of rickets and osteomalacia. We're not speculating about this. We can see it in the bones themselves, bowed femurs and tibias where the leg bones curved under body weight, deformed ribs with the characteristic rachitic rosary, misshapen pelvises that would have caused obstructed labour, abnormally thin bone cortex indicating inadequate mineralization, dental hyperplasia, defects in tooth enamel that form during childhood illness, cranial deformities, the whole suite of vitamin D deficiency symptoms preserved in skeletal remains thousands of years old. One particularly striking example comes from a Neolithic site in Sweden called Ajvide on the island of Gotland. Archaeologists excavated a burial ground with dozens of individuals dating to about 5,000 years ago. Many of the skeletons, particularly children and young adults, showed severe rickets. We're talking about bones so deformed that these individuals would have had serious mobility problems. They would have walked with a pronounced limp or waddle. They would have been in constant pain. And this wasn't just one or two unlucky individuals, it was a significant portion of the population at this site. This suggests that vitamin D deficiency was endemic in this community, affecting large numbers of people across multiple generations. Similar findings come from Neolithic Britain. At sites like Hambledon Hill and Windmill Hill, archaeologists have found multiple skeletons with rickets, particularly among children. The frequency of rickets in these populations appears to have been much higher than in modern populations, even accounting for the fact that rickets still occurs today in some communities with limited sun exposure and poor nutrition. We're looking at rickets rates that might have been 20%, 30%, possibly even 40% in some communities, compared to less than 1% in most modern developed nations. That's a staggering difference, and it speaks to how severe the vitamin D crisis was for these early northern European populations. And here's something really interesting. When you compare skeletal remains from different time periods and different geographic locations within Europe, you can actually track the evolution of lighter skin through its effect on bone health. Earlier skeletal remains, say, from 15,000 years ago, show higher rates of severe rickets. Later remains, from 5,000 years ago, still show rickets, but the severity is somewhat reduced and the frequency might be lower. Modern European populations have much lower rates of rickets, and when it does occur, it's usually in individuals with darker skin, or in populations with limited sun exposure and poor nutrition. This pattern is consistent with populations gradually evolving lighter skin over thousands of years, which reduced but didn't completely eliminate the vitamin D deficiency problem. Even light-skinned people in northern Europe can develop rickets if they don't get enough sun exposure or dietary vitamin D, but their risk is much lower than it would be for dark-skinned people in the same environment. Archaeologists have also found something else intriguing: changes in burial practices that might reflect the trauma and confusion these populations experienced around childhood death and childbirth complications. In some Neolithic cemeteries, there are clusters of infant and child burials, sometimes with unusual grave goods or positioning that suggests these deaths were seen as particularly tragic or mysterious. There are also burials of young women, sometimes with the remains of an unborn or partially born infant still in the pelvic area, direct physical evidence of death in obstructed labour. These aren't common findings, but they occur frequently enough to suggest that childbirth complications were a recognised and feared aspect of life in these communities. The people burying these women probably didn't understand why childbirth was so dangerous, but they clearly recognised it as a major threat, and they developed cultural practices around it, special burial rites, protective amulets placed with pregnant women, rituals intended to ensure safe delivery, none of which actually helped, because you can't fix a contracted pelvis with rituals, but it shows they were trying to grapple with a problem they could observe but couldn't explain or prevent. And here's the kicker. Humans can store vitamin D in fatty tissues and liver, but that storage is limited. You can't just gorge on vitamin D during summer and expect it to last indefinitely. Vitamin D has a half-life in your body of about 15 days. So if you stop synthesizing vitamin D at the start of winter, within a few months, your stores are significantly depleted. By late winter, March in the Northern Hemisphere, people who didn't build up adequate stores during summer are running on empty. That's when you'd see the worst ricket symptoms manifesting, the worst bone pain, the worst complications. Late winter and early spring would have been the deadliest times for vitamin D deficiency in these ancient populations. Just when you need to be strong and healthy to start the new agricultural season or resume hunting, you're at your weakest. There's also an age gradient in vulnerability. Infants and young children are most at risk because they're growing so rapidly. Their bones are mineralizing and lengthening at a fast pace, which requires lots of vitamin D and calcium. Adolescents going through growth spurts are also vulnerable. Pregnant and nursing women are at increased risk because the developing fetus and nursing infant are pulling calcium and vitamin D from the mother's body. Elderly people have reduced capacity to synthesize vitamin D from sun exposure, so they're vulnerable too. Really, the only people who are relatively safe from severe deficiency are healthy adults in their prime who aren't pregnant or nursing. And even they would have experienced symptoms, bone pain, muscle weakness, fatigue, if their vitamin D levels drop too low. Let me paint you a picture of what a settlement of dark-skinned migrants in Northern Europe might have looked like after a few generations at these latitudes, because understanding the human reality makes this more than just an abstract evolutionary story. You've got a community of maybe 100 to 200 people living in a cluster of wooden longhouses or hide tents somewhere in what's now northern Germany or southern Scandinavia. The time period is around 12,000 to 15,000 years ago, late Ice Age or early post-glacial period. The environment is harsh, dense forests, cold winters, short growing seasons if they're practicing any agriculture at all, which is questionable this early. Most likely they're still hunter-gatherers, following seasonal migration patterns of game animals, supplementing with gathered plants, nuts, fish when available. It's late winter, February or early March. This is when things are worst. Food stores from the previous autumn's harvest or hunting are running low. People are tired, hungry, cold. They've been living in close quarters through the long, dark winter months, which creates its own tensions, interpersonal conflicts, cabin fever, the psychological strain of darkness and confinement. But there's something else, something that would have been deeply concerning and utterly mystifying to these people. Many of the children, maybe 30 or 40 out of 80 total kids in the community, are showing obvious signs of illness. They've got bowed legs, visible even through their clothing. They move with difficulty, often crying out in pain when they have to walk any distance. Several of them have deformed chests, with those distinctive rib bumps creating an unsettling appearance. Their teeth are coming in late, and when they do come in, they're weak and discoloured. The parents can see their children suffering, and they have no idea what's wrong. This isn't like a fever or a cough that comes on suddenly and either kills you or goes away. This is a slow, progressive deformation that worsens over months and years. You watch your 2-year-old take their first steps, and everything seems fine. Then by age 3, you notice their legs look a bit odd. By age 4, the bowing is pronounced, and they're walking with a waddle. By age 5, they're in constant pain, significantly shorter than they should be, and showing multiple skeletal deformities. And it's not just your child, it's happening to many children in the community. Some families seem spared, or their children only have mild symptoms. Others are devastated, with multiple children severely affected. There's no obvious pattern, no clear reason why some kids are healthy and others aren't. The community's healer, probably an older person with knowledge of medicinal plants and ritual practices, has tried everything. Herbal poultices applied to the affected bones, special foods, ritual dances to appease the spirits. Sacrifices of precious resources, a hunted deer, stored grain, offered to whatever gods or forces might be causing this affliction. Nothing works. The children keep getting worse, and then there are the women. Over the past decade, 3 women in the community have died in childbirth. Not from bleeding or infection, which people at least understood as risks of childbirth, but from something else. Prolonged labour where the baby simply wouldn't come, no matter how hard the woman pushed, no matter what interventions the midwives tried. Hours stretched into days. The woman's screams echoed through the settlement. Eventually silence, both mother and baby dead. 3 times in 10 years, which in a community of this size represents a catastrophic maternal mortality rate. The community is traumatized. The elders are talking about curses. Maybe they settled in a bad location. Maybe they offended some local spirits. Maybe there's something wrong with the water source. Various theories get floated, none of them correct, because how could they be correct? These people don't have the conceptual framework to understand UV radiation, vitamin D, calcium metabolism, bone mineralization. They're operating with a pre-scientific understanding of the world where illness is caused by supernatural forces, spiritual imbalances, or miasmas and evil airs. They can observe the symptoms, the bowed legs, the difficult births, but they can't diagnose the underlying cause. It's like trying to fix a car engine when you don't know what an engine is. You can see that the car doesn't work, but you have no idea how to fix it. There's probably a lot of blame being thrown around. Women who give birth to children with rickets might be accused of doing something wrong during pregnancy. Did they break some taboo, eat the wrong food, anger some spirit? The mother becomes a target for suspicion and social ostracism, which is grotesquely unfair but psychologically understandable. People want to find a cause, an explanation, someone or something to blame, because randomness and meaningless suffering are psychologically intolerable. Better to believe that someone did something wrong and that's why bad things happened, because then you can avoid those same mistakes and protect yourself and your children. Except in this case, there was no mistake to avoid. The problem was literally in their skin, and there was nothing they could do about it through behavior or ritual. Some families might make the connection that their children seem healthier in summer and worse in winter. But what could they do with that observation? They can't make winter go away. They can't make the sun shine more. They're stuck with the seasonal cycle, and their bodies aren't adapted to it. Maybe they try spending more time outside during summer, even though that conflicts with the need to be working, hunting, gathering, tending crops if they're early agriculturalists. Maybe they experiment with different foods, trying to find something that helps, occasionally stumbling on things like fish liver or bone marrow that actually do contain vitamin D and might provide some small benefit, but not understanding why those foods help or being able to access them consistently enough to make a real difference. And all of this is happening against a backdrop of generally difficult living conditions. These aren't people living comfortable modern lives who happen to have a vitamin D problem. They're dealing with cold, hunger, predators, intertribal conflicts, injuries, infections, high infant mortality from multiple causes, short lifespans. The vitamin D crisis is piled on top of all the other challenges of existence at this time and place. It's not like they can focus all their attention on solving the bone problem. They're just trying to survive day to day. The vitamin D deficiency is one more thing going wrong, one more burden to bear, one more source of grief and confusion in lives that were already hard enough. Now multiply this scenario across dozens or hundreds of small communities scattered across northern Europe over thousands of years. Thousands of children with rickets, thousands of women dying in obstructed labour, thousands of families grieving and confused and trying desperately to fix a problem they couldn't understand. The human cost of this evolutionary transition was enormous. We talk about natural selection in abstract terms, selective pressure, fitness differentials, gene frequency changes, but behind those abstractions are real people suffering and dying. Evolution isn't gentle, it's not kind. It doesn't care about individual suffering, it just grinds forward, generation after generation, filtering genes through the brutal sieve of survival and reproduction. Some families are doing better than others, though, and nobody quite understands why. Maybe one family has several children who are healthy and growing normally, while their neighbours' children are all severely affected by rickets. What's the difference? Well, possibly, one of those healthy children was born with a random mutation that reduced melanin production. Lighter skin, more UVB penetration, better vitamin D synthesis. That child is healthier, grows taller, doesn't develop bone deformities. If that child is a girl, she'll have a normally shaped pelvis and will be able to successfully give birth to her own children. If it's a boy, he'll be stronger and more physically capable, potentially more successful at hunting or defending the community. Either way, that genetic mutation, lighter skin, provides a survival advantage in this specific environment. That child is more likely to survive to adulthood, more likely to reproduce successfully, more likely to have many offspring who inherit the lighter skin genes. And here's the beautiful, terrible elegance of natural selection. This process doesn't require anyone to understand what's happening. It doesn't require conscious decision-making. It happens automatically, generation after generation. The genes that produce better outcomes in this environment, lighter skin in this case, become more common. The genes that produce worse outcomes, dark skin, at these latitudes, become less common. It's not fair. It's not justice. It's just math and biology grinding away, filtering the gene pool through the harsh sieve of survival and reproduction. The speed at which this happened varied by location. In the far north, where the selective pressure was most intense, the shift from dark to light skin probably happened relatively quickly, maybe 5,000 to 10,000 years. In southern Europe, where dark skin wasn't as much of a disadvantage, the shift was slower and less complete, which is why southern Europeans still have noticeably darker skin than northern Europeans today. In some populations that maintained access to dietary vitamin D sources, particularly coastal populations with access to fatty fish, the selective pressure for lighter skin was reduced, and those populations didn't lighten as much as inland. Populations. But make no mistake, what we're talking about here is one of the most intense episodes of natural selection in recent human history. The selective pressure to develop lighter skin in northern latitudes was enormous. It rivaled or exceeded the selective pressure that produced other famous examples of rapid human evolution, like lactose tolerance or high-altitude adaptations in Tibetans. Women with dark skin in northern Europe had measurably lower reproductive success than women with lighter skin. That's not a moral judgment. It's a statistical observation about who survived and reproduced. And over thousands of years, that statistical edge compounds. Lighter skin genes spread through the population. Dark skin genes diminish and eventually disappear or become rare. The population's appearance changes. And by the time you reach the historical period, when we have written records and artistic depictions of people, populations in northern Europe are light-skinned because the dark-skinned individuals have been filtered out by millennia of natural selection. This is why skin colour correlates so strongly with latitude. It's not random, it's not cultural, it's not socially constructed. It's a direct biological response to UV radiation levels, which are determined by latitude, cloud cover, and seasonal variation. Dark skin near the equator protects against high UV, maintains folate, allows enough UV through for vitamin D. Light skin at high latitudes allows maximal UV penetration for vitamin D synthesis, while accepting the trade-off of less folate protection, which isn't a big deal at high latitudes because UV levels are lower anyway. Intermediate skin tones at intermediate latitudes, a compromise between the two selective pressures. It's elegant, it's logical, and it's completely impersonal. Evolution doesn't care about your feelings or your politics. It just cares about survival and reproduction. Skin colour is simply a solution to a problem. How much UV should your skin allow through? And the answer depends entirely on where you live. Now, as we wrap up this chapter of the story, I want you to sit with the sheer tragedy of what happened to these populations. They left Africa seeking new opportunities, new lands, better conditions. They were brave, curious, adventurous. They walked into the unknown, and they paid a terrible price for it. Generations of suffering, children with deformed bones, women dying in childbirth, communities struggling to survive. All because their skin was the wrong colour for their new environment. All because they hadn't yet evolved the biological adaptations necessary to thrive at these latitudes. It took thousands of years and countless lives before evolution could fix the problem through the spread of light skin mutations. These weren't just abstract genetic changes we're discussing. These were real people dying, real families grieving, real communities struggling to understand why life had become so hard. But evolution did eventually fix it. The mutations happened. The lighter-skinned individuals survived and reproduced more successfully. The genes spread. The population adapted. And by the time we reach the modern era, populations at different latitudes have skin colours that match their UV environments. The crisis passed. The adaptation succeeded, but the cost was high and it took a long time to pay. In the next part of this story, we'll dive into the specific molecular mechanisms of how this transformation happened, the exact genes that mutated, the biochemical pathways involved, and the remarkable fact that different populations evolved light, skin through completely different genetic routes. But for now, we're leaving our ancestors in the depths of the vitamin D crisis, struggling to survive in lands where their perfect African adaptation had become a deadly liability. So we've established the problem. Dark-skinned humans in northern latitudes are experiencing a vitamin D crisis that's killing children and women at alarming rates. Natural selection is bearing down on these populations with tremendous force. Now let's talk about the solution, and by solution, I mean the series of random genetic accidents that happen to fix the problem entirely by chance. Because that's how evolution works. It's not intelligent design. It's not purposeful. It's just blind luck filtered through the merciless sieve of survival. Some mutations help, most mutations do nothing or actively harm, and the helpful ones spread while the harmful ones disappear along with the people who carried them. Let's zoom way in here, down to the molecular level, because understanding what actually happened requires understanding what genes are and how they work. Your genome, your complete set of genetic instructions, consists of about 3.2 billion base pairs of DNA. Think of DNA as a four-letter alphabet, A, T, G, and C, standing for adenine, thymine, guanine, and cytosine. These are the chemical building blocks, the nucleotides, that make up your genetic code. 3 billion letters arranged in a specific sequence, and that sequence contains all the instructions for building and operating a human body. It's like the most complicated instruction manual ever written, except it wasn't written. It evolved through 4 billion years of trial and error. Within that massive genome, there are roughly 20,000 to 25,000 genes, specific stretches of DNA that code for proteins. Proteins do essentially all the work in your body: enzymes that catalyze chemical reactions, structural proteins that build tissues, transport proteins that move molecules around, signaling proteins that coordinate cellular activities, and so on. Each gene is basically a recipe for making a specific protein. The DNA sequence of the gene determines the amino acid sequence of the protein, which determines the protein's three-dimensional shape, which determines what that protein does in your body. Change the DNA sequence, and you change the protein. Change the protein, and you change what happens in your cells. Change what happens in your cells, and you change what the organism looks like and how it functions. Now, skin color is controlled by several genes, but a few big players do most of the work. The most important one for our story is called SLC24A5. Catchy name, right? It stands for Solute Carrier Family 24 Member of 5, which is exactly the kind of creative naming convention you'd expect from scientists who spend their days sequencing genomes. This gene codes for a protein that sits in the membrane of melanosomes, those little packages where melanin is produced inside melanocytes. The protein's job is to transport calcium ions across the melanosome membrane, and that calcium transport is somehow involved in melanin synthesis. Reduce the activity of this protein, and you reduce melanin production. Reduce melanin production, and you get lighter skin. Simple, right? Except the detailed biochemistry of how calcium transport regulates melanin synthesis is actually incredibly complicated and not fully understood even today. But we don't need to understand the mechanism completely to observe the effect. Mess with SLC24A5 and you mess with skin color. The specific mutation that causes light skin in Europeans is a single nucleotide change in the SLC24A5 gene. One letter out of the roughly 13,000 letters that make up this gene, position 111 in the protein sequence, there's normally a glycine amino acid. But if you change a single G to an A in the DNA code, just that one letter swap, you get an alanine instead of glycine at that position. This is called the A111T polymorphism, and it's present in roughly 99% of Europeans, almost 100% of people of European descent. It's nearly fixed in the population, meaning it's basically universal. If you're of European ancestry, you almost certainly have this mutation. Both copies, in fact, one from each parent, because it's so common that both your parents probably had it, and their parents, going back dozens of generations. This tiny change, glycine to alanine, a single amino acid swap in a protein that's 422 amino acids long, significantly reduces the protein's ability to transport calcium. The melanosomes don't work as efficiently. Melanin production drops by maybe 30 to 40%. Your skin lightens from dark brown to a much lighter shade, anywhere from olive to pale depending on what other genes you have. That's it. That's the molecular basis of light skin in Europeans. One letter change out of 3 billion. Let me put that in perspective because the scale is genuinely staggering. Imagine you've got the complete works of Shakespeare, all 37 plays, all the sonnets, all the poems, everything he ever wrote. That's roughly 1 million words, or about 5 million characters including spaces. Now imagine you have 600 complete copies of Shakespeare's entire works all laid out in sequence. That's approximately 3 billion characters, roughly equivalent to the size of the human genome. Now imagine you change one single letter in one single word in one single play, somewhere in that massive collection. Maybe you change the T in two to a D so it reads do instead. Just that one letter, and that one letter change is sufficient to dramatically alter the appearance of every human being who inherits that modified version. That's what we're talking about here. The precision is staggering. The economy is remarkable. Evolution isn't crudely hammering away at the human form with a sledgehammer, painting in broad strokes. It's making microscopic edits with a molecular scalpel, single letter changes in genetic code, and some of those edits have enormous visible consequences while most do nothing at all. Let's talk about another gene, SLC45A2, which codes for another membrane transport protein involved in melanosome function. This one is sometimes called MATP, membrane-associated transporter protein, because scientists apparently ran out of creative naming schemes and just started describing what the protein does. This protein sits in melanosome membranes and helps regulate the internal environment where melanin synthesis occurs. There are several variants of this gene that affect skin colour, but one particular mutation that's common in Europeans, again, a single nucleotide change, because evolution apparently likes to make point mutations when it's editing for skin. Colour lightens skin significantly. It's not quite as dramatic as the SLC2405 mutation, but it contributes meaningfully to the light European phenotype. Here's what's interesting about having multiple genes involved. They can interact in complex ways. If you have one light skin variant in SLC2405 but dark skin variants everywhere else, you'll be somewhat lighter than if you had dark skin variants in all genes, but you won't be as light as someone who has light skin variants in both SLC2405 and SLC45A2. The effects are roughly additive, though not perfectly so because biology is messy and genes interact in complicated ways that we're still figuring out. This is why you see a continuous distribution of skin tones within populations rather than discrete categories. It's not like you're either light or dark with nothing in between. You can have two light skin genes and be quite pale, or one light skin gene and one dark skin gene and be medium toned, or various combinations that produce the full spectrum of human skin colour, from very dark to very light, with every possible shade in between. And this is where we need to pause and emphasise something important. Race, as conventionally understood, doesn't map cleanly onto genetic reality. When you actually look at the genetic architecture of skin colour, what you find is a small number of genes with various alleles, different versions, and those alleles are distributed across populations in frequencies that correlate with latitude and UV. Exposure, not with socially constructed racial categories. Someone from southern India might have darker skin than someone from North Africa, but that doesn't mean they're genetically more African or less Asian or whatever category you want to impose. They just happen to have inherited more of the dark skin alleles, probably because their ancestors lived in a high UV environment where those alleles were beneficial. Genetics doesn't care about your taxonomy, it just cares about local adaptation. Between SLC2405 and SLC45A2, you've got the major genetic determinants of light skin in European populations. There are other genes involved too, TEOR, which codes for tyrosinase, the enzyme that actually catalyzes melanin synthesis, TRP1, which codes for a related enzyme, OCA2, which is involved in melanin production and also affects eye colour, and a handful of others. But SLC2405 and SLC45A2 are the heavy hitters. They account for most of the difference between dark African skin and light European skin. Now here's the crucial question. When did these mutations happen? When did light skin first appear in European populations? And the answer, which we know from multiple lines of genetic evidence looking at the distribution and variation of these alleles across populations, is surprisingly recent. Recent enough that it completely upends some common assumptions about human prehistory. The SLC2405 mutation appears to have originated and spread within the last 20,000 to 30,000 years. Some estimates put it even more recently, maybe 10,000 to 15,000 years ago, though the exact timing is debated because dating these things precisely is difficult, and different analytical methods sometimes give slightly different dates. But what's absolutely clear, beyond any reasonable doubt, is that this mutation is young. really, really young in evolutionary terms. Modern humans, anatomically modern Homo sapiens, have been around for about 300,000 years. The SLC2405 mutation has been around for maybe 30,000 years at most, possibly as little as 10,000 years. Let's do that math. That means anatomically, modern humans existed for somewhere between 270,000 and 290,000 years without this mutation. For 90% or more of the time that humans have existed as a species, light skin didn't exist. Everyone was dark-skinned. Every human ancestor you can trace back beyond about 30,000 years ago, which is maybe 900 to 1,200 generations, had dark skin. Light skin is a brand new feature, an extremely recent evolutionary innovation that appeared only after humans had spread out of Africa and been living in northern latitudes for thousands of years. And we can actually see this in the archaeological record through ancient DNA analysis, which is some of the most fascinating genetic detective work being done right now. Scientists can extract DNA from ancient bones. If the bones are well preserved and stored in the right conditions, DNA can survive for tens of thousands of years, though it's usually degraded and fragmented, and they can sequence that DNA and look at specific genes, including the ones that control skin color. This lets them directly determine what color skin ancient people had, rather than just guessing based on artistic representations or skeletal features, neither of which are reliable indicators of skin tone, and what they've found is remarkable. People who lived in Europe 40,000 years ago, early modern humans who had recently migrated from Africa or the Middle East, almost certainly had dark skin based on the genetic variants they carried. People who lived in Europe 20,000 years ago still had mostly dark skin, though some light skin variants were starting to appear at low frequencies. People who lived in Europe 10,000 years ago had a mix. Some still had quite dark skin, some had intermediate tones, and some had lighter skin, suggesting the transition was actively underway but not complete. And people who lived in Europe 5,000 years ago looked much more like modern Europeans, with light skin being dominant or nearly universal in northern populations. You can literally trace the evolution of light skin through ancient DNA samples arranged chronologically. Early samples, dark skin genes; middle samples, mix of dark and light skin genes; late samples, mostly light skin genes. Modern samples, almost entirely light skin genes in northern European populations. It's a beautiful illustration of evolution in progress, captured in ancient bones dug up from archaeological sites across Europe. We're not speculating about this. We're not inferring it indirectly. We're directly reading the genetic code from people who lived thousands of years ago and determining what they looked like. This is the kind of evidence that makes evolutionary biology such a powerful science. You can make predictions about what you should find, and then you go find it, and it matches your predictions. Theory and evidence aligning perfectly. And here's what's really fascinating. We can actually track how fast this mutation spread through European populations by looking at the genetic diversity around the SLC2405 gene region. When a beneficial mutation appears and spreads rapidly through a population, what geneticists call a selective sweep, it carries along with it nearby genetic variants that happen to be sitting close to it on the same chromosome. Those variants hitchhike along with the beneficial mutation. By looking at the pattern of genetic variation around SLC2405, geneticists can estimate how long ago the mutation appeared and how strongly it was selected for. And what they find is evidence of one of the strongest selective sweeps in the human genome. This mutation spread like wildfire through European populations. It went from near zero to nearly 100% frequency in, at most, a few thousand years, possibly faster. Why so fast? Because the selective pressure was enormous. Remember those women dying in childbirth? Those children with rickets? That's not subtle selective pressure, that's survival or death pressure. If you have the dark-skinned version of SLC2405 in Northern Europe 15,000 years ago, your children have a significantly higher risk of rickets, and your daughters have a significantly higher risk of dying in childbirth. If you have the light-skinned version, those risks drop dramatically. The difference in reproductive success, the number of children who survive to adulthood and have their own children, is substantial. Even a relatively small difference in reproductive success, compounded over dozens of generations, creates massive changes in gene frequencies. A mutation that increases your lifetime reproductive success by even 1 to 2% will eventually become fixed in a population. The light skin mutations probably increased reproductive success by much more than that in northern latitudes, maybe 5%, 10%, possibly even higher in the most extreme environments. That kind of selective advantage creates incredibly rapid evolutionary change. Let's do some back-of-the-envelope math to illustrate this, because numbers can help make the abstract concrete. Imagine a population of 1,000 people living in northern Europe 20,000 years ago. One day, or more accurately one generation, a baby is born with a new mutation in the SLC24A5 gene. That baby has one copy of the light skin allele and one copy of the dark skin allele, making them heterozygous for this trait. Their skin is somewhat lighter than their fully dark-skinned parents, though not as light as someone with two copies of the light skin allele would be. That's a starting frequency of 0.05% if we're counting alleles, one light skin allele out of 2,000 total alleles in the population, since each person has two copies of every gene. Now imagine that this mutation provides a 5% reproductive advantage. What does that mean in practical terms? It means that people carrying this mutation have, on average, 5% more children who survive to adulthood and have their own children compared to people without the mutation. Maybe dark-skinned parents have an average of 4 surviving children per family, while light-skinned parents have an average of 4.2 surviving children. That doesn't sound like much, an extra 0.2 children per family, but remember, we're talking about compounding effects over multiple generations. Small advantages, given enough time, produce enormous changes. Let's trace what happens to that mutation over time. After 20 generations, maybe 500 to 600 years at roughly 25 to 30 years per generation, that mutation has gone from 0.05% frequency to about 1.3% frequency. Still quite rare, but it's growing. After 50 generations, maybe 1,250 years, it's up to about 7% frequency. Now 1 in 14 people carry at least one copy of the light skin allele. After 100 generations, 2,500 years, it's around 39% frequency. Now nearly 4 out of 10 alleles in the population are the light skin version. The transition is accelerating because as the allele becomes more common, it's present in more people, and each of those people is passing it on to their children. After 150 generations, 3,750 years, it's reached 83% frequency. Most people now have at least one copy of the light skin allele, and many have 2 copies. After 200 generations, 5,000 years, it's above 99%, essentially fixed in the population. Almost everyone has 2 copies of the light skin allele. The dark skin allele hasn't disappeared entirely. It might persist at very low frequencies, maybe 1 in 1,000 people still carrying it, but it's become rare while the light skin allele has become ubiquitous. Those are rough numbers based on simplified population genetics models, and the real dynamics are more complicated because population size varies, migration occurs, genetic drift plays a role, and selection coefficients aren't constant across time and space. But the fundamental point holds. Strong selective pressure can drive a beneficial mutation from near zero to near fixation in remarkably few generations. 5,000 years seems like a long time to us. It spans all of recorded human history from the first writing systems to now, but in evolutionary terms it's incredibly fast. It's 1.7% of the time that modern humans have existed as a species. It's a tiny fraction of the time evolution typically takes to produce major changes in organisms, and yet it was enough time for light skin to go from non-existent to nearly universal in northern European populations. And we know this happened because we can actually measure the strength of selection using genetic techniques. When a beneficial mutation spreads rapidly through a population, what geneticists call a selective sweep, it leaves distinctive signatures in the genome that can be detected thousands of years later. The mutation itself reaches high frequency, obviously, but it also drags along with it genetic variants that happen to be sitting nearby on the same chromosome. These nearby variants hitchhike, along with the beneficial mutation, reaching higher frequencies than they would have on their own. This creates a pattern where you see reduced genetic diversity around the selected site. All the genetic variants that weren't linked to the beneficial mutation got left behind and dropped to low frequency, while the variants that were linked got carried along. By looking at the pattern of genetic variation around the SLC24A5 gene in modern European populations, geneticists can work backwards and estimate how recently the selective sweep occurred and how strong the selection was. And what they find is evidence of one of the strongest selective sweeps in the entire human genome. The region around SLC2405 shows dramatically reduced genetic diversity compared to other parts of the genome, consistent with a very recent, very intense selective sweep. The estimated selection coefficient, the reproductive advantage provided by the mutation, is somewhere between 5% and 10%, possibly even higher. That's enormous in evolutionary terms. For comparison, most beneficial mutations that spread through populations have selection coefficients of maybe 1 to 2%. A 5 to 10% advantage is the kind of selection pressure that can drive evolutionary change at breakneck speed. And here's something fascinating. The selective sweep appears to have happened more recently in Northern Europe than in Southern Europe, which makes perfect sense. The closer you get to the Arctic Circle, the stronger the vitamin D crisis, the stronger the selective pressure for light skin, the faster the light skin alleles spread. In Scandinavia, the sweep was probably more recent and more intense than in, say, Greece or southern Italy, where the vitamin D problem was less severe and the selective pressure was weaker. You can actually see this in the geographic distribution of the SLC2405 light skin allele. It reaches highest frequencies in Northern Europe and lower, though still high, frequencies in Southern Europe, with a smooth gradient in between. This gradient reflects the strength of selection at different latitudes, stronger in the north where UV was scarce, weaker in the south where UV was more abundant. And this actually happened. Multiple times, independently, in different populations. Because here's where the story gets truly mind-blowing. Light skin evolved separately in different parts of the world through completely different genetic mutations. Europeans developed light skin through mutations in SLC, 24A5 and SLC45A2. East Asians developed light skin through an almost entirely different set of mutations. This is convergent evolution, the same solution arising independently in different populations because the same environmental pressure is selecting for the same outcome. Let's talk about East Asia, because this is where the convergent evolution story gets truly spectacular. Populations in northern China, Korea and Japan live at latitudes that are somewhat comparable to southern and central Europe. Beijing is at 40 degrees north, roughly the same as Madrid or Philadelphia. Seoul is at 37.5 degrees north, similar to Athens or San Francisco. Tokyo is at 35.7 degrees, comparable to Los Angeles or Tunisia. Some northern Asian populations living in Siberia and Mongolia are at much higher latitudes, 50 to 60 degrees north, comparable to northern Europe. These populations all face similar vitamin D challenges to Europeans: seasonal UV variation with long winter months of limited vitamin D synthesis, short cold days, the need to optimize UVB penetration to maintain adequate vitamin D production, without developing rickets or osteomalacia. The selective pressure is fundamentally the same. Get more UVB through your skin or face, serious health consequences. And just like Europeans, these populations evolved lighter skin. This isn't subtle. If you look at someone of northern East Asian descent, Chinese, Korean, Japanese, and compare them to someone of sub-Saharan African descent, the difference in skin tone is obvious and substantial. East Asians have significantly lighter skin than equatorial Africans. If you compare them to northern Europeans, the skin tones are roughly similar, maybe slightly different in undertone. Europeans often have pink or ruddy undertones, while East Asians often have more yellow or olive undertones, but the overall lightness is comparable. Both populations have clearly moved away from the ancestral dark African skin tone toward much lighter pigmentation. But here's where it gets absolutely mind-blowing. When geneticists sequence the genes controlling skin colour in East Asian populations and compare them to European populations, the genetic architecture is almost completely different. The SLC2405 mutation that's nearly universal in Europeans, present in 99% of people of European descent, essentially fixed in the population, one of the strongest selective sweeps in the human genome, is basically absent in East Asians. They don't have it. They're still carrying the ancestral African version of SLC2405, the same version that produces dark skin. Their SLC2405 gene looks like an African SLC2405 gene, not like a European SLC2405 gene. So if they don't have the major European light skin mutation, how did they end up with light skin? Through completely different mutations in completely different genes. Let me walk you through this because it's genuinely one of the most elegant demonstrations of convergent evolution in action. One important gene in East Asians is OCA2, which codes for a protein involved in melanosome maturation and melanin production. You might recognize this gene from eye color studies. It's the gene that's largely responsible for blue eyes in Europeans through a mutation that reduces brown pigment in the iris. But East Asians have different variants of OCA2 that affect skin color without producing blue eyes. These variants reduce melanin production in skin melanocytes, leading to lighter skin, but they don't have the same effect on eye pigmentation that the European blue eye variants do. Same gene, different mutations, different effects on different tissues. Another important gene is EDAR, ectodysplazin A receptor, which is involved in the development of skin, hair, teeth, and glands during embryonic development. There's a particular variant of EDAR called 370A that's extremely common in East Asian populations, found in 90% or more of East Asians, but very rare in Europeans and Africans. This variant has multiple effects. It produces thicker hair shafts, giving East Asians their characteristically thick, straight hair. It produces shovel-shaped incisors, a distinctive tooth shape where the back of the front teeth is scooped out rather than flat. It increases the density of eccrine sweat glands in the skin. And it also lightens skin colour, probably by affecting melanocyte development or function during skin formation. So East Asians have this EDAR variant that Europeans don't have, and it contributes to their lighter skin through a completely different mechanism than European light skin genes. There are other genes too. East Asians have specific variants in genes like DCT, dopachrome tautomerase, which is involved in melanin synthesis pathways. They have variants in KITLG, KIT ligand, which regulates melanocyte development and migration. They have their own unique variants in TYR and TYRP1, the genes coding for tyrosinase and tyrosinase-related proteins that directly catalyze melanin production. When you add up all these different genetic variants, OCA2, EDAR, DCT, KITLG, TIR, TRP1, and probably a few others we haven't identified yet, you get the genetic architecture underlying light skin in East Asians. And it's a completely different genetic architecture than in Europeans. It's like two separate construction crews building similar houses using completely different materials and techniques. The European crew is using SLC2405 and SLC45A2 as their primary building materials. The East Asian crew is using OCA2 and EDAR and KITLG as their primary materials. Both crews end up with houses, or in this case light skin, that look roughly similar from the outside and serve the same functional purpose of allowing more UVB penetration for vitamin D synthesis. But if you tear down the walls and look at how they're constructed, the underlying structure is completely different. Different genes, different proteins, different cellular mechanisms, all producing a similar macroscopic outcome. This is what convergent evolution looks like at the molecular level. Two populations separated by thousands of miles, living at similar latitudes, facing similar environmental pressures, evolving similar solutions to the same problem, but arriving at those solutions through different genetic pathways. They started from a common ancestor, dark-skinned Africans, who migrated out of Africa tens of thousands of years ago. The population split, with some groups moving west into Europe and others moving east into Asia. Each population accumulated random mutations over thousands of generations. In Europe, mutations in cell C2405 and cell C45A2 happen to provide vitamin D benefits and spread rapidly. In East Asia, mutations in OCA2 and EDAR happen to provide vitamin D benefits and spread rapidly. Different mutations, same selective pressure, similar outcome. And this tells us something profound about the nature of skin color as an evolutionary trait. It's highly evolvable. There are multiple genetic pathways that can lead to lighter skin. Evolution found several different solutions to the same problem, which suggests that the problem, insufficient UVB penetration in low UV environments, is a strong enough selective pressure that evolution will find whatever genetic solution happens to be available in a given population. Europeans got light skin one way, East Asians got light skin a different way. If there were other human populations living at high northern latitudes that we haven't studied, they'd probably have their own unique set of light skin genes different from both Europeans and East Asians. And we actually have an example of this with South Asians. Populations in northern India, Pakistan, and neighbouring regions also have lighter skin than equatorial Africans, though not as light as northern Europeans or East Asians. When you look at their genetic architecture, it's a mix. Some individuals carry the European SLC24A5 light skin allele, probably inherited from ancient population mixing when groups from the West migrated into South Asia. But they also carry their own unique variants in other genes that contribute to skin colour. It's like they borrowed some genetic solutions from Europeans but also developed some of their own. This makes sense given the complex migration and mixing history of South Asia, which has been a crossroads of human populations for tens of thousands of years. This is absolutely remarkable. Two populations, facing similar environmental challenges, evolved similar solutions but through different genetic pathways. It's like two engineers independently designing bridges to span the same river, and they both create suspension bridges, but one uses steel cables and the other uses composite materials, and they arrive at similar final designs through completely different engineering approaches. The outcome looks similar: a bridge that spans the river, or light skin that allows more UVB penetration. But the underlying mechanism is different. What this tells us is profound. Light skin is not an ancestral trait inherited from a common light-skinned ancestor. It's not like modern Europeans and East Asians both descended from a single population of light-skinned people who lived thousands of years ago. They both descended from dark-skinned Africans, and they both independently evolved lighter skin after migrating to northern latitudes. The common ancestor of Europeans and East Asians, whoever that was, living somewhere in Africa or the Middle East tens of thousands of years ago, almost certainly had dark skin. Light skin evolved separately after the population split and migrated to different regions. This is powerful evidence that skin colour is purely an environmental adaptation, not some inherent characteristic that defines distinct populations. If Europeans and East Asians can independently evolve similar skin tones through different mutations in different genes, that tells you that skin colour is a highly flexible trait that responds to local UV conditions through natural selection. And here's the thing: this pattern, convergent evolution of the same trait through different genetic mechanisms, shows up all over biology. It's not unique to human skin colour. Cavefish in different cave systems have independently evolved blindness and loss of pigmentation through mutations in different genes. Multiple groups of mammals have independently evolved echolocation, bats, whales, some shrews, through different modifications of their auditory systems. Flying has evolved independently in insects, pterosaurs, birds and bats through completely different anatomical structures. Convergent evolution is everywhere because similar environmental pressures select for similar solutions, but there are often multiple genetic paths to reach those solutions. Evolution is tinkering with whatever genetic variation is available in a population, and different populations have different mutations available to work with, so they end up taking different routes to the same destination. This also means that the genetic differences between populations in skin colour are remarkably shallow. We're not talking about massive rewiring of the genome, we're talking about a handful of genes with slightly different variants. Literally 10 to 15 genes account for most of the visible variation in skin colour across all human populations. That's it, out of 20,000 genes total. You share about 99.9% of your genome with every other human on the planet, regardless of what you look like. The differences that we fixate on, skin colour, eye colour, hair texture, facial features, come down to tiny variations in a tiny number of genes. Everything else, all the genes that build your brain, your liver, your kidneys, your muscles, your immune system, your nervous system, all the fundamental biological machinery that makes you human, is essentially identical across all populations. And yet these tiny genetic differences have had enormous historical consequences, because humans are incredibly visual creatures who make snap judgments based on appearance. The SLC24A5 mutation, one letter change out of 3 billion, has been used to justify slavery, colonialism, segregation, discrimination, and genocide. A molecular triviality has been blown up into a social catastrophe. That's not biology's fault. That's humans layering cultural meaning onto biological variation that, from an evolutionary perspective, is completely superficial. But let's get back to the molecular story because there's more to tell. We've talked about the mutations that lighten skin, but we should also talk about the mutations that don't. Because for every beneficial mutation that spreads through a population, There are thousands of other mutations that appear and disappear without consequence, or cause harm and get filtered out. DNA mutates constantly. Every time a cell divides and copies its DNA, there's a small chance of making a copying error. Most mutations occur in non-coding DNA, the parts of the genome that don't code for proteins, and have zero effect on the organism. Some mutations occur in coding DNA but don't change the protein because the genetic code is redundant. Multiple DNA sequences can code for the same amino acid. Some mutations do change the protein, but in ways that don't significantly affect its function. And some mutations, a small minority, actually break something important, causing disease or reducing fitness. The vast majority of mutations are either neutral or harmful. Beneficial mutations are rare, but when they do occur, and when the environment is exerting strong selective pressure, those beneficial mutations can spread with stunning speed. The light skin mutations are examples of beneficial mutations in the right place at the right time, but there were probably many other mutations affecting melanin production that appeared and disappeared without spreading. Maybe they didn't lighten skin enough to provide a vitamin D advantage. Maybe they lightened skin too much, removing so much melanin that folate protection became an issue even at northern latitudes. Maybe they caused other problems. Melanin isn't just for skin color, it's also in your eyes and inner ear and brain, so mutations that affect melanin production can sometimes cause vision problems, hearing problems, or neurological issues. The mutations that spread were the ones that hit the sweet spot. Lighten the skin enough to improve vitamin D synthesis, but not so much that you create new problems. And here's something worth understanding. These mutations aren't unique to the populations where they spread. The SLC24A5 light skin mutation that's nearly universal in Europeans. It almost certainly appeared multiple times in human history, probably in various African populations, but it didn't spread in those populations because it provided no advantage. In equatorial Africa, lighter skin is a disadvantage, not an advantage. Anyone born with that mutation would have had increased risk of skin cancer, increased folate depletion, no reproductive advantage, possibly a reproductive disadvantage. So the mutation would appear, stick around for a few generations at low frequency through random drift, and then disappear again when the person carrying it happened not to reproduce or their descendants didn't survive. Same mutation, different environment, different outcome. In Europe, that mutation was a lifesaver. In Africa, it was at best neutral and at worst harmful. Environment is everything. This brings us to a concept called balancing selection, which is relevant for populations living at intermediate latitudes. At very high UV levels, equatorial Africa, dark skin is optimal. At very low UV levels, northern Scandinavia, light skin is optimal. But what about places in between? What about Mediterranean regions, the Middle East, northern India, central China, where UV levels are moderate? In these regions, there's a trade-off. Darker skin provides better folate protection but might compromise vitamin D synthesis. Lighter skin provides better vitamin D synthesis but might compromise folate protection. The optimal solution is somewhere in the middle, intermediate skin tone that balances both selective pressures. And indeed, when you look at populations native to these intermediate latitudes, they tend to have intermediate skin tones. Not as dark as equatorial Africans, not as light as northern Europeans or northern East Asians. Medium brown, olive, tan, shades that represent a genetic compromise between competing selective pressures. In these populations, you might find genetic variation for both darker and lighter skin being maintained in the population, because neither is clearly superior. Maybe in unusually sunny years, people with darker skin have a slight advantage. In unusually cloudy years, people with lighter skin have a slight advantage. Over the long term, both variants persist at intermediate frequencies. This is balancing selection, multiple variants being actively maintained by natural selection, because each has advantages in different contexts. It's less common than directional selection, where one variant is clearly superior and spreads to fixation, but it does occur, and skin colour in intermediate latitudes might be one example. There's also the question of how quickly skin colour can change in response to changing environments. If a population migrates from one latitude to another, how long does it take for their skin colour to adapt to the new UV conditions? The answer seems to be surprisingly fast, at least in evolutionary terms, though not instantaneously. We've already seen that light skin evolved in Europeans within maybe 20,000 to 30,000 years, possibly much faster. That's quick, but it's not overnight. If a dark-skinned population moves to high latitudes and stays there for thousands of years, and if they're not getting adequate dietary vitamin D, they'll experience strong selective pressure and their skin will lighten relatively rapidly, within hundreds of generations, maybe faster. If a light-skinned population moves to low latitudes and stays there, they'll experience pressure to darken their skin, though possibly not as strongly because modern humans have cultural adaptations, clothing, shelters, dietary supplements that can partially buffer against the environmental pressure. And this brings up an interesting modern complication. Human populations have been moving around rapidly in the last few centuries, much faster than evolution can respond. Light-skinned Europeans settled in Australia, a high UV environment, and they haven't had time to evolve darker skin to adapt. The result? Australia has the highest rate of skin cancer in the world. Australians of European descent are getting blasted with UV levels their skin isn't adapted for, and skin cancer is the consequence. Conversely, dark-skinned populations have migrated to high latitudes, Africans to North America and Europe, for example, and they're experiencing vitamin D deficiency at higher rates than light-skinned populations in the same locations. Their skin is blocking UVB that's already scarce, and vitamin D deficiency is the consequence. These are examples of evolutionary mismatch, organisms living in environments their biology isn't adapted to. Modern medicine and technology can compensate: sunscreen, vitamin D supplements, protective clothing, but the biological mismatch is real. Now let's zoom back out from the molecular details and think about what all this means. The evolution of light skin is one of the most dramatic, most rapid, most well-documented examples of natural selection acting on human populations in recent history. It's not subtle. It's not ambiguous. It's not controversial among scientists, though it's sometimes misunderstood or misrepresented in public discourse. The evidence is overwhelming. Skin color is an adaptive trait that evolved in response to latitude-specific UV conditions through random mutations filtered by natural selection. Dark skin evolved first, in Africa, as protection against high UV. Light skin evolved later, multiple times independently in northern latitudes, as an adaptation to low UV. Different populations took different genetic routes to get there, but they ended up at similar destinations. This is evolution in action, playing out across geography and time, written in our genes and visible on our skin. And here's what I want you to really internalize. The specific mutations that cause light or dark skin are morally and functionally neutral outside of their UV context. SLC24. A 5 doesn't make you smarter or stronger or better. It just makes your skin lighter. That's it. That's all it does. It was beneficial in Northern Europe 15,000 years ago because lighter skin solved a vitamin D problem. It would have been harmful in equatorial Africa for the same reason. Lighter skin would have caused a folate problem. The mutation itself isn't good or bad. It's context dependent. And the fact that humans have constructed elaborate social hierarchies based on this molecular triviality is frankly absurd from a biological perspective. We've taken tiny variations in a handful of genes and used them to justify treating people differently, when the underlying biology is screaming at us that these variations are superficial adaptations to local sunlight conditions and nothing more. The molecular story of skin color evolution is a story of random mutations, environmental pressure, survival, and reproduction. It's elegant, it's logical, and it's completely impersonal. Evolution doesn't have preferences, it doesn't have goals. It just responds to whatever selective pressures are present by filtering genetic variation through differential survival and reproduction. The populations that happened to produce light skin mutations in low UV environments survived and thrived. The populations that didn't produce those mutations, or produced them in high UV environments where they were disadvantageous, didn't survive as well. That's it. That's the whole story at the molecular level. Everything else, all the social, cultural, political meaning we've layered onto skin color, is human construction, not biological reality. In the next part of our story, we're going to look at some fascinating exceptions to the general rule of high latitude equals light skin. Populations like the Inuit who live at extreme northern latitudes but remained relatively dark-skinned because they solved the vitamin D problem through diet rather than genetics. We'll also explore how agriculture accelerated the evolution of light skin in Europe by removing dietary sources of vitamin D and making the vitamin D crisis even worse. But for now, We're leaving this chapter with a clear understanding of the molecular machinery. A handful of genes, a few key mutations, strong selective pressure, rapid evolutionary change. That's how light skin happened. Not through divine intervention, not through purposeful self-modification, but through the blind, mechanical process of mutation and selection, playing out across thousands of generations. Evolution doesn't care about your hopes or fears or ideologies. It just grinds forward, generation after generation, editing the genome one mutation at a time, producing organisms that are well adapted to their local environments. And sometimes, when the environment changes dramatically, like when dark-skinned humans walk into northern winters, evolution edits fast. Now we need to talk about one of the most consequential accidents in human history, an event that completely transformed how humans lived, what they ate, where they settled, and, crucially for our story, how fast their skin colour evolved. About 10,000 to 12,000 years ago, in several different regions around the world more or less independently, humans figured out agriculture. They learned to plant seeds deliberately, harvest crops, save seeds for the next planting season, and gradually domesticate wild plants into more productive cultivated varieties. This sounds like progress, and in many ways it was. Agriculture supported much larger populations, enabled permanent settlements, allowed specialization of labor, and ultimately led to cities, writing, and civilization as we know it. But agriculture also created new problems, and one of those problems was a catastrophic worsening of the vitamin D crisis in northern latitudes. Farming, it turns out, accidentally turbocharged the evolution of light skin in European populations by eliminating dietary sources of vitamin D that hunter-gatherers had relied on. Let me explain how this happened, because it's a perfect example of how cultural changes can intensify biological selective pressures in ways nobody could have predicted. Let's start by understanding what hunter-gatherers were eating before agriculture, because this matters tremendously for vitamin D, and the details really bring home just how dramatic the dietary shift was. Hunter-gatherer diets were diverse, seasonal, and heavily dependent on local ecology, but across northern Europe they generally included significant amounts of animal products, meat, organs, bone marrow, and in coastal or riverine areas, fish and shellfish. And here's the critical point. Many animal products contain meaningful amounts of vitamin D, especially the parts that modern Western cuisine has largely abandoned, but that traditional cultures have always valued. Fatty fish are particularly rich in vitamin D, and I mean extraordinarily rich. Wild salmon can contain 600 to 1,000 IU of vitamin D per 3.5 ounce serving. Mackerel has similar levels. Herring has even more, up to 1,600 international units per serving. These fish accumulate vitamin D in their fatty tissues because they're eating algae, and smaller fish that synthesize or consume compounds related to vitamin D production, and it concentrates as you move up the food chain. A hunter-gatherer population living near the North Atlantic coast with regular access to fatty fish could easily consume 1,000 to 2,000 IU of vitamin D per day just from fish, which is well above the modern recommended daily intake of 600 to 800 IU. That's enough to maintain adequate vitamin D levels even with limited sun exposure. Cod liver oil deserves special mention because it's basically liquid vitamin D. A single tablespoon of cod liver oil contains about 1,360 international units of vitamin D, plus enormous amounts of vitamin A. Arctic and Scandinavian populations who had access to cod figured out long ago that cod liver, not the flesh, the liver specifically, was nutritionally valuable. They would render the oil from cod livers and consume it, either straight or mixed into food. Not exactly a delicacy by modern standards, and I suspect it's an acquired taste at best, but it's one of the richest natural sources of vitamin D available. The Vikings, centuries later, would trade cod liver oil as a valuable commodity. They understood it prevented certain illnesses, though they didn't know about vitamin D specifically. They just knew it worked, which was good enough. But fatty fish aren't the only dietary source. Land animals also contain vitamin D, and this is where eating the whole animal becomes important. The muscle meat that modern Western cuisine favours, steaks, chops, chicken breast, the parts you'd find at a typical grocery store, has almost no vitamin D. Maybe 5 to 10 IU per serving. Not enough to matter. But the organs? That's where the nutrition is. Beef liver contains about 50 IU of vitamin D per 3.5 ounce serving. Pork liver has similar amounts, kidneys have vitamin D, heart has some, brain has some. The point is, if you're eating the whole animal the way hunter-gatherers did, the flesh, yes, but also the liver, kidneys, heart, brains, tongue, marrow from the bones, rendered fat for cooking, you're accumulating vitamin D from multiple sources across the carcass. And hunter-gatherers absolutely ate the whole animal. They didn't have the luxury of being picky. When you successfully hunt a wild boar or deer after days of tracking, you use every edible part. The organs in particular were probably highly valued because they're incredibly nutrient-dense. Liver is rich in iron, vitamin A, B vitamins, and yes, vitamin D. Hunter-gatherers knew, not through formal nutritional science obviously, but through generations of practical experience, that eating organ meats kept you healthy in ways that just eating muscle meat didn't. Many traditional cultures gave the best parts of the animal, including organs, to pregnant women, nursing mothers, and growing children, the people who needed the most nutrients. That wasn't random. That was practical wisdom encoded in cultural practices, accumulated over thousands of years of observation about what foods produced healthy offspring. Animal fat also contains some vitamin D, particularly the fat from animals that have been exposed to sun, which would be all wild animals. They're not living in indoor feedlots. They're outside, getting sun exposure, which triggers vitamin D synthesis in their skin, and that vitamin D gets stored in their fatty tissues. So when you render the fat from a hunted animal and use it for cooking or eat it directly, you're getting some vitamin D. Not huge amounts, but every bit counts when you're living at northern latitudes with limited sun exposure. Eggs from wild birds also contain vitamin D in the yolk, about 40 to 50 international units per egg. Hunter-gatherers would have collected wild bird eggs seasonally when they were available. Duck eggs, goose eggs, eggs from various ground-nesting birds. Again, not a massive amount of vitamin D per egg, but if you're collecting and eating eggs regularly during nesting season, it contributes to your total intake. Even bones provided vitamin D indirectly through bone marrow and bone broth. Marrow is the fatty substance inside bones, and it's nutritious and delicious, rich in fat, minerals, and yes, some vitamin D. Hunter-gatherers would crack open bones to extract the marrow, which could be eaten raw or roasted. They'd also boil bones for hours to make broth, extracting minerals and nutrients from the bone matrix. This wasn't just for flavour, though bone broth does add richness to soups and stews. It was a way to extract every last bit of nutrition from an animal carcass. Nothing wasted, everything used. Add all of this up: fatty fish if you're coastal, organ meats from hunted game, animal fat, eggs, bone marrow, bone broth, and a hunter-gatherer living in northern Europe 15,000 years ago could reasonably be consuming 500 to 1,000 IU of vitamin D per day. From diet alone, possibly more if they had good access to fatty fish. That's not optimal. Sun exposure would still be important for maintaining adequate vitamin D levels, especially during summer when you need to build up stores for winter, but diet could compensate to a significant extent. The combination of some sun exposure during summer months plus regular consumption of animal products meant that hunter-gatherers could maintain vitamin D levels that, while probably not ideal by modern standards, were sufficient to avoid severe deficiency in most individuals most of the time. Now enter agriculture, stage left, with all the confidence of a technology that's about to change everything while creating a whole new set of problems nobody anticipated. Agriculture began in the Fertile Crescent, the region encompassing modern Iraq, Syria, Lebanon, Israel, Palestine, Jordan, and parts of Turkey and Iran, around 10,000 BCE. People started cultivating wheat, barley, lentils, chickpeas, and other crops. They domesticated sheep, goats, cattle, and pigs. The practice spread from there, reaching Europe by around 7,000 to 6,000 BCE, moving west and north through Greece, the Balkans, Italy, and eventually into Central and Northern Europe. By 4,000 to 3,000 BCE, agriculture had reached Scandinavia and the British Isles. This wasn't a rapid conquest. It took thousands of years for farming to replace hunting and gathering as the primary subsistence strategy across Europe. But once it did take hold in a region, it transformed life completely. Agriculture brought stability. You knew where your food was coming from, those fields right there that you planted and tended and would harvest in a few months. You could build permanent houses because you weren't following game animals around anymore. You could accumulate possessions because you didn't have to carry everything with you. You could support larger populations because farmed land produces more calories per acre than wild land. Villages grew into towns. Towns grew into cities. Specialization became possible. Not everyone had to be involved in food production, so you could have potters, metalworkers, priests, administrators. It was the foundation of civilization. Great, right? Except for one small problem. The agricultural diet was dramatically lower in vitamin D than the hunter-gatherer diet, and nobody realized this was a problem until the consequences started showing up in their children's bones. Here's what happened. Agriculture is based on plants: wheat, barley, oats, rye in Europe, rice in Asia, maize, beans, squash in the Americas. These crops provide the caloric foundation of the diet. You're growing grain, harvesting it, storing it, and eating it as bread, porridge, beer, whatever form works. Grain is great for calories. It stores well, it's relatively easy to grow in large quantities once you've figured out the techniques, and it can feed a lot of people per acre of land. But grain contains zero vitamin D. Plants don't synthesize vitamin D. They don't need it. They don't have bones to mineralize or calcium metabolism to regulate. The vitamin D pathway is an animal thing. So when you shift from a diet that's maybe 50 to 70% animal products, meat, fish, organs, eggs, dairy, to a diet that's maybe 70 to 80% grain and vegetables with only occasional animal products, your vitamin D intake drops off a cliff. And it gets worse because the animal products early farmers ate were different from what hunter-gatherers ate. Hunter-gatherers ate wild game: deer, boar, aurochs, wild cattle, various birds, fish from rivers and oceans. Wild animals, especially fish, have good vitamin D content. Farmers ate domesticated animals: sheep, goats, cattle, pigs. These animals were often kept primarily for milk, wool, and labour, with meat being a somewhat expensive byproduct. A farmer might slaughter an animal for meat a few times a year for special occasions, but day-to-day animal protein came more from dairy products and eggs, which have some vitamin D but not as much as wild fatty fish or organ meats. And crucially, early farmers often settled inland, on fertile river valleys or plains with good soil for growing crops, places that were far from the ocean. No ocean fish means no salmon, no herring, no mackerel, no cod liver oil. You might have access to freshwater fish from rivers: pike, perch, trout, but these have maybe 1/10 the vitamin D content of ocean fish, not nearly enough to compensate for the lack of sun exposure in northern latitudes. Let me paint you a picture of what an early farming community in northern Europe might have looked like, diet-wise, because understanding the specifics helps clarify why this created such an intense vitamin D crisis. You've got a village of maybe 100 to 200 people living in wooden longhouses in what's now Germany or southern Scandinavia, around 4000 BCE. The village is surrounded by fields where they grow barley, wheat, and some legumes. They have a small herd of cattle, some sheep, a few pigs. The cattle are primarily dairy animals. They're too valuable for labour and breeding to slaughter regularly. The sheep are kept for wool. The pigs are occasionally slaughtered for meat, but sparingly. A typical daily diet for a person in this village might look like this. Breakfast is barley porridge, maybe with some milk if the cows have been giving milk, perhaps sweetened with honey if it's available, but more likely just plain. Lunch is bread made from wheat or barley flour, possibly some cheese if it's available, maybe some onions or cabbage from the garden if it's summer. Dinner is more bread or porridge, occasionally some pork or mutton if an animal was recently slaughtered, but more often just beans or lentils for protein, some root vegetables, turnips, parsnips, whatever stores well over winter. Eggs occasionally, if the chickens have been laying and if the eggs aren't needed for breeding more chickens. Milk or whey to drink if you have access to dairy animals. Maybe some wild greens or berries during summer when they're available, though you're spending so much time on agricultural work that foraging becomes a secondary activity. Maybe some ale if you've brewed it, which many households did because ale was safer to drink than water in many cases, and provided some calories from fermented grain. It's not a starvation diet. There are adequate calories, reasonable amounts of protein from beans and occasional animal products, sufficient carbohydrates from grain, but look carefully at what's missing. No fatty fish whatsoever unless you're one of the lucky families that can afford to buy dried or salted fish from coastal traders, which is expensive and beyond the means of most subsistence farmers. No organ meats from wild game because you're not hunting wild game anymore, you're too busy farming, and the wild game populations have declined anyway as forests have been cleared for agriculture. Very little animal fat compared to a hunter-gatherer diet because your domesticated animals are too valuable to slaughter regularly. The fat you do eat comes mostly from milk and cheese, which have some fat, but it's not the same as eating the rendered fat from a wild boar or deer. Almost no food source is rich in vitamin D. The diet is maybe 70 to 80% grain and plant products by calories, 20 to 30% animal products. And the animal products you do eat are mostly milk, cheese, and occasional meat, not the liver, kidney, bone marrow, and fatty fish that hunter-gatherers would have consumed regularly and that actually contain meaningful amounts of vitamin D. You're essentially living on bread, porridge, vegetables, and dairy. It's filling. It keeps you from starving. But it's nutritionally deficient in specific ways that you have no ability to recognize or understand because the science of nutrition won't exist for another 10,000 years. And let's talk about what occasional meat actually means in an early farming economy, because this matters for understanding the depth of the dietary shift. When I say farmers ate meat occasionally, I mean maybe a few times a month at most, possibly less depending on the season and the wealth of the household. Domesticated animals were valuable capital assets, not food on the hoof. A cow could provide milk for years, multiple calves over its lifetime, and eventually meat when it was too old to produce milk. But if you slaughter it early, you lose all that future production, so you keep it alive as long as it's productive. Same with sheep. They provide wool every year through shearing, and they produce lambs that grow up to produce more wool and more lambs. Slaughtering them means losing that ongoing production. Pigs were the exception because they don't provide anything while alive except offspring, and they can be fed on scraps and waste that other animals can't eat. So pigs were raised primarily for meat. But even pigs were slaughtered strategically, usually in late fall before winter when you couldn't feed them anymore, and the meat would be preserved through salting or smoking to last through winter. You'd have fresh pork for a brief period around slaughter time, and then you'd be eating preserved pork sparingly through the rest of the year, making it last as long as possible. Compare this to a hunter-gatherer economy, where meat consumption could be quite high, especially for successful hunters. A hunting party kills a wild boar or deer, and that's maybe 50 to 100 pounds of meat plus organs, plus bones for marrow and broth. For a small group of 20 to 30 people, that's several pounds of meat per person. They'd feast on fresh meat for a few days, couldn't let it go to waste before it spoiled, and preserve what they couldn't eat immediately through smoking or drying. Then they'd go hunt again. The meat supply was variable, sometimes abundant after a successful hunt, sometimes scarce between hunts. But over time, meat and animal products probably constituted a large portion of the diet, maybe 40 to 60% of calories for some Northern European hunter-gatherer groups. That's dramatically different from 20 to 30% for farmers, and the social dynamics around meat were different too. In a hunter-gatherer society, successful hunters shared meat with the community because they couldn't eat an entire deer by themselves before it spoiled, and because reciprocal sharing was how you built social networks that would support you when you were the one who needed help. So meat was distributed relatively widely, and everyone got some, though the best parts might go to high-status individuals or people with special needs like pregnant women. In a farming society, animals belonged to individual households, and slaughtering an animal meant that household got the meat. You might share some with neighbours or relatives, but the distribution was less communal. If your household didn't own many animals, you ate less meat. If you were poor, you might eat meat only a few times a year, at festivals or special occasions. This created class stratification in diet that didn't exist to the same extent in hunter-gatherer societies, where everyone participated in the hunt and everyone shared in the kill. The elimination of fishing from the diet also deserves more attention because it's such a dramatic loss of vitamin D. Hunter-gatherers living near coastlines or major rivers didn't just occasionally eat fish, they ate fish constantly. Fishing was a daily or near-daily activity. Fish runs happened seasonally. Salmon, for example, swim upstream to spawn at specific times of year, and when the runs happened, you could catch enormous quantities of fish. Archaeological sites from coastal hunter-gatherer communities show massive middens, trash piles, full of fish bones, shellfish remains, seal bones if they were hunting marine mammals. These people were eating seafood as a staple, not a luxury. A coastal hunter-gatherer family might eat fish at every meal during good fishing seasons. Farming changed this completely. Farms were located inland on fertile soil good for growing crops. River valleys, yes, but usually not right on the coast where soil might be sandy or salty. You settled where you could grow wheat and barley successfully, and those places were usually miles from the ocean, sometimes dozens of miles. Rivers provided freshwater fish, but as I mentioned earlier, freshwater fish have much lower vitamin D content than ocean fish. We're talking maybe 50 to 100 IU per serving, versus 600 to 1,600 IU for fatty ocean fish. And river fishing was less productive than ocean or estuary fishing. You could catch pike, perch, trout, but in smaller quantities than you could catch ocean fish. So fish went from being a daily staple to being an occasional supplement, and even when farmers did eat fish, it was the wrong kind of fish for vitamin D. Now imagine you're a child growing up in this village. You're eating this grain-heavy, vitamin D-poor diet from infancy through childhood. Your mother might have breastfed you for a couple of years. Breastfeeding was universal in pre-modern societies, not by choice, but because there were no alternatives. But breast milk contains vitamin D only if the mother has adequate vitamin D, which she probably doesn't if she's eating a farming diet and living at 50 degrees north latitude. So you're starting life already somewhat deficient. Then you're weaned onto the same grain-based diet everyone else eats. Porridge, bread, milk if it's available, occasional vegetables, rarely any meat or fish. You live in a house, which means you're spending significant time indoors. Hunter-gatherer children are outside essentially all the time. They're following their parents around as the family moves across the landscape hunting and gathering, playing outside, exposed to sun whenever it's available. Farmer children might be outside working in the fields during planting and harvest seasons, and those are crucial times when vitamin D synthesis can happen if the sun cooperates. But they also spend a lot of time indoors doing domestic tasks, grinding grain, preparing food, spinning and weaving, watching younger siblings, all the endless labour required to keep a household functioning. In winter, everyone spends most of their time indoors near the fire because it's too cold to be outside for long periods. Less sun exposure means less vitamin D synthesis. Less vitamin D from food means less dietary backup. And you're at 50 or 55 degrees north latitude where winter sun provides almost no UVB for vitamin D synthesis anyway. All of these factors compound. The result? Rickets. Lots and lots of rickets. Archaeological evidence from early farming communities in northern Europe shows rickets rates that are absolutely staggering. We're not talking about isolated cases or rare conditions. We're talking about epidemic levels. Some cemetery populations show 40%, 50%, in some cases even 60% of children with visible bone deformities consistent with rickets. Let me put that in perspective. That means more than half the children in some farming communities were suffering from severe vitamin D deficiency to the point where their bones were visibly deforming. This isn't subtle. This isn't slightly suboptimal vitamin D levels. This is massive population-wide nutritional catastrophe that would have been obvious to anyone looking at the community's children. Picture a village with 200 people, 80 of whom are children under age 15. If 50% of those children have rickets, that's 40 kids with bowed legs, deformed chests, dental problems, stunted growth, chronic pain. That's 40 families dealing with the grief and confusion of watching their children suffer from a condition they don't understand and can't treat. That's 40 kids who will grow up with permanent skeletal deformities, limited mobility, chronic health problems, and if they're girls, potentially life-threatening pregnancy complications. And this is happening in village after village across northern Europe as agriculture spreads and replaces hunting-gathering. It's a humanitarian crisis in slow motion, playing out over thousands of years, affecting millions of individuals, and nobody understands why it's happening or how to stop it. The archaeological evidence is heartbreaking when you look at it closely. Excavations of Neolithic cemeteries in places like Denmark, Germany, Poland and Britain have uncovered skeletal remains that tell devastating stories. Children buried with severely bowed femurs and tibias, the long bones of their legs curved from bearing weight on an inadequate bone structure. Young adults with shortened stature, maybe 5 to 10 centimetres shorter than their genetic potential would have allowed, because their bones didn't grow properly during childhood. Women with deformed pelvises showing signs of obstructed labour, sometimes with fetal remains still in the birth canal, frozen in the final moments of a death that should have been preventable. Teeth showing enamel hyperplasia, those horizontal grooves or pits that form when tooth development is disrupted by severe illness or malnutrition during childhood. Skulls with craniosynostosis, premature fusion of skull bones that can occur with rickets. Ribs with the rachitic rosary, those characteristic nodules at the junction points. One particularly well-documented example comes from a Neolithic site called Ajvide on Gotland, an island in the Baltic Sea off the coast of Sweden. This was a farming community dating to about 3000 BCE. Archaeologists excavated a cemetery with remains of over 80 individuals spanning several generations. When anthropologists analysed the skeletons for health markers, they found that approximately 40% of the children and young adults showed signs of rickets. Some cases were mild, slight bowing of the legs, minor dental problems. Others were severe, extreme bone deformations that would have caused significant disability. The pattern was clear. This wasn't random bad luck affecting a few unlucky families. This was a systematic problem affecting the entire community across multiple generations. The farming lifestyle was creating conditions that made vitamin D deficiency endemic. Similar patterns emerged from other sites. Hambledon Hill in southern England, a Neolithic causewayed enclosure dating to around 3500 BCE, has yielded skeletal remains showing high rates of rickets among children. Windmill Hill, another Neolithic site in England from the same period, shows the same pattern. Multiple sites in Denmark from the Neolithic and Bronze Age periods show elevated rickets rates compared to earlier Mesolithic pre-agricultural sites in the same region. The transition from hunting-gathering to farming correlates clearly with increased rates of skeletal indicators of vitamin D deficiency. The bones don't lie. The evidence is unambiguous. Farming made the vitamin D crisis worse. And the consequences rippled through communities in ways that went beyond just individual health. High rates of childhood disability meant more labour burden on healthy family members who had to care for disabled children while also maintaining the farm. Women dying in childbirth meant children growing up without mothers, which had cascading effects on child survival and family welfare. Short stature meant reduced physical capability for agricultural labour, which required strength and endurance. Chronic bone pain reduced work efficiency. Dental problems affected ability to eat tough foods. The health crisis created by vitamin D deficiency had economic and social consequences that would have affected the entire community's resilience and survival. They probably noticed that farming life seemed less healthy in some ways than the old hunting life their grandparents had told stories about. Hunter-gatherers, despite the popular image of their lives as nasty, brutish and short, actually had pretty good nutrition by pre-modern standards. They ate diverse diets, got plenty of exercise, and while they faced dangers from hunting accidents, predators, and tribal conflicts, they didn't have the infectious disease burden that comes from living in dense permanent settlements with domesticated animals and poor sanitation. Farmers, on the other hand, lived in crowded villages where diseases could spread easily. They worked long hours doing repetitive agricultural labour that was hard on the body. Turns out hoeing fields and harvesting grain by hand is actually physically exhausting in a different way than hunting, and their diets, while providing reliable calories, were less nutritionally diverse. The transition from hunting-gathering to farming came with trade-offs. More food security and population growth, yes, but also new health problems, including, though they didn't realise it, a massive increase in vitamin D deficiency. And here's where evolution kicks into overdrive. Remember, natural selection works by filtering genetic variation through differential survival and reproduction. The stronger the selection pressure, the faster evolution proceeds. When hunter-gatherers in northern Europe had access to dietary vitamin D from fish and wild game, the pressure to evolve lighter skin was real, but not absolutely critical. Sure, lighter skin would help with vitamin D synthesis, and individuals with lighter skin would have some reproductive advantage, but it wasn't life or death for most people, because they could compensate partially through diet. But once agriculture eliminated those dietary sources, the pressure intensified dramatically. Now lighter skin wasn't just helpful, it was essential. The difference in survival and reproduction between dark-skinned and light-skinned individuals widened. Dark-skinned farming children had very high rickets rates. Light-skinned farming children had lower rickets rates. The fitness differential increased, and evolution accelerated. We can actually see this acceleration in the genetic evidence. When scientists analyse ancient DNA from skeletal remains across Europe from different time periods, they can track the frequency of light skin alleles over time and watch them spread. What they find is fascinating. The major European light skin mutations in SLC24A5 and SLC45A2 were present at low frequencies in European populations during the Mesolithic period, the period after the Ice Age but before agriculture, roughly 10,000 to 6000 BCE when people were still hunter-gatherers. These mutations had probably been around for thousands of years already, drifting at low frequencies, providing some advantage but not spreading rapidly. Then agriculture arrives, and the frequency of these alleles explodes. By the Bronze Age, 3000 to 1000 BCE, they're approaching fixation in northern European populations. The transition from light skin is rare to light skin is universal happens much faster after agriculture than it was happening before agriculture. This strongly suggests that farming intensified the selective pressure. A specific example helps make this concrete. La Braña 1, a skeleton from northern Spain dating to about 7,000 years ago, was a Mesolithic hunter-gatherer. Genetic analysis showed he had dark brown skin and blue eyes, an unusual combination to modern eyes, but common in European hunter-gatherers of that period. He lived in Spain at about 43 degrees north latitude, in a region with relatively good sun exposure compared to northern Europe. He had the genes for blue eyes, mutations that had already spread in European populations, but he still had dark skin because the light skin mutations hadn't spread widely yet. Fast forward 2,000 years to the Neolithic period, after farming had spread to Spain. Skeletal remains from early farming communities in Spain dating to 5,000 years ago start showing mixed genetics. Some individuals still have dark skin genes, but light skin genes are becoming more common. Fast forward another 2,000 years to the Bronze Age 3,000 years ago. By this point, most skeletal remains in Spain show predominantly light skin genetics. The transition happened over roughly 4,000 years, from 7,000 years ago to 3,000 years ago, and it correlates closely with the spread of agriculture through the region. Similar patterns show up across Europe. In Scandinavia, where agriculture arrived later, around 4000 BCE, the transition to light skin appears to have happened even faster once farming took hold, probably because the vitamin D crisis was more severe at those higher latitudes. Hunter-gatherers in Scandinavia who had access to ocean fish could maintain adequate vitamin D. Farmers in Scandinavia eating grain-based diets inland could not. The selective pressure was enormous, and light skins spread like wildfire, possibly reaching near fixation within just 1,000 to 2,000 years after agriculture became the dominant subsistence strategy. That's incredibly fast. Evolutionary changes that normally take tens of thousands of years happened in just a few thousand years because the selective pressure was so intense. Now you might be wondering, didn't these farming populations eventually figure out that diet matters? Didn't they notice that people who ate more animal products seemed healthier? And the answer is, probably to some extent, but knowledge of nutrition was limited, and more importantly, dietary choices are constrained by what's available and affordable. If you're a subsistence farmer living on a small plot of land, you grow crops because crops provide reliable calories that keep your family alive. You keep some animals for dairy and eggs and occasional meat, but you can't afford to slaughter animals frequently because they're more valuable alive. A cow produces milk for years, but you can only butcher it for meat once. Ocean fish might be available if you live near the coast, but if you're inland, getting fish means trade, which means you need something to trade, which you might not have. Dried or salted fish from the coast might be available at markets, but again, that costs money or trade goods that a subsistence farmer might not have. In other words, even if people noticed a correlation between diet and health, they couldn't necessarily act on it. They ate what they could produce or afford, which for most farmers meant a grain-heavy diet with limited animal products. Only wealthier individuals, people who could afford to regularly purchase meat, fish, and other expensive foods, had access to adequate dietary vitamin D. This probably created a class gradient in rickets rates, with poorer farming families experiencing higher rates of rickets than wealthier families. But everyone was affected to some degree, and the selective pressure for lighter skin remained intense across the population, just stronger in some communities than others. There's also an interesting dynamic around milk consumption that's worth mentioning. Dairy products contain some vitamin D, not as much as fatty fish, but more than nothing. Fresh milk contains maybe 40 IU of vitamin D per cup. Cheese contains a bit more, depending on the type. So populations that consumed a lot of dairy, and many early farming populations did because keeping dairy animals was an efficient way to convert grass into calories and protein, had somewhat better vitamin D status than populations that consumed less. Dairy. But here's the catch. Most adult humans in most populations were lactose intolerant. The ability to digest lactose as an adult a trait called lactase persistence, is controlled by a genetic mutation that appeared and spread in some populations but not others. This mutation is very common in northern European populations, where dairy farming was intensive, but rare or absent in many other populations. The standard human pattern is to produce the enzyme lactase, which breaks down lactose milk sugar, as an infant and young child, but then stop producing it after weaning. This makes sense. If you're not drinking milk anymore, why waste energy producing an enzyme you don't need? But in populations that started dairy farming and relied heavily on milk as a food source, there was suddenly a selective advantage to being able to digest milk as an adult. You could access more calories and nutrients from your herds. A mutation that kept lactase production going into adulthood, lactase persistence, appeared and spread rapidly in these populations. By the Bronze Age, lactase persistence was common in northern Europe, less common in southern Europe, and rare in populations that didn't practice intensive dairy farming. This created an interesting feedback loop. Populations that developed lactase persistence could consume more dairy, which provided some dietary vitamin D, which slightly reduced the selective pressure for lighter skin, but only slightly, because milk doesn't contain enough vitamin D to fully solve the problem. Meanwhile, populations without lactase persistence couldn't consume much dairy without getting sick. Lactose intolerance causes digestive problems, cramps, diarrhea, all of which would have been seriously debilitating in a pre-modern context. So they relied even more on grain-based diets with minimal animal products, experienced even worse vitamin D deficiency, and faced even stronger selective pressure for lighter skin. Genetics and culture and diet all feeding back on each other in complex ways. Let's talk about geography, because not all agricultural populations experienced this crisis equally. Populations in the Mediterranean region who adopted farming, Greeks, Italians, Southern French, North Africans, had the advantage of living at lower latitudes with better sun exposure. They could synthesize vitamin D from sun even on a grain-heavy diet, as long as they spent enough time outside. Their skin color changed somewhat. Mediterranean populations today are lighter than equatorial African populations, but the pressure wasn't as extreme as in northern Europe. They could afford to retain more melanin because the vitamin D crisis wasn't as acute. This is why southern Europeans have darker skin on average than northern Europeans. The selective pressure for extremely light skin was weaker at those latitudes, so the population didn't lighten as much. Populations in the Middle East, where agriculture first developed, faced a different situation. They were at intermediate latitudes, 35 to 40 degrees north, where sun exposure was reasonably good. But they were also in a region where agriculture had been practiced longer, which meant more generations of living on grain-heavy diets. And many Middle Eastern populations lived in urban areas by the Bronze Age, where people spent time indoors, wore protective clothing to shield from the intense sun, and had limited access to fresh fish if they lived inland. The result was a mix. Some Middle Eastern populations lightened significantly, others less so, depending on local conditions. Modern Middle Eastern populations show a wide range of skin tones from quite light to quite dark, reflecting complex histories of migration, mixing, and local adaptation to different UV and dietary conditions. East Asian populations also experienced the agricultural transition, though with different crops: rice in southern China and Southeast Asia, millet in northern China, and somewhat different timelines. The vitamin D crisis in East Asia was real, but possibly less severe than in Europe for a few reasons. First, many early agricultural populations in China had access to fish from rivers or the ocean. China has a long coastline and major rivers that provided freshwater fish. Second, East Asian cuisine traditionally included more diverse animal products, including insects, which can contain some vitamin D. Third, the latitude range in China spans from tropical in the south to temperate in the north, so populations in southern China faced less vitamin D stress than populations in northern China. But northern Chinese populations did face similar pressures to northern Europeans, and they evolved lighter skin, as we discussed earlier, through different genetic mutations. One of the most striking pieces of evidence for the agricultural acceleration hypothesis comes from comparing populations that adopted farming to populations that didn't. The Sami people of northern Scandinavia, who historically practiced reindeer herding rather than agriculture and consumed a diet rich in reindeer meat, fish, and other animal products, have somewhat darker skin on average than their Swedish and Norwegian farming neighbours, despite living at the same high latitudes. They're not as dark as Africans, obviously. They've still undergone some lightening due to low UV exposure, but they retained more pigmentation than farming populations because their diet provided adequate vitamin D. Similarly, Inuit populations in the Arctic, who we'll discuss more later, maintained relatively dark skin despite extreme northern latitudes because their traditional diet of marine mammals, seals, and fish provided massive amounts of vitamin D, far more than they could ever synthesize from sun exposure. These exceptions prove the rule. The intensity of the selective pressure for light skin depended not just on latitude, but on diet. Cut off dietary vitamin D through the adoption of grain-based agriculture, and the pressure for light skin intensifies dramatically. There's also evidence from skeletal health markers that farming populations had worse vitamin D status than hunter-gatherer populations. When archaeologists compare skeletal remains from hunter-gatherer cemeteries to early farming cemeteries in the same region, they consistently find higher rates of rickets, dental problems, shorter stature, and other markers of nutritional stress in the farming populations. This isn't just about vitamin D. Agriculture also introduced other dietary deficiencies and health problems, but vitamin D deficiency is clearly part of the pattern. The bones don't lie. You can see the disease in the archaeological record, preserved in thousands of skeletons from early farming communities across Europe. And here's something that often gets overlooked. This wasn't just an ancient problem. Vitamin D deficiency continued to be a serious issue in European populations well into the modern era. Rickets was endemic in industrial cities in 19th century Europe. London, Manchester, Glasgow, cities where working-class children lived in crowded, polluted conditions, rarely saw sunlight because they worked long hours indoors in factories and ate poor diets consisting mainly of bread and other cheap starches. Charles Dickens wrote about children with bowed legs and deformed bones in his novels because it was a visible, common reality in Victorian England. The problem wasn't solved until the 20th century when vitamin D was identified, when milk started being fortified with vitamin D, and when public health campaigns encouraged sun exposure and better nutrition. For tens of thousands of years, from the adoption of agriculture until the mid-20th century, vitamin D deficiency was a persistent health problem in northern populations, only partially mitigated by the evolution of lighter skin. So agriculture fundamentally changed the trajectory of human evolution in northern latitudes. It created a massive increase in population size. Farming supports far more people per square mile than hunting and gathering, which meant more opportunities for beneficial mutations to appear and spread. It created intense new selective pressures by eliminating dietary vitamin D sources. It accelerated the evolution of light skin by making the fitness difference between dark-skinned and light-skinned individuals much more extreme. And it did all of this as an unintended consequence of people trying to secure more reliable food sources for their families. Nobody set out to change the human genome, they just wanted to not starve. But by changing what they ate and where they lived, they fundamentally altered the evolutionary pressures acting on their populations, and their descendants' appearances changed as a result. This is a perfect example of how culture and biology interact. Culture, in this case, the cultural innovation of agriculture, creates new environmental conditions. Those new conditions change which genetic variants are advantageous and which are disadvantageous. Natural selection acts on those variants. The population's genetic makeup shifts. Physical appearance changes. All without anyone understanding what's happening or why. The farmers burying children with rickets had no idea they were living through one of the most intense episodes of natural selection in human history. They just knew their children were sick and they didn't know how to fix it. But at the genetic level, evolution was grinding away, spreading the light skin mutations that provided a survival advantage in this new agricultural context. And the speed of this process is worth emphasizing one more time because it's genuinely remarkable. We're talking about visible, dramatic changes in appearance, from dark brown skin to pale white skin, happening in just a few thousand years. 4,000 years sounds like a long time, but it's only 160 generations at 25 years per generation. That's recent enough that if you could somehow line up all your direct ancestors from you back to an early European farmer, you could literally watch skin color change step by step, generation by generation, from dark to light. Early in the line, everyone is dark-skinned. Midway through, you'd see a mix, some dark, some medium, some light. Near the end, almost everyone is light-skinned. And all of this happened because people started growing grain instead of hunting deer, moved inland away from fish, and inadvertently eliminated their primary dietary source of vitamin D while living at latitudes where sun exposure couldn't. Compensate. Cause and effect, playing out across thousands of years, written in bones and genes and skin colour, visible to anyone who knows how to read the evidence. The agricultural revolution was many things: a technological breakthrough, a social transformation, the foundation of civilization, and one of the most important events in human history. But it was also, unintentionally and unknowingly, an evolutionary catalyst that turbocharged the development of light skin in northern populations by making the vitamin D crisis exponentially worse. The farmers who planted those first wheat fields in northern Europe had no idea they were also planting the seeds of a dramatic evolutionary transformation that would change what their descendants looked like 100 generations later. They were just trying to survive another winter. But survival is what evolution is all about, and the populations that survived were the ones whose random genetic mutations happened to solve the new vitamin D problem created by agriculture. The rest, as they say, is history, or more accurately, evolutionary biology. So we've established a pretty clear pattern. Humans migrated to northern latitudes, lost access to adequate UVB radiation for vitamin D synthesis, developed severe vitamin D deficiency that killed their children and caused women to die in childbirth, and evolved lighter skin through random mutations that allowed more UV penetration and solved the vitamin D crisis. High latitude equals light skin, low latitude equals dark skin. Simple, right? Evolution following predictable rules based on UV exposure. Except evolution doesn't always follow simple rules, and there are some spectacular exceptions to this pattern that actually help us understand the underlying mechanism even better. The most famous exception, the one that really makes evolutionary biologists sit up and take notice, is the Inuit. The Inuit, the indigenous peoples of the Arctic regions of North America, Greenland, and eastern Siberia, live at some of the most extreme northern latitudes inhabited by humans. We're talking about 60, 65, 70 degrees north, well into the Arctic Circle. Some Inuit communities in northern Greenland and Arctic Canada are above 75 degrees north. These are latitudes where the sun doesn't rise above the horizon for months during winter, where summer days last 24 hours but the sun never gets very high in the sky even at its peak, where UVB radiation levels are extraordinarily low year-round. If there's any population on Earth that should have evolved extremely light skin to maximize vitamin D synthesis from whatever weak UV is available, it's the Inuit. And yet, when European explorers first encountered Inuit populations in the 16th and 17th centuries, they described them as having relatively dark skin. Not as dark as equatorial Africans, but noticeably darker than Europeans, more of a medium brown, or olive tone rather than pale white. This seems to violate everything we've established about skin colour evolution. The Inuit have been living at these extreme northern latitudes for at least 4,000 to 5,000 years, possibly longer depending on which ancestral populations you're counting. That's plenty of time for light skin mutations to appear and spread if there was strong selective pressure for them. They experienced the same winter darkness, the same weak UV, the same basic environmental conditions that drove Europeans and Northern Asians to evolve light skin. So why didn't the Inuit evolve light skin? What's going on here? The answer is diet, and it's one of the most elegant demonstrations you'll find of how cultural adaptations can override biological selective pressures. Let's talk about what the traditional Inuit diet consisted of, because once you understand what they were eating in detail, the whole puzzle makes perfect sense, and you start to appreciate just how complete their cultural solution to the vitamin D problem was. The Inuit were, and in some communities still are to the extent that traditional lifestyles persist, marine hunters operating in one of the harshest environments on Earth. Their diet was based almost entirely on animals from the ocean: seals, whales, walruses, fish, seabirds, and occasionally land animals like caribou or polar bears when available. And I don't mean they ate these animals occasionally as supplements to a plant-based diet. I mean these animals were the diet, the whole diet, pretty much everything they consumed. Somewhere between 90% and 99% of traditional Inuit calories came from animal sources, depending on the season, the specific community, and what was available at any given time. Plants are scarce in the Arctic, and that's putting it mildly. There are no forests, tree-line ends well south of most Inuit territories. There's limited vegetation, some low shrubs, lichens, mosses, grasses during the brief summer. Growing seasons are incredibly short, maybe 2 to 3 months of the year when temperatures rise above freezing and plants can actually grow. You can gather some berries, crowberries, blueberries, cranberries, during late summer when they ripen. You can dig up some roots. You can collect certain edible plants and seaweeds along the coast. But these plant foods are not abundant enough to form a significant part of your diet. They're seasonal supplements, nice when available, but not something you can rely on for caloric needs. The Inuit adapted to an environment where plant foods were essentially unavailable for most of the year by becoming obligate carnivores, or more accurately, obligate consumers of marine mammals and fish, and they became extraordinarily good at it. Seal hunting was the foundation of traditional Inuit subsistence, and we're talking about multiple species, ringed seal being the most common, but also bearded seal, harp seal, hooded seal, harbour seal depending on the region. Seals are relatively abundant in Arctic waters. They're not as dangerous to hunt as whales, and they're a manageable size for a hunting party to transport back to camp. A single ringed seal provides maybe 50 to 100 pounds of meat and blubber, enough to feed a family for days or weeks depending on family size and what other food is available. Hunting seals required sophisticated technology and knowledge. You needed to find their breathing holes in the ice and wait for hours in freezing temperatures, or you needed to approach them on the ice without spooking them, or you needed to hunt them. From kayaks in open water during summer. The Inuit developed specialized harpoons designed to penetrate seal skin and blubber, with detachable heads that stayed in the seal while the hunter maintained control via a line. Not exactly the kind of gear you can pick up at your local sporting goods store. This was highly refined technology developed over thousands of years, and once you killed a seal, you used every part. The meat was eaten fresh when available, or dried or frozen for storage. The blubber, that thick layer of fat insulating the seal from frigid water, was eaten both fresh and rendered into oil for cooking, lighting, and heating. Seal blubber is incredibly energy dense, and in an environment where you need massive caloric intake just to maintain body temperature, high-fat foods are essential. The organs, liver, kidneys, heart, intestines, were prized delicacies, eaten fresh or cooked, rich in nutrients including massive amounts of vitamin D. The skin was used for clothing and kayak covering. The bones were carved into tools, needles, and weapons. Nothing was wasted because nothing could afford to be wasted. A seal represented days or weeks of food, fuel, and materials, and every part had value. Whale hunting was more dangerous and required more coordination, but the payoff was enormous. A bowhead whale could provide 50 to 70 tons of meat and blubber. That's not a typo. Tons, not pounds. One successful whale hunt could feed an entire community for months. Beluga whales are smaller, maybe 1 to 1.5 tons, but still represent a huge food source. Narwhals, with their distinctive spiral tusks, were hunted both for meat and for the ivory tusk, which had trade value. Whale hunting required multiple hunters working together, specialized weapons, larger harpoons than those used for seals, and boats that could handle rough Arctic seas. The Inuit developed the umiak, a large open boat made from driftwood or whale bones covered with seal or walrus skin, specifically for whale hunting. Multiple families would work together on a whale hunt, and the meat and blubber would be distributed according to complex social rules about who participated and what role they played. And what they did with whale and seal products is fascinating from a nutritional perspective. Fresh meat was eaten raw, cooked, or dried. Raw meat might sound unappetizing to modern Western sensibilities, but it has significant nutritional advantages in an Arctic environment. Cooking destroys some vitamins, particularly vitamin C, and in an environment where scurvy is a real threat and plant sources of vitamin C are unavailable. Eating raw meat and organs preserves the vitamin C naturally present in animal tissues. The Inuit didn't develop scurvy the way European Arctic explorers did, despite eating virtually no plants, specifically because they ate significant amounts of raw or lightly cooked meat and organs. Blubber deserves special attention because it's nutritionally extraordinary, and because it's so central to vitamin D intake. Seal blubber is about 90% fat by composition, and it's not just any fat. It's rich in omega-3 fatty acids from the fish the seals eat, and it contains staggering amounts of fat-soluble vitamins including vitamin D and vitamin A. The Inuit ate blubber, both solid, chunks of blubber with some meat attached, eaten fresh or after a short fermentation period, and rendered into oil. Rendering involved heating the blubber to melt the fat, then straining out the solid bits, leaving pure seal oil or whale oil. This oil was consumed straight, mixed into food, used for cooking, and burned in lamps for light and heat during the long Arctic night. You'd fill a shallow stone lamp with seal oil, insert a wick made from moss or other fibrous material, light it, and you'd have both light and heat. Not a lot of heat, certainly not enough to warm an entire dwelling to comfortable temperatures, but enough to keep your living space above freezing and provide light for working during the months of polar night. From a vitamin D perspective, this constant consumption of blubber and organ meats is the key to the whole story. When scientists have analysed the vitamin D content of traditional Inuit foods, the numbers are frankly astonishing. Seal meat contains roughly 1,500 to 2,000 IU of vitamin D per 3.5 ounce serving, which is already 3 to 4 times higher than the richest plant source, which would be mushrooms exposed to UV light, and good luck finding those growing wild in the Arctic. But that's just the meat. Seal blubber can contain 3,000 to 4,000 IU per serving. Seal liver? We're talking 5,000 to 10,000 IU or more depending on what the seal has been eating and the season. Whale blubber is similar or even higher. Beluga muktuk, that's the skin and outer layer of blubber from beluga whales, typically eaten raw and frozen, sliced thin like sushi, can contain 4,000 to 5,000 IU per serving. It's considered a delicacy in traditional Inuit cuisine, and people would eat it at celebrations and special occasions, but also just as regular food when available. Now let's do the math on what this means for daily vitamin D intake, because the numbers are genuinely remarkable. A traditional Inuit hunter or family member consuming primarily seal and whale might eat, say, half a pound of meat, a quarter pound of blubber, and some organ meats over the course of a day. That's not unusual in an Arctic environment where you're burning 4,000 to 5,000 calories per day just to maintain body temperature and perform physical activities like hunting. You eat a lot. Half a pound of seal meat, 3,000 to 4,000 IU. Quarter pound of blubber, 3,000 to 4,000 IU. A serving of liver or other organs, 2,000 to 5,000 IU. Add it up, and you're looking at 8,000 to 13,000 IU of vitamin D per day, possibly more if you're eating particularly vitamin D-rich parts like liver, or if you're consuming extra blubber for energy in extremely cold conditions. Now, here's where it gets interesting from a vitamin D perspective. Marine mammals, particularly seals and whales, contain absolutely massive amounts of vitamin D in their tissues, far, far more than terrestrial animals, and more than most fish. A serving of seal meat contains somewhere around 1,500 to 2,000 IU of vitamin D. That's already impressive, 2 or 3 times what you'd get from salmon. But seal meat isn't even the most vitamin D-rich part of the seal. Seal blubber, the thick layer of fat under the skin, can contain 3,000 to 4,000 IU per serving. Seal liver, even higher, possibly 5,000 to 10,000 IU depending on the seal's diet and the season. We're talking about vitamin D concentrations that are off the charts compared to what you'd find in terrestrial animals, or even most fish. Whales are similar. Whale meat contains substantial vitamin D. Whale blubber, which the Inuit rendered into oil and consumed both as food and for lighting and heating, is extraordinarily rich in vitamin D. Beluga whale skin, which is considered a delicacy in Inuit cuisine and is called muktuk, contains massive amounts of vitamin D along with high levels of vitamin C, which is important because you need vitamin C to avoid scurvy, and there's essentially no vitamin C available from plants in the Arctic, so the Inuit got their vitamin C from raw or lightly cooked animal tissues where the vitamin is preserved. Ringed seal, bearded seal, harp seal, hooded seal, all species hunted by Inuit, are vitamin D powerhouses. Let me put some numbers on this to make it concrete. A traditional Inuit hunter consuming a diet heavy in seal and whale might be ingesting 5,000 to 10,000 IU of vitamin D per day, possibly more. Some estimates go even higher for individuals eating large amounts of blubber and organ meats, maybe 15,000 to 20,000 IU per day. Compare that to the modern recommended daily intake of 600 to 800 IU for adults, or the 1,000 to 2,000 IU that hunter-gatherers in northern Europe might have gotten from a mixed diet of fish and game. The Inuit were getting an order of magnitude more vitamin D from diet than any other population we've discussed. They were absolutely drowning in dietary vitamin D, consuming more than they could possibly synthesize from sun exposure, even if they had light skin and lived at the equator. Their dietary vitamin D intake was so high that UV exposure became completely irrelevant for maintaining adequate vitamin D levels. Why do marine mammals have such extraordinarily high vitamin D content compared to terrestrial animals? The answer lies in food chain biology and a phenomenon called bioaccumulation, and understanding this helps explain why the Inuit solution to the vitamin D problem was so spectacularly effective. Let's start at the bottom of the food chain and work our way up, because that's how vitamin D concentrates in marine ecosystems. At the base of the marine food web, you have phytoplankton, microscopic photosynthetic organisms floating in the ocean, including algae, diatoms, and dinoflagellates. These organisms are exposed to sunlight as they float near the water's surface, and like land plants, they have biochemical pathways that respond to UV radiation. When UV light hits certain compounds in phytoplankton, it triggers synthesis of compounds related to vitamin D. Not exactly the same as mammalian vitamin D, but chemically similar precursors. These compounds accumulate in the phytoplankton's tissues at relatively low concentrations. One phytoplankton cell doesn't contain much, but there are trillions upon trillions of phytoplankton cells in the ocean, and they're constantly being eaten by the next level of the food chain. Zooplankton, tiny animals like krill, copepods, and small jellyfish, eat phytoplankton by the millions. A single copepod might consume hundreds of phytoplankton cells per day. All those vitamin D precursors from all those phytoplankton cells accumulate in the zooplankton's tissues, concentrated into a smaller biomass. Now the vitamin D concentration is higher than it was in the phytoplankton, maybe 10 times higher, maybe more. Then small fish, herring, capelin, sand lance, eat the zooplankton. A herring might consume thousands of copepods over its lifetime. All that vitamin D concentrates again. The herring's vitamin D content is now significantly higher than the zooplankton's was. Then larger fish, cod, salmon, mackerel, eat the small fish. A salmon might eat hundreds of herring over several years. The vitamin D keeps concentrating, accumulating in the salmon's fatty tissues. Then seals eat the salmon, along with other fish. A seal might eat tens of thousands of fish over its 20-year lifespan. The vitamin D accumulates in the seal's blubber and liver, reaching concentrations that are orders of magnitude higher than what was in the original phytoplankton. And then whales eat either fish directly, toothed whales like belugas and orcas, or filter feed on krill and small fish, baleen whales like bowheads. A whale might consume tons of krill or hundreds of thousands of fish over its lifetime. The vitamin D reaches concentrations that are frankly astounding. This is bioaccumulation in action, and it's the same process that concentrates other fat-soluble compounds in marine food chains, including unfortunately some toxins like mercury and PCBS, but also beneficial compounds like omega-3 fatty acids and vitamin D. At each step up the food chain, compounds that accumulate in fat don't get metabolized or excreted efficiently, they just keep building up. By the time you reach top predators like seals and whales, you're looking at vitamin D concentrations that can be hundreds or thousands of times higher than what you'd find in terrestrial animals. Terrestrial food chains don't work the same way for vitamin D because the base of the terrestrial food chain, plants, don't synthesize vitamin D the way marine phytoplankton do. Land plants make vitamin D precursors when exposed to UV, but in much smaller amounts, and most terrestrial animals don't accumulate it to the same extent. A deer-eating plant accumulates some vitamin D from sun exposure on its skin and from the plants it eats, but nothing like the concentrations in a seal that's eating fish that ate zooplankton, that ate phytoplankton in a long bioaccumulation chain. This is why marine mammals are such uniquely rich sources of vitamin D compared to terrestrial mammals. And the Inuit, by focusing their diet on marine mammals at the very top of this food chain, were essentially harvesting the accumulated vitamin D from vast swaths of ocean ecosystem. Every seal they caught represented the vitamin D from thousands of fish, which represented the vitamin D from millions of zooplankton, which represented the vitamin D from billions of phytoplankton. They were concentrating and consuming the vitamin D production of enormous volumes of ocean. It's an incredibly efficient solution to the vitamin D problem, far more efficient than trying to synthesize vitamin D from weak Arctic sunlight. One seal could provide enough vitamin D for a family for weeks. You'd have to spend hundreds of hours in weak Arctic sun to synthesize the same amount, and during winter, you couldn't synthesize it at all, no matter how long you stayed outside. This also explains why inland Arctic peoples who didn't have access to marine food chains faced more selective pressure for light skin. Terrestrial animals like caribou, elk, and even bears don't accumulate vitamin D to anywhere near the same extent as seals and whales. A caribou's liver might have 300 to 500 EU of vitamin D per serving. Decent, certainly better than plants, but nowhere near the 5,000 to 10,000 IU you might get from seal liver. Without that bioaccumulated marine vitamin D to draw on, inland Arctic peoples had to rely more on synthesizing vitamin D from sun exposure, which created selective pressure for lighter skin to maximize whatever weak UV was available. There's a grim historical comparison that really drives home just how critical the traditional Inuit diet was for survival in the Arctic, and that's the experience of European explorers who tried to survive in Arctic regions without adopting Inuit dietary practices. The history of Arctic exploration from the 16th to early 20th centuries is littered with expeditions that ended in disaster, starvation, disease, and death, often specifically because European explorers refused to eat the way the Inuit ate. They brought their own food, salted pork, hardtack biscuits, canned vegetables, dried beans, maybe some lime juice to prevent scurvy if they were being progressive about it, and they viewed Inuit food as disgusting, primitive, barely edible. Raw seal meat? Fermented whale blubber? Seal oil? Not exactly the kind of fare you'd find in a proper British officer's mess, and many explorers would rather starve than adopt savage food practices, and starve they did. Scurvy was a constant plague on Arctic expeditions despite the fact that Inuit never got scurvy. Why? Because Inuit ate fresh raw meat and organs that contained vitamin C. Cooking destroys vitamin C, and the European habit of thoroughly cooking all meat meant they were destroying what little vitamin C was available in their food. The Inuit knew, not through formal nutritional science but through generations of practical experience, that eating raw or lightly cooked meat kept you healthy. Europeans dismissed this as barbaric and paid for their cultural prejudice with their lives and health. The Franklin expedition of 1845 searching for the Northwest Passage ended with all 129 men dead, many from scurvy and other nutritional deficiencies that could have been prevented if they'd eaten Inuit foods. But it's not just vitamin C. Europeans in the Arctic also suffered from what we can now recognise as vitamin D deficiency, though they didn't have a name for it at the time. Bone pain, muscle weakness, fatigue, symptoms that were attributed to polar anemia or mysterious Arctic diseases but were actually just severe vitamin D deficiency. They were eating salt pork and hardtack, minimal vitamin D, in an environment with no UV for half the year. The Inuit eating seal blubber next to them were fine. The Europeans suffering from mysterious illnesses were slowly dying from preventable nutritional deficiencies, and when later expeditions finally did start adopting Inuit dietary practices, eating fresh seal meat, consuming blubber, living more like the Inuit, their health improved dramatically and survival rates went up. It's almost like the people who had been living successfully in the Arctic for thousands of years knew what they were doing, and the newcomers who thought they knew better didn't. This brings us to a more modern and somewhat tragic development. What happens when Inuit populations abandon traditional diets and adopt Western dietary patterns? Because this has happened over the last century or so as Inuit communities have become more integrated into broader Canadian, American and Danish economic systems, and the health consequences have been severe. Modern Inuit communities often have access to store-bought foods, packaged carbohydrates, processed meats, soft drinks, all the standard offerings of a Western diet, and these foods are often cheaper and more convenient than traditional foods that require hunting, which requires equipment, time, skill, and increasingly expensive fuel for boats and snowmobiles. Younger generations who grew up in towns rather than traditional camps may never fully learn traditional hunting skills. The result is a dramatic shift away from traditional seal and whale-heavy diets toward Western diets heavy in carbohydrates and processed foods, and the health outcomes have been devastating. Modern Inuit populations show high rates of vitamin D deficiency despite living in the same environment their ancestors thrived in. They're not synthesizing it from sun, same UV conditions as always, meaning essentially none during winter, and they're not getting it from diet anymore if they're eating imported foods rather than seals. The result is widespread vitamin D deficiency with all its associated health problems: bone pain, muscle weakness, increased fracture risk, and in children, rickets. Yes, rickets, the same disease that plagued early European farmers, is now appearing in Inuit children who aren't eating traditional foods. It's a perfect demonstration that skin colour is not enough if you're not getting dietary vitamin D in an environment with minimal UV exposure. There are also broader health consequences. Traditional Inuit diets, while extraordinarily high in fat and cholesterol by conventional nutritional guidelines, were associated with relatively low rates of cardiovascular disease. This is sometimes called the Inuit paradox. How could a population eating 70% of their calories from fat have low heart disease rates? The answer appears to be that the fat they were eating was rich in omega-3 fatty acids from marine sources, which are protective against cardiovascular disease, and their overall diet was nutrient-dense and free of refined carbohydrates and processed foods. Modern Inuit populations eating Western diets have seen dramatic increases in obesity, diabetes, cardiovascular disease, and other metabolic disorders that were virtually unknown in traditional populations. The dietary shift has been catastrophic for public health, and this creates a real policy dilemma. How do you preserve traditional food cultures in the face of economic modernization? How do you support traditional hunting when it's increasingly expensive and when younger generations are growing up in towns rather than camps? How do you balance cultural preservation with the practical realities of modern life? These are not easy questions, and different Inuit communities are grappling with them in different ways. Some communities have programs to support traditional food sharing, where successful hunters distribute country food to elders and families who can't hunt themselves. Some communities are trying to revitalize traditional knowledge by bringing elders into schools to teach hunting skills and traditional food preparation. But the pressures of modernization are strong, and the trend overall has been away from traditional diets with serious health consequences. This completely eliminated the selective pressure for light skin. Think about how natural selection works. You only evolve lighter skin if individuals with lighter skin have a reproductive advantage over individuals with darker skin. That advantage comes from being able to synthesize more vitamin D, which leads to healthier bones, fewer pregnancy complications, more surviving children. But if you're already getting 10,000 IU of vitamin D per day from your diet, synthesizing an extra 200 or 500 IU from sun exposure doesn't matter. You're already far above the threshold for adequate vitamin D status. Dark skin isn't a disadvantage because dietary vitamin D has completely compensated for the lack of UV. There's no fitness differential between dark-skinned and light-skinned individuals. Without that fitness differential, there's no selective pressure, and without selective pressure, evolution doesn't act. Dark skin persists simply because there's no reason for it to change. In fact, you could make an argument that dark skin might have been slightly advantageous for Inuit even at high latitudes, for reasons unrelated to vitamin D. The Arctic environment has some unique UV challenges. During summer, when the sun is up 24 hours a day for weeks or months, and when there's snow and ice everywhere reflecting sunlight, UV exposure can actually be quite high despite the low angle of the sun. Snow reflects up to 80 to 90% of UV radiation, creating a double dose. You're getting hit from above by direct sunlight, and from below by reflected UV bouncing off the snow and ice. This can cause snow blindness, a painful temporary loss of vision caused by UV damage to the cornea, and it can cause severe sunburn if you're not careful. The Inuit developed snow goggles, thin slits carved in wood or bone that reduce glare and UV exposure, as a cultural adaptation. But having some melanin in your skin to provide built-in UV protection wouldn't hurt either. So dark skin might have been maintained partly through lack of selective pressure for lightning, and partly through weak selective pressure for UV protection in a high reflectivity environment. Let's compare this to other populations living at high northern latitudes to see how the pattern holds. The Sami people of northern Scandinavia, northern Norway, Sweden, Finland, and northwestern Russia live at latitudes comparable to the Inuit, roughly 65 to 70 degrees north. Historically, they practiced reindeer herding and hunting with some fishing. Their traditional diet included a lot of reindeer meat, which is lean but nutritious, along with fish from rivers and lakes, and some wild plants during summer. Reindeer meat contains vitamin D, though not as much as seal or whale, maybe 200 to 400 IU per serving depending on the cut. Fish from northern rivers, Arctic char, salmon during runs, whitefish, contains good amounts of vitamin D, maybe 400 to 600 IU per serving. So the traditional Sami diet provided significant dietary vitamin D, more than European farmers but less than Inuit. And if you look at Sami people, their skin tone is intermediate. They're noticeably lighter than Inuit, but they're somewhat darker on average than their Swedish and Norwegian farming neighbours further south. This makes perfect sense given the framework we've established. The Sami got enough dietary vitamin D from their traditional reindeer and fish diet to partially compensate for low UV, reducing the selective pressure for extremely light skin. But they didn't get as much dietary vitamin D as the Inuit, so there was still some pressure for lighter skin, and they did lighten somewhat compared to their ancient ancestors. They're not as light as Scandinavian farmers who had almost no dietary vitamin D and faced extreme selective pressure for light skin, but they're lighter than Inuit who had massive dietary vitamin D and faced essentially no selective pressure for light skin. It's a perfect gradient. Dietary vitamin D inversely correlates with skin lightening at the same latitude. Another interesting comparison comes from the indigenous peoples of coastal Alaska and eastern Siberia, groups like the Yupik, Aleut, and Chukchi. These populations are closely related to the Inuit genetically and culturally. They live at similar high northern latitudes, and they have similar traditional diets based heavily on marine mammals and fish. And guess what? They also maintained relatively dark skin for the same reason the Inuit did. High dietary vitamin D from sea mammals eliminated the selective pressure for light skin. Their skin tones are similar to Inuit, medium brown, darker than Europeans, lighter than equatorial Africans. Again, the pattern holds perfectly. If you're getting massive vitamin D from diet, your skin colour doesn't need to change to optimise UVB penetration. Now let's talk about populations that live at high latitudes but didn't have access to marine mammals, to see the other side of the equation. The indigenous peoples of northern interior regions, places far from the ocean where marine mammals weren't available, faced very different selective pressures. The Evenki people of central and eastern Siberia, for example, traditionally hunted forest animals like reindeer, elk and bear, and fished in rivers. They didn't have access to seals or whales. Their dietary vitamin D came from reindeer, fish and occasional large game. That's decent by European farming standards, but nowhere near Inuit levels. And if you look at Evenki people, they have noticeably lighter skin than coastal populations like the Chukchi, who had access to marine mammals. Not as light as Europeans, but lighter than you'd expect for populations living at 60 degrees north. The lack of marine mammal access meant more selective pressure for light skin, and they evolved somewhat lighter pigmentation as a result. This pattern repeats across Siberia and northern North America. Coastal populations with marine mammal access, relatively dark skin. Interior populations without marine mammal access, lighter skin, though not as light as Europeans because they still had some dietary vitamin D from terrestrial game and fish. It's a consistent pattern that strongly supports the dietary compensation hypothesis. Skin colour at high latitudes is determined not just by UV levels, but by dietary vitamin D availability. Culture, specifically subsistence strategies and diet, shapes the evolutionary trajectory of physical traits by modifying the selective environment. There's also an interesting temporal dimension to this story. The Inuit and their ancestors have been in the Arctic for several thousand years, but they haven't been there as long as humans have been in Europe. Modern Inuit culture, with its sophisticated marine hunting technology, only emerged around 1000 to 1500 CE, though ancestral populations with earlier versions of Arctic marine hunting have been in the region longer, maybe 4,000 to 5,000 years. Compare that to European populations, which have been at high northern latitudes for 40,000 to 50,000 years, with ancestors dealing with low UV conditions. The Inuit had less time for evolution to act, but more importantly, they entered the Arctic already equipped with a cultural toolkit, harpoons, boats, clothing, hunting strategies that allowed them to exploit marine mammals effectively. They didn't have to wait thousands of years for biological evolution to solve the vitamin D problem through lighter skin. They solved it immediately through culture by eating seals and whales. This brings up a fascinating question. What would have happened if the Inuit hadn't developed marine hunting technology? What if they'd tried to survive in the Arctic on a diet of caribou and fish, without access to seals and whales? The answer is probably that they wouldn't have survived at all, or if they did, they would have evolved much lighter skin relatively quickly due to intense selective pressure. Without the dietary vitamin D from marine mammals, the vitamin D crisis at 70 degrees north latitude would have been catastrophic. Rickets rates would have been extreme. Maternal mortality from obstructed labour would have been devastating. the population would have experienced incredibly strong selective pressure for any genetic variant that improved vitamin D synthesis, including light skin. But they never had to face that crisis because cultural innovation, the development of sophisticated marine hunting, provided a solution before biological evolution needed to act. This is actually a broader pattern in recent human evolution. As humans have become more technologically sophisticated, cultural adaptations have increasingly buffered us against environmental selective pressures that would otherwise drive biological evolution. The Inuit didn't need to evolve light skin because they had the cultural tools to hunt seals. Modern humans of all skin colours can live at any latitude because we have vitamin D supplements, fortified foods, and medical care. Humans can survive at high altitudes without evolving special hemoglobin variants because we have supplemental oxygen and medical treatments for altitude sickness. We can survive in extreme heat or cold because we have air conditioning and heating. Culture increasingly acts as a buffer against natural selection, slowing down or preventing biological evolutionary changes that would otherwise occur. But let me be clear about something. The Inuits' dark skin isn't a failure to evolve or some kind of evolutionary lag. It's not that they didn't have enough time to evolve light skin. It's that they didn't need to evolve light skin. Evolution only acts when there's selective pressure. If dark skin isn't causing reproductive disadvantage, and it wasn't because dietary vitamin D solved the problem, then there's no reason for light skin to evolve. The persistence of dark skin in Inuit populations is an elegant demonstration that evolution is responsive to the actual selective pressures organisms face, not to abstract principles about what should happen based on geography alone. And here's where the exception really does prove the rule. The Inuit case actually strengthens our understanding of why skin colour evolved the way it did in other populations. If skin colour were determined by some other factor, say temperature, or distance from Africa, or cultural preferences, or any of the other hypotheses that have been proposed over the years, then the Inuit would be a massive problem for those theories. How would you explain dark skin at the coldest inhabited latitudes on Earth if temperature determined skin colour? How would you explain populations living far from Africa retaining dark skin if distance from Africa determined skin colour? But if skin colour is specifically a response to vitamin D availability, whether from sun exposure or diet, then the Inuit fit the pattern perfectly. They have dark skin because they don't need light skin. They don't need light skin because they get adequate vitamin D from their diet. The exception proves that the rule is specifically about vitamin D, not about latitude in general. There are other interesting exceptions and variations worth mentioning. The Aboriginal Australians, for example, have dark skin despite living at relatively high southern latitudes in Tasmania, around 42 to 43 degrees south, comparable to northern Spain or southern Italy. Why didn't they evolve lighter skin? Probably because Tasmania has a maritime climate with relatively mild conditions. Outdoor lifestyles were common, and UV levels were adequate for vitamin D synthesis year-round even with dark skin. There was selective pressure to lighten somewhat. Aboriginal Tasmanians are lighter than equatorial Africans, but not enough pressure to drive the extreme lightening that occurred in northern Europe. Similarly, some Native American populations in the northern parts of South America, in high-altitude Andean regions where UV exposure is actually quite high, despite the latitude, maintained relatively dark skin. At high altitude, the atmosphere is thinner, UV radiation is more intense, and you actually need more melanin protection rather than less, even though you're further from the equator. So these populations faced competing pressures, high latitude suggesting lighter skin, but high altitude and high UV suggesting darker skin, and the result was intermediate skin tones that balance both factors. The general pattern is this: skin colour evolves to optimize vitamin D synthesis, while minimizing folate degradation and skin cancer risk in a given environment. That environment is defined by UV exposure, which depends on latitude, altitude, cloud cover, and season. But it's also defined by dietary vitamin D availability, which depends on subsistence strategies and local ecology. And it's modified by cultural factors like clothing, shelter, and time spent indoors versus outdoors. All of these factors interact to determine the optimal skin colour for a given population in a given environment. The rule isn't high latitude equals light skin. The rule is low vitamin D availability equals selective pressure for traits that improve vitamin D status, which might be light skin if diet isn't compensating, but might not be if diet is. Providing adequate vitamin D, And this, fundamentally, is why the Inuit are so important for understanding human evolution. They demonstrate that evolution is not deterministic. It's not a fixed program running on autopilot. It's a responsive process that reacts to actual selective pressures in real environments. Change the selective pressure by adding massive dietary vitamin D through marine mammal hunting, and you change the evolutionary trajectory. The same environmental conditions, extreme northern latitude, minimal UV exposure, long dark winters, produce different evolutionary outcomes in different populations depending on their cultural adaptations and subsistence strategies. The Inuit kept dark skin not because evolution failed, but because evolution had no reason to act. Their cultural solution to the vitamin D problem was so effective that it eliminated the biological problem entirely. This has implications for how we think about human diversity more broadly. Skin colour isn't some essential characteristic that defines populations in some deep, meaningful way. It's a highly plastic trait that evolved rapidly in response to local conditions, and that can be overridden by cultural adaptations when those adaptations effectively buffer against the original selective pressure. The fact that the Inuit look different from Europeans isn't because they're fundamentally different kinds of humans. It's because they face different selective pressures due to their different diets and lifestyles. Change the diet and you change the evolutionary trajectory. The variation we see in skin colour across human populations is almost entirely explicable in terms of UV exposure and vitamin D availability, with diet playing a crucial modifying role. Nothing more mysterious than that. No racial essences, no fundamental biological categories, just populations adapting to local conditions in different ways depending on their cultural toolkits. And here's one final thought experiment that really drives the point home and helps us understand just how powerful the interaction between culture and biology can be. Imagine an alternate history where the Inuit, for some catastrophic reason, abandoned marine hunting and switched to a completely different subsistence strategy. Maybe some dramatic climate change eliminated seals and whales from Arctic waters, glaciation patterns shift, ocean currents change, marine ecosystems collapse. Or maybe some cultural shift led them to adopt agriculture or intensive reindeer herding instead of marine hunting. Maybe contact with Europeans led to overhunting and depletion of seal and whale populations to the point where marine hunting was no longer viable. Whatever the mechanism, imagine Inuit populations suddenly finding themselves in the Arctic but without access to marine mammals, forced to survive on whatever they could grow during the brief Arctic summer. Hardy grains, maybe, root vegetables. Greenhouse farming, or on reindeer herding supplemented with minimal fishing. Their dietary vitamin D would plummet basically overnight in evolutionary terms. Instead of 10,000 IU per day from seal and whale, they're down to maybe 300 to 500 IU per day from occasional reindeer meat and river fish. They're eating a grain and root vegetable-based diet at 70 degrees north latitude, with essentially zero UV exposure for 6 months of the year. The selective pressure for light skin would become absolutely enormous, far more intense than what Europeans experienced because the UV conditions in the Arctic are even worse than in northern Europe. Winter darkness is longer, summer sun is weaker, UVB levels are lower year-round. Without dietary compensation, the vitamin D crisis would be catastrophic. Rickets rates would skyrocket. You'd probably see 60%, 70%, maybe 80% of children with severe bone deformities within a generation or two of the dietary shift. Maternal mortality from obstructed labour would be devastating, maybe 30 to 40% of women dying in their first childbirth attempt. The population would experience a severe bottleneck. Many families would have no surviving children. The community would be in crisis, watching their children suffer and die from preventable bone disease, completely mystified about what was happening because the change from their perspective is that they stopped hunting seals and started farming. And how could that possibly be connected to their children's twisted legs and soft skulls? But at the genetic level, natural selection would be acting with incredible intensity. Any genetic variant that improved vitamin D synthesis would provide enormous fitness advantage. Light skin alleles that might have been present at low frequencies in the population, maybe 1% or 2%, just random variation sitting in the background, would suddenly be under strong positive selection. Individuals with those alleles would have healthier children who survive to reproduce. The alleles would spread rapidly. Within maybe 50 to 100 generations, that's 1,250 to 2,500 years at 25 years per generation, you'd probably see light skin alleles go from rare to common, or even fixed in the population. And I'd bet you'd see evolution towards skin that's even lighter than modern Scandinavians, because the selective pressure at 70 degrees north on a grain-based diet would be more extreme than at 60 degrees north. You might see evolution toward the palest possible human skin tones, maybe albino light if the selective pressure was intense enough, and if albino genes didn't have other deleterious effects. The population would transform from medium brown-skinned to pale white-skinned in just a few thousand years, driven entirely by the dietary shift that removed their vitamin D supply. Of course, the population might not survive long enough for this evolution to happen. If 70 to 80% of children have rickets, and 30 to 40% of women die in childbirth, your population is shrinking fast. You're losing people faster than you're replacing them. The community might collapse entirely before evolution can rescue them. Or they might figure out some other solution, rediscover marine hunting, trade for fish with coastal groups, migrate to lower latitudes where UV is better. But if they stayed put and survived as a population, evolution would definitely act, and the endpoint would be very light skin. This thought experiment illustrates something crucial about human evolution. Skin color is not some deep essential characteristic tied to ethnic or racial identity. It's a plastic trait that responds to environmental conditions. The same population, same genetic ancestry, same cultural heritage, same language and traditions can evolve dramatically different appearances depending on what selective pressures they face. And those selective pressures are determined not just by geography but by culture. What you eat, how you live, what technologies you use, all of these factors shape the evolutionary environment in which your genes are being filtered by natural selection. Change the culture, and you change the trajectory of biological evolution. The Inuit stayed dark-skinned because their culture provided a solution to the vitamin D problem. If that cultural solution had failed or been lost, biological evolution would have kicked in and solved the problem genetically through lighter skin. One way or another, evolution finds solutions to survival problems. But which solution gets implemented depends on what's available, and cultural solutions can outcompete biological ones if they're sufficiently effective. This also helps us understand the modern human condition, where rapid cultural change has completely outpaced biological evolution. We're living in environments our bodies aren't evolved for, eating foods we're not adapted to, following lifestyles that create selective pressures our genes haven't caught up with. Light-skinned Europeans living in Australia getting skin cancer, because their pale skin evolved for northern latitudes but they're now in high UV environments. Dark-skinned Africans living in Scandinavia getting vitamin D deficiency, because their dark skin evolved for equatorial sun but they're now in low UV environments. People of all backgrounds eating industrial diets heavy in refined carbohydrates and developing metabolic diseases their ancestors never faced. These are all examples of evolutionary mismatch, organisms living in conditions their biology isn't adapted to. But unlike our ancestors, we have technological solutions. We can take vitamin D supplements to compensate for dark skin in low UV environments. We can use sunscreen to protect light skin in high UV environments. We can modify our diets to avoid metabolic disease. We can use medical interventions to solve health problems that would have killed our ancestors. Culture buffers us against natural selection more comprehensively than ever before, which means human biological evolution has probably slowed down dramatically in the last few centuries and will continue to slow as technology advances. We're not going to evolve new adaptations to modern life. We're going to engineer solutions to modern problems. The Inuit solution, solve vitamin D with culture rather than genetics, is becoming the human solution more broadly. We're increasingly using cultural and technological adaptations to override biological limitations rather than waiting for biological evolution to catch up. But the Inuit story remains important because it shows us what's possible. It demonstrates that humans have always been creative problem solvers, using whatever tools are available, cultural or biological, to adapt to challenging environments. It reminds us that human diversity is not about fundamental differences in capability or worth, but about different populations solving similar problems in different ways depending on their circumstances. And it provides a perfect case study in how evolution actually works, opportunistically, pragmatically, using whatever variation happens to be available to solve whatever problems organisms face in their specific environments. The Inuit didn't need light skin because they had seals. Europeans needed light skin because they had wheat. Same problem, different solutions, both effective, neither superior to the other. Just populations adapting to their conditions in whatever way worked, driven by the simple, inexorable logic of natural selection, filtering genetic and cultural variation through the harsh sieve of survival and reproduction. So when you look at a map of global human skin color variation, and you notice that most populations at high latitudes have light skin but the Inuit and some other Arctic populations don't, you're not seeing some mysterious exception to the rules of evolution. You're seeing evolution working exactly as it should, responding to the specific selective pressures that each population faced in their particular environmental and cultural context. The Inuit solved the vitamin D problem with seals and whales. Europeans solved it with genetic mutations for light skin. Both solutions work. Both are products of evolution, biological evolution in one case, cultural evolution in the other. And both demonstrate the same underlying principle. Organisms adapt to their environments, and sometimes the most effective adaptation is a good dinner. So we've spent considerable time discussing skin colour, how it evolved, why it evolved, what selective pressures drove the changes. But skin colour wasn't the only aspect of human appearance that changed as populations moved into northern latitudes and adapted to new environments. If you look at a modern northern European, say, someone from Sweden or Denmark or northern Germany, you're not just seeing light skin. You're potentially seeing blue or green eyes, blonde or red hair, relatively narrow noses, stockier body proportions, and various other features that differ from what you'd see in equatorial African populations. Some of these changes were driven by the same selective pressures that produce light skin. Others evolved for completely different reasons. And some may have spread not because they provided survival advantages at all, but because people found them attractive, sexual selection rather than natural selection. Let's unpack this, because the genetics of human appearance are fascinatingly complex and not always intuitive. Let's start with eye colour, because blue eyes are one of the most striking visible differences between northern European populations and most other human groups, and the genetics tell a remarkable story. The default human eye colour, the ancestral condition, what everyone had before any mutations changed things, is brown, dark brown specifically. This is because the iris, the coloured part of your eye, naturally accumulates melanin pigment just like skin does. Melanin in the iris appears brown, and the more melanin you have, the darker brown your eyes look. Everyone in Africa 300,000 years ago had brown eyes. Everyone who migrated out of Africa initially had brown eyes. Brown eyes were universal in humans for the vast majority of our species' existence. Blue eyes, green eyes, hazel eyes, all of these are relatively recent innovations caused by mutations that reduce the amount of melanin in the iris. And here's what's remarkable. Blue eyes appear to have originated from a single mutation in a single individual who lived somewhere around the Black Sea region, possibly in what's now Ukraine, southern Russia, or nearby areas, somewhere between 6,000 and 10,000 years ago. One person, one mutation, and from that single individual, the blue eye trait spread across Europe and is now present in maybe 20 to 40% of European-descended populations, with particularly high frequencies in Scandinavia and the Baltic region where blue eyes can be found in 70 to 80% of the population. The mutation is in a gene called OCA2, oculocutaneous albinism type 2, which codes for a protein involved in melanin production. But here's where it gets technically interesting. The specific mutation that causes blue eyes isn't actually in the OCA2 gene itself. It's in a nearby regulatory region, in what's called an intron of a completely different gene, HERC2, that happens to regulate OCA2 expression. This regulatory region acts like a dimmer switch for the OCA2 gene specifically in the iris. The mutation essentially turns down the production of OCA2 protein in melanocytes within the iris tissue, without affecting OCA2 production in other parts of the body like skin melanocytes or hair follicles. It's an exquisitely specific genetic tweak. Reduce melanin in the iris, leave everything else alone. Less OCA2 protein in iris. Melanocytes means less melanin gets deposited in the iris tissue during development. Less melanin in the iris means the iris appears blue rather than brown. And here's something most people don't realize. The blue color isn't from blue pigment. There's no blue pigment in blue eyes, no blue molecules, nothing actually blue at the molecular level. It's a structural color caused by light scattering off the collagen fibers in the iris stroma, when there's minimal melanin to absorb the incoming light. It's the same physical phenomenon that makes the sky appear blue, called Rayleigh scattering, where shorter wavelengths of light, blue, scatter more than longer wavelengths, red. So when white light hits the iris, the blue wavelengths scatter back toward the observer, while the red wavelengths pass through or get absorbed by whatever minimal melanin is present. This is why blue eyes can appear to change shade in different lighting conditions. The underlying structure is the same, but different lighting conditions produce different scattering patterns. And here's another fascinating detail. All blue-eyed people appear to share the exact same mutation in the exact same position in their genome. When geneticists analysed the DNA of hundreds of blue-eyed individuals from different countries, they found that the blue eye mutation is identical in all of them, and the genetic regions surrounding it show remarkably low diversity, which is the signature of a recent selective sweep from a single origin. This means all blue-eyed people alive today, whether they're in Scandinavia, Britain, Germany, Russia, or anywhere else, are descended from a single individual who lived around 6,000 to 10,000 years ago, somewhere near the Black Sea region. One person, one mutation, one family line that spread that mutation across Europe, and now billions of people carry it. That's extraordinary when you think about it. Blue eyes went from 0 to 20 to 40% frequency across Europe in maybe 400 generations. That's incredibly rapid spread. Now here's the interesting question that's puzzled evolutionary biologists. Why did this mutation spread so fast? Blue eyes don't provide any obvious survival advantage. They don't help you see better. If anything, they might slightly reduce visual acuity in very bright conditions because there's less melanin to absorb excess light entering the eye, though the effect is minimal and largely compensated by pupil constriction. They don't protect against UV damage to the eye any better than brown eyes. In fact, lighter eyes may be slightly more vulnerable to UV damage, though again the effect is small because most UV is blocked by the lens and cornea before reaching the iris. Anyway, and everyone should be wearing UV-protecting sunglasses in bright sun regardless of eye colour. There's no vitamin D connection. Eye melanin has nothing to do with vitamin D synthesis, which happens in skin tissue, not eye tissue. There's no clear connection to any disease resistance or metabolic advantage. So why would a mutation that just changes iris colour, with no apparent survival benefit, spread from near zero frequency to high frequency in thousands of years? The most likely explanation, which has become almost consensus among evolutionary biologists studying this, is sexual selection. Mate choice based on physical appearance. People with blue eyes were considered attractive, unusual, desirable as potential mates. Maybe the novelty of blue eyes made individuals stand out in populations where everyone had brown eyes, catching the eye, pun intended, of potential partners. Maybe there was some cultural association between blue eyes and positive traits. Perhaps blue eyes were seen as signs of health, youth, divine favour, or some other desirable quality. Maybe it was purely aesthetic preference with no deeper meaning. People just liked the way blue eyes looked. Or maybe it started with one powerful or charismatic individual or family who happened to have blue eyes, and through social dynamics, preferential mating, and possibly even political marriages among elite families, the trait spread through the population. Sexual selection can drive extraordinarily rapid changes in appearance when mate choice is influenced by visual traits, even when those traits provide no survival advantage whatsoever, and may even be slightly disadvantageous. The classic example in evolutionary biology is the peacock's tail, massively expensive to grow and maintain, requiring enormous caloric investment, actively harmful for escaping predators. Try flying quickly with a 3-foot train of feathers, dragging behind you. And yet peacock tails exist and are elaborately decorated because peahens prefer males with impressive tails. The male peacock pays a survival cost to grow that tail, but he gains a reproductive benefit because females choose him as a mate, and the reproductive benefit outweighs the survival cost. The same logic could apply to blue eyes in humans. Maybe they conferred some slight survival disadvantage in bright Arctic summers, with high UV reflection off snow. But if blue-eyed individuals had greater reproductive success because people found them attractive and chose them as mates, the trait would spread despite the survival cost. There's also a fascinating social dynamic that might have amplified sexual selection for blue eyes, assortative mating. Once blue eyes became somewhat common in a population, People with blue eyes might have preferentially mated with other blue-eyed individuals, either because they found blue eyes attractive or because blue eyes became associated with particular social groups or classes. Since blue eyes are largely recessive, you need 2 copies of the blue eye allele to have blue eyes. Assortative mating would increase the frequency of blue eyes more rapidly than random mating. If blue-eyed people consistently choose other blue-eyed partners, you get clustering of blue eye alleles in family lines, and the trait spreads faster through the population. And here's another wrinkle worth considering. The timing and geography of blue eye spread correlates interestingly with the spread of agriculture into Europe. Blue eyes appear to have originated somewhere around the Black Sea region, right around the time that farming was spreading into Europe from the Fertile Crescent. Early European farmers might have been the population where blue eyes spread most rapidly. Why would farmers show stronger sexual selection for eye colour than hunter-gatherers? Possibly because farming communities were larger, denser, had more social stratification and complexity, and had more potential mates to choose from, all of which could amplify the effects of sexual selection on visible traits. In a hunter-gatherer band of 30 to 50 people, your mate choice is limited by who's available and roughly your age. In a farming village of 200 to 500 people, you have more choice, social status matters more, and physical appearance might play a bigger role in mate selection. This is speculative, but it's at least plausible that the larger social groups and more complex social dynamics of farming populations accelerated the spread of sexually selected traits like blue eyes. Green eyes and hazel eyes work similarly. They're caused by different mutations that reduce melanin in the iris to varying degrees. Green eyes have more melanin than blue eyes, but less than brown eyes, creating an intermediate appearance. Hazel eyes have even more melanin, often with patches of different pigmentation creating a multicoloured appearance. These colours also appear to have originated relatively recently, within the last 10,000 years or so, and they're most common in European populations, though they occur at low frequencies in other populations too. The genetics are more complex than blue eyes, multiple genes are involved and the inheritance patterns are messier, but the basic story is the same. Mutations reducing iris melanin spread through European populations, probably through sexual selection. Now let's talk about hair colour, because blonde hair and red hair follow a similar pattern and may have spread for similar reasons. The ancestral human hair colour is black, dark black hair packed with eumelanin, the dark brown-black form of melanin. Everyone in Africa had black hair. Early migrants to Europe had black hair. Black hair remained universal, or nearly universal in human populations until relatively recently, within the last 10,000 to 20,000 years for blonde hair, possibly even more recently for red hair in its current distribution. Blonde hair is caused by mutations that reduce eumelanin production in hair follicles without completely eliminating it. There are multiple genes involved. Geneticists have identified at least 20 to 30 genetic variants across more than a dozen genes that contribute to blonde hair. But some of the major players are familiar from our skin colour discussion. Genes like SLC24A5, TYR, TYRP1, and OCA2 all affect melanin production in hair follicles as well as skin melanocytes. This makes perfect biological sense when you understand that hair colour and skin colour both depend on the same fundamental melanin synthesis pathways operating in different cell types. Hair follicles contain specialized melanocytes that produce melanin and transfer it to growing hair cells. These melanocytes use essentially the same genetic machinery as skin melanocytes. So mutations that affect melanin production in one cell type often affect it in others. This is why you see strong correlations between skin color and hair color across populations. Very light-skinned people usually have light hair, blonde, light brown, or red. Very dark-skinned people usually have very dark hair, black or very dark brown. It's not a perfect correlation. You can find light-skinned people with dark hair, particularly in southern Europe and the Middle East, where populations have intermediate skin tones, but the trend is clear. The genes are linked because they're working through the same biochemical pathways. If you have genetic variants that reduce overall melanin production, both your skin and your hair end up lighter. If you have variants that increase melanin production, both end up darker. But here's where it gets interesting from an evolutionary perspective. Blonde hair doesn't provide any obvious survival advantage that we can identify. It doesn't keep you warmer in cold climates. Hair provides insulation regardless of colour, and melanin content doesn't significantly affect hair's thermal properties. If anything, having less melanin in your hair might make your scalp slightly more vulnerable to UV damage from sun exposure, though this effect would be minimal since hair itself provides the primary protection, and most people's scalps aren't exposed to sustained direct sunlight. There's definitely no vitamin D connection. Hair doesn't synthesize vitamin D. That happens in skin tissue below the hair follicles. There's no obvious connection to disease resistance or metabolic advantages. So why did blonde hair spread to relatively high frequencies in northern European populations? Maybe 30 to 40% of Scandinavians have naturally blonde hair as children, though many darken to medium or light brown as adults, which is its own interesting phenomenon related to melanin production changes during puberty. The explanation probably involves multiple factors working together. First, genetic hitchhiking. If you're already under strong selection for light skin because of vitamin D advantages, and many of the same genetic variants that produce light skin also tend to produce lighter hair as a pleiotropic effect, meaning one gene affecting multiple traits, then lighter hair comes along for the ride automatically. You're not selecting for blonde hair directly, you're selecting for light skin, but blonde hair genes get pulled along because they're genetically correlated with light skin genes. This is called genetic hitchhiking, or linkage disequilibrium, and it's a powerful force in evolution. Neutral or even slightly deleterious traits can spread if they're genetically linked to beneficial traits under strong selection. Second, sexual selection might have favoured blonde hair independently of any connection to light skin. Maybe blonde hair was considered attractive in northern European populations. Maybe it was seen as distinctive, youthful, beautiful, desirable. There's actually some evidence that lighter hair colour is associated with youth. Children often have lighter hair than adults in populations where blonde hair is common, and hair tends to darken during puberty and young adulthood as melanin production increases. So blonde hair might have been unconsciously associated with youthfulness, and if youthful appearance was considered attractive, which seems to be fairly universal across human cultures, then sexual selection could favour retention of blonde hair into adulthood. This is speculative, but it's biologically plausible. Third, founder effects and genetic drift might have played a role. Northern Europe went through some dramatic population bottlenecks during and after the last ice age. Ice sheets covered Scandinavia, the Baltic, northern Britain. Human populations had to retreat south during glacial maxima, then recolonize northern regions during warmer periods. These repeated cycles of population decline and expansion create opportunities for random genetic drift to push trait frequencies around. If blonde hair genes happen to be more common in the small populations that recolonized Scandinavia after the ice retreated, they could have reached high frequency just by chance in that founder population. Then, as that population expanded, the high blonde hair frequency persisted. Red hair is even more fascinating and mysterious because it's rarer and has more concentrated geographic distribution than blonde hair. Natural red hair, we're talking vibrant ginger, copper, auburn, not just reddish-brown, is caused primarily by mutations in the MC1R gene, melanocortin-1 receptor, which plays a crucial role in melanin synthesis. MC1R is a receptor protein on the surface of melanocytes, and it responds to hormonal signals from the pituitary gland that tell melanocytes whether to produce eumelanin, dark brown-black pigment, or pheomelanin, red-yellow pigment. When MC1R is functioning normally, it promotes eumelanin synthesis. When MC1R is impaired by certain mutations, melanocytes default to producing mostly pheomelanin instead. The result is red or reddish-orange hair. But MC1R mutations don't just affect hair colour, they also affect skin. People with red hair variants of MC1R typically have very pale skin that burns easily and tans poorly, and they often have freckles. The freckles are actually patches where melanocytes are producing small amounts of eumelanin in response to sun exposure, creating islands of darker pigmentation against the pale pheomelanin-based background skin tone. Red-haired individuals often have the palest skin of any human population, and they're particularly vulnerable to sunburn and skin cancer due to their minimal eumelanin production. From an evolutionary perspective, this seems like it should be disadvantageous. Pale skin with poor tanning ability in environments that still get some UV exposure during summer should increase skin cancer risk. So why does red hair persist at relatively high frequencies in certain populations? Red hair is most common in populations from the British Isles, particularly Scotland and Ireland, where maybe 10 to 13% of people have natural red hair, and it's also found at lower frequencies in other parts of Northern Europe, maybe 2 to 4% in Scandinavia, England and Northern Germany. Outside of European populations, it's extremely rare, less than 0.5% globally. Why such concentrated geographic distribution in the British Isles specifically? Several factors probably contributed. First, the British Isles have particularly low UV exposure due to being islands in the North Atlantic, with persistent cloud cover and high latitude. We talked earlier about how Britain's maritime climate creates constant cloudiness that limits UV even during summer. In that extreme low UV environment, the vitamin D advantage of very pale skin might have outweighed the skin cancer disadvantage. Remember, skin cancer typically doesn't kill you until after reproductive age, so from natural selection's perspective, it's not as important as reproductive success. If red-haired, pale-skinned women could synthesize vitamin D more efficiently in Britain's weak, cloud-filtered sunlight, they might have had better bone health, healthier pregnancies, and higher reproductive success despite increased skin cancer. Risk later in life. Second, founder effects probably played a major role. The British Isles were relatively isolated after the last ice age. They were connected to mainland Europe by a land bridge that eventually flooded as sea levels rose, creating the English Channel and North Sea. Island populations tend to accumulate unusual genetic variants at higher frequencies than mainland populations due to isolation and small population sizes. If MC1R red hair variants happen to be carried by early settlers of Ireland and Scotland, those variants could have reached unusually high frequency just through genetic drift in small, isolated populations. Third, sexual selection might have favoured red hair specifically in Celtic cultures. Red hair is extraordinarily visually striking. It's rare enough to be distinctive, but common enough in these populations to not be completely alien. Various Celtic myths and legends feature red-haired heroes and heroines, suggesting that red hair might have been considered attractive or associated with positive traits like courage, passion, or divine favour. If red-haired individuals were seen as desirable mates, sexual selection could have maintained or even increased red hair frequency, despite any survival disadvantages from sun sensitivity. Fourth, and this is more speculative, there might be some other selective advantage to red hair variants that we haven't identified yet. Some studies have suggested that people with red hair variants might have different pain sensitivity, different responses to anesthetics, or different immune system functioning compared to people with other hair colours. If any of these differences provided advantages in the British Isles' specific environment, perhaps resistance to certain diseases, or some metabolic advantage we don't understand yet, that could explain why red hair persists at such high frequency, despite the apparent disadvantages of extreme sun sensitivity. Now let's shift gears and talk about other physical features that evolved in response to northern climates, because skin and hair and eye colour are just the beginning. Body proportions, facial features, and overall physique also adapted to cold conditions, and these adaptations follow predictable patterns that you can see across multiple human populations and even across different mammal species living in cold climates. There's a principle in biology called Bergmann's rule, named after 19th century German biologist Carl Bergmann, who first described the pattern, which observes that within a species, populations living in colder climates tend to have larger body sizes than populations in warmer climates. The reason is straightforward physics and geometry. Larger bodies have lower surface area to volume ratios compared to smaller bodies, which means less surface area per unit of body mass through which heat can escape to the environment. A big spherical object loses heat more slowly than a small spherical object, all else being equal, because the volume, which generates heat through metabolism, increases with the cube of the radius, while the surface area, which loses heat to the environment, only increases with the square of the radius. So as you scale up, you get proportionally less surface area per unit of volume, which means better heat retention. In cold climates where maintaining body temperature is a constant challenge and heat loss can be fatal, bigger bodies are advantageous. You generate more metabolic heat in absolute terms because you have more tissue, and you lose that heat more slowly because your surface area to volume ratio is lower. This is why polar bears are huge compared to sun bears from tropical forests, why Arctic foxes are larger than desert kit foxes, and why emperor penguins in Antarctica are much larger than African penguins from temperate South Africa. And you can see the same pattern in human populations. Northern Europeans tend to be taller and heavier on average than equatorial Africans. Inuit tend to be stockier than Polynesian islanders, and the pattern holds even accounting for nutritional and environmental factors. Some of this difference is genetic. Populations living in cold climates for thousands of generations have evolved toward larger average body size. Conversely, in hot climates where dissipating excess metabolic heat is the challenge, smaller bodies are advantageous. You have higher surface area to volume ratio, which means more surface through which to lose heat, and you generate less absolute metabolic heat because you have less tissue. This is why people from tropical regions often have more slender builds. It's an adaptation for heat dissipation. The pattern isn't absolute, and there's lots of variation within populations, but the trend is real and measurable. Statistical studies looking at average height and weight across human populations show significant correlations with average environmental temperature, with colder climates associated with larger body size. There's a related biogeographic principle called Allen's rule, named after American zoologist Joel Allen, which observes that within a species, populations in colder climates tend to have shorter limbs and appendages relative to their body size, compared to populations in warmer climates. Again, this is about surface area and heat conservation. Your limbs, arms, legs, hands, feet, fingers, toes, are basically cylinders or cones extending from your core, and these shapes have high surface area to volume ratios. They're heat radiators. Every inch of arm or leg is surface area losing heat to the environment without contributing proportionally to metabolic heat generation. In cold climates, long exposed limbs are a liability. They lose heat rapidly, and in extreme cold they're vulnerable to frostbite. Shorter, stockier limbs relative to body size reduce total surface area and keep the limbs closer to the warm body core, reducing heat loss. In hot climates, the opposite is true. Long, thin limbs increase surface area for heat dissipation without adding much metabolic heat generation. They're heat radiators working in reverse, helping you cool down rather than trying to conserve heat. And you can see this pattern dramatically in human populations. Compare Inuit body proportions, very short, stocky build with short limbs, relatively short fingers and toes, everything compact and close to the core, with Nilotic peoples from Sudan and Ethiopia, very tall and slender with extremely long limbs, elongated legs, long fingers, maximizing surface area for heat dissipation. These are adaptations to opposite thermal environments, cold versus hot, and they're strikingly different in appearance. The ratio between limb length and torso length is actually quantifiable and shows strong geographic patterns. Scientists use measurements like the crural index, ratio of lower leg length to thigh length, and brachial index, ratio of forearm length to upper arm length, to characterize body proportions. Populations from hot climates have high values for these indices: long lower legs relative to thighs, long forearms relative to upper arms. Populations from cold climates have low values, shorter extremities relative to more proximal segments. The pattern is so consistent that anthropologists can make reasonable inferences about the climate a population's ancestors lived in just by measuring skeletal proportions. Find a skeleton with very long legs and high crural index, probably from a hot climate population. Find one with short, stocky proportions and low crural index, probably from a cold climate population. And these aren't trivial differences. Studies have shown that the heat loss difference between cold-adapted and heat-adapted body proportions can be 10 to 15% under extreme conditions. That's significant when you're trying to maintain core body temperature in minus 40-degree conditions, or trying to dissipate heat in plus 40-degree conditions. It's the difference between comfortable survival and hypothermia or heat stroke. Natural selection has been working on these body proportions for tens of thousands of years, fine-tuning populations to their local thermal environments. Facial features also adapted to cold climates in ways that are functional rather than merely aesthetic, and one of the most notable adaptations is nose shape. If you look at populations from different climates, you'll notice distinct patterns. People from cold, dry climates tend to have narrower, more projecting noses with higher nasal bridges. Think of the stereotypical Northern European nose, Russian nose, or Central Asian nose. People from hot, humid climates tend to have broader, flatter noses with lower nasal bridges. Think of the stereotypical West African nose, Southeast Asian nose, or Melanesian nose. This isn't random aesthetic variation, and it's not just cultural preferences being expressed. It's functional adaptation to air conditioning, not the mechanical kind with compressors and refrigerants, unfortunately for our ancestors who had to manage with biological systems, but the biological air conditioning that happens in your nasal passages every time you breathe. When you breathe air through your nose, that air needs to be processed before it reaches your lungs. Your lungs are delicate tissues lined with thin membranes optimized for gas exchange. They need air to be at body temperature, 37 degrees Celsius, 98.6 degrees Fahrenheit, and saturated with moisture, 100% relative humidity. If you breathe cold, dry air directly into your lungs without processing it, you damage the lung tissue, reduce oxygen absorption efficiency, lose excessive moisture through evaporation from lung surfaces, and generally make breathing much less efficient and much more uncomfortable. So your nasal passages do critical pre-processing. They warm the air through contact with warm, blood-rich nasal mucosa lining the passages, and they humidify it through evaporation from the mucous membranes. By the time air exits your nasal passages and enters your trachea, it should be close to body temperature and nearly saturated with moisture. A longer, narrower nasal passage provides more surface area for this warming and humidifying to occur. The air has to travel further through warm, moist tissue before reaching your lungs, spending more time in contact with the nasal mucosa, picking up more heat and moisture through extended contact. The turbinates, curled bones inside your nasal cavity lined with mucous membranes, increase surface area even further, creating a maze-like path that maximizes air-tissue contact time. This is why narrow projecting noses are advantageous in cold, dry climates. They're more efficient air conditioners, bringing Arctic air closer to body temperature and adequate humidity before it hits your lungs. Conversely, in hot, humid climates, the air is already warm and humid when you breathe it in. You don't need much warming or humidifying. The air is already at or near the ideal temperature and moisture level for your lungs. What you might actually want is some cooling, some heat dissipation through respiratory evaporation. Broader, shorter nasal passages move air more quickly with less surface contact, which is fine when the incoming air doesn't need much conditioning. Less tissue contact means less resistance to airflow, which might actually improve breathing efficiency when you're exercising in hot conditions and need to move lots of air quickly. So broader noses make functional sense in tropical climates where the air conditioning problem is minimal or reversed. The correlation between nose shape and climate is one of the strongest and most consistent patterns in human physical anthropology. Studies measuring nasal dimensions across hundreds of populations worldwide show clear relationships. Nasal width decreases and nasal projection increases as you move toward colder, drier climates, and the correlation holds even after controlling for genetic ancestry and population history. This strongly suggests that nose shape is under direct selection by climate, rather than just being neutral variation that happened to cluster geographically by chance. The really fascinating thing about all of these body proportion and facial feature adaptations is that they evolved independently in different populations facing similar climatic conditions. Northern Europeans evolved narrow noses, stocky builds, and short limbs in response to cold climates. Northern Asians, Mongolians, Siberians, Northern Chinese, Tibetans evolved remarkably similar features in response to remarkably similar cold, dry conditions. But when geneticists look at the underlying genes responsible for these traits, they find that Europeans and Asians achieved these adaptations through different genetic mutations in different genes. Just like the skin color convergence we discussed earlier, where Europeans and East Asians evolved light skin through different mutations in different genes, Europeans and East Asians also evolved cold-adapted body proportions and facial features through different genetic routes. Different populations, same selective pressures, similar outcomes, but achieved through different molecular mechanisms. It's convergent evolution operating on multiple traits simultaneously across the entire phenotype. And here's something worth emphasizing about the magnitude of these adaptations. The physical differences we're talking about, body proportions, nose shape, limb length, are all relatively subtle in their functional impact compared to the dramatic life or death consequences of getting skin color wrong in a given UV environment. If you measured the actual functional difference between a narrow European nose and a broad African nose in terms of air warming and humidifying efficiency under extreme cold conditions, you'd find maybe 10 to 20% difference in performance. That's measurable, it's real, it does affect comfort and potentially respiratory health in extreme cold, but it's not catastrophic. You can survive with a broad nose in Siberia. It's not optimal. You'll have colder air hitting your lungs in winter. You might be more prone to respiratory infections, but it's not immediately fatal. Similarly, the heat retention advantage of stockier builds versus slender builds is measurable but modest, maybe 5 to 10% difference in heat loss rate under cold conditions. That makes a difference over hours and days of cold exposure, and it could be the difference between comfortable survival and hypothermia in extreme situations, but it's not the same order of magnitude as the vitamin D crisis created by dark skin in northern latitudes. Rickets killed or disabled huge percentages of children. Deformed pelvises killed women in childbirth. The selective pressure was enormous and immediate. Body proportions and nose shape provided advantages but not absolute requirements for survival, so you see more variation within populations and less clear-cut geographic patterning compared to skin colour. Skin colour had to optimise for vitamin D, mess that up and you die or fail to reproduce. Body proportions and nose shape provide advantages but not existential requirements, so you see more variation and less intense selection. This is why these traits show more overlap between populations and more individual variation within populations than skin colour does. You can find stocky builds in tropical Africa and slender builds in northern Europe because these traits aren't under life or death selective pressure the way skin colour was. They're under weak to moderate selection that produces tendencies and averages but allows for lots of individual variation. And this is actually fortunate from an evolutionary perspective because it means populations can adapt relatively quickly to new thermal environments if they migrate. The genetic variation is already present within populations, it just needs to shift in frequency through selection. A population moving from Africa to Europe doesn't need brand new mutations for cold adaptation to body proportions. They likely already have some individuals with slightly stockier builds, and those individuals will have slightly higher fitness in the cold environment, and over many generations the population average shifts. There are also some other cold climate adaptations that are less visible but equally interesting. Populations living in extreme cold environments tend to have higher basal metabolic rates. They burn more calories at rest just to maintain body temperature. This makes sense. If you're constantly losing heat to a cold environment, you need to generate more heat metabolically to compensate. Inuit populations, for example, have been shown to have metabolic rates 10 to 20% higher than you'd expect based on body size alone. That means they need to consume more calories, which they got from their fat-rich seal and whale diet. But it also means they can maintain body temperature more effectively in extreme cold. Some cold-adapted populations also have genetic adaptations related to fat metabolism and distribution. Brown adipose tissue, brown fat, is specialized tissue that generates heat directly through metabolic activity, rather than just providing insulation like white fat. Babies are born with substantial brown fat to help them regulate temperature, but adults lose most of it. However, some cold-adapted populations appear to retain more brown fat into adulthood, or have more active brown fat compared to populations from warmer climates. The genetics are still being worked out, but there are hints that genes involved in brown fat activity show different variants in cold-adapted populations. Blood circulation adaptations are another fascinating area. People adapted to cold climates show enhanced vasoconstriction responses, the ability to restrict blood flow to extremities to preserve core body temperature, and also better ability to periodically dilate blood vessels in fingers and toes to prevent frostbite. This is sometimes called the Hunter's response or Lewis wave, where blood flow to fingers alternates between constriction to save heat and dilation to prevent tissue damage from cold, creating a wave-like pattern. Inuit and Sami populations show stronger and more frequent Lewis waves compared to people from temperate climates, suggesting genetic adaptation. Even immune system adaptations may be related to climate. Cold climates have different disease ecology than tropical climates, different pathogens, different infection risks, different immune challenges. Some studies have found that populations from different climates show different frequencies of immune system gene variants, possibly reflecting adaptation to local disease environments. This is still an active area of research, but it's plausible that moving from tropical Africa to glacial Europe involved adapting not just to cold and low UV, but also to a completely different set of infectious diseases. Now let's talk about a slightly uncomfortable topic: the genetic diversity and evolution of other physical features that we often use to categorize people into racial groups. Features like skull shape, jaw structure, tooth morphology, and so on. The traditional approach to physical anthropology in the 19th and early 20th centuries was to measure these features obsessively and use them to create elaborate racial classification schemes. This approach was deeply flawed, often racist in its assumptions and applications, and modern genetics has largely demolished the idea that these measurements define distinct biological races. But the features themselves are real. They do vary across populations, and they did evolve in response to various selective pressures and demographic processes. We can study them scientifically without endorsing the racist classification schemes of the past. Skull shape, for example, shows geographic variation. Populations from East Asia tend to have flatter facial profiles compared to Europeans, who tend to have more projecting midfaces. Populations from sub-Saharan Africa show more prognathism, forward projection of the jaw, compared to European or Asian populations. These differences are quantifiable and have genetic bases. But here's the crucial point. They're not discrete categories, they're continuous variation. If you measure skull shape across all human populations, you don't find clear boundaries separating races. You find gradients, with populations blending into each other geographically. An individual from northern China looks more similar to someone from Mongolia than to someone from southern China, who looks more similar to someone from Southeast Asia, who looks more similar to someone from southern India, and so on. There are no sharp divisions, just gradual change across geography. Moreover, different features don't covary perfectly. Someone might have skull proportions typical of one population, but skin colour typical of another, and hair texture typical of a third. This happens all the time, especially in populations with mixed ancestry, and it demonstrates that these features evolve independently and are controlled by different genes. The 19th century racial anthropologists wanted to believe that all physical features clustered together into neat packages, that someone with African skin would have African skull shape, hair texture, etc. But genetics shows this isn't true. Different features are controlled by different genes that can be inherited independently and that respond to different selective pressures. You can be dark-skinned with straight hair, light-skinned with tightly curled hair, have European skull proportions with Asian eye features. Any combination is genetically possible because the traits aren't locked together. This brings us back to the broader theme that's run through this entire discussion of human physical variation. Humans are one species with relatively recent common ancestry, and the visible differences between populations reflect local adaptations to different environments operating on a small subset of our genes over relatively short timescales. We share 99.9% of our DNA with every other human regardless of what we look like. The 0.1% that varies includes the genes controlling skin colour, eye colour, hair texture, body proportions, facial features, and other visible traits that we use to categorize people. But that 0.1% is superficial in both the literal sense. Most of it affects surface features of appearance, and in the evolutionary sense, it represents recent local adaptations that don't reflect deep differences in biology. And here's maybe the most important point. The visible features that humans instinctively use to categorize each other into groups, skin color primarily, but also hair texture, eye shape, nose shape, and so on, are terrible markers for genetic relationship and shared ancestry. Two people can look very similar but be only distantly related genetically. Two people can look quite different but be closely related genetically. Physical appearance is not a reliable guide to underlying genetic similarity. This is because the genes controlling visible appearance have been under strong recent selection in response to local environments, which means they've been changing rapidly and can differ dramatically between populations. Meanwhile, the vast majority of your genome, the genes coding for your immune system, your metabolism, your brain development, your organ function, all the fundamental biological machinery, has been changing much more slowly and is much more similar across all populations. This is why race as a biological concept doesn't hold up under genetic scrutiny. The features we use to define races, primarily skin color, but also other visible traits, are controlled by a tiny number of genes that have been under strong local selection and don't reflect overall genetic similarity. Two West Africans might be more genetically different from each other than a West African and a European, even though they have similar skin color. Skin color tells you about adaptation to UV levels. It doesn't tell you about overall genetic relatedness. Modern genetics has definitively shown that human genetic variation is clinal. It varies gradually across geography, rather than being clustered into discrete racial groups. There's more genetic variation within traditionally defined racial groups than between them. Race is a social construct imposed on biological variation, not a biological reality discovered through scientific investigation. But, and this is crucial, saying race is a social construct doesn't mean physical differences don't exist or aren't real. Obviously they exist. We can see them. We can measure them. We can identify the genes responsible for them. The point is that those physical differences don't cluster into neat racial categories the way 19th century anthropologists believed. They vary continuously across geography in response to local selective pressures, and different traits evolved independently through different genetic changes in different populations. Blue eyes, blonde hair, light skin, narrow noses, stocky builds, these all evolved in Northern European populations not as a package deal but as independent responses to various selective pressures, and they can occur in different combinations. Sexual selection shaped some features, natural selection shaped others, genetic drift shaped others, and the results are the mosaic of human physical diversity we see today. So when you look at someone of Northern European descent and notice their light skin, blue eyes, blonde hair, narrow nose, and compact build, you're not seeing a single coordinated evolutionary adaptation. You're seeing multiple independent evolutionary changes that happen to accumulate in the same population over the last 10,000 to 20,000 years. Some were driven by vitamin D requirements, some were driven by cold adaptation, some were driven by sexual selection, some were probably just random drift. All of them involved different genes, different mutations, different selection pressures, different timescales. The Northern European phenotype is a collection of traits, not a package, and each trait has its own evolutionary story. Understanding those stories separately, and then understanding how they came together in particular populations, gives us a much richer and more accurate picture of human evolution than the old racial typology ever did. And this is true for every human population. The features we associate with Asian appearance, African appearance, indigenous American appearance, these are all collections of independent traits, each with its own genetic basis and evolutionary history. Some traits are truly shared due to common ancestry. Some are convergent adaptations to similar environments. Some spread through sexual selection. Some are random noise from genetic drift. Untangling which is which requires careful genetic analysis, not just looking at surface appearance. Modern genetics gives us the tools to do that untangling, and what we find consistently is that human diversity is vastly more complex, more interesting, and more beautiful than simple racial categories could ever capture. We're one species, recently out of Africa, rapidly adapting to diverse environments across the globe, with cultural and biological evolution interacting in complex ways to produce the marvelous variation we see today. And that story, the real story based on evidence, is far more fascinating than any racial mythology could ever be. We've traced the evolution of human skin colour from its origins in Africa through migrations, mutations, selective pressures, dietary adaptations, and convergent evolution across different populations. We've seen how skin colour, along with other physical traits like eye colour, hair colour, and body proportions, evolved in response to local environmental conditions. Now we need to address the elephant in the room. What does all of this genetic and evolutionary evidence tell us about race? Because for centuries, human societies have used visible physical differences, primarily skin colour, to categorize people into racial groups, to build hierarchies, to justify everything from slavery to genocide. And the science we've been discussing has profound implications for those racial categories. Spoiler alert, the implications are not what 19th century racial scientists thought they'd be. Let's start with some cold, hard numbers that really put human genetic diversity in perspective. The visible differences in skin colour that we use to categorize people into groups, the difference between the darkest-skinned person from equatorial Africa and the lightest-skinned person from Scandinavia, come down to approximately 15 to 30 genes. That's the current scientific estimate based on genome-wide association studies that have identified genetic variants associated with skin pigmentation. Different studies give slightly different numbers depending on methodology, but let's use 20 genes as a reasonable middle estimate. 20 genes out of approximately 20,000 total protein-coding genes in the human genome. Do that math. That's 0.1% of your genome, 1/10 of 1%. The genes controlling the most visually obvious difference between human populations represent a vanishingly small fraction of your total genetic information. And here's what's even more striking. Those 20 genes are mostly involved in the same biochemical pathway, melanin synthesis. They're variations on a theme, different control points in the same process. Some genes control melanin production in melanocytes, some control melanosome development, some control the distribution of melanosomes to surrounding skin cells, some regulate how much melanin is made in response to UV exposure. But they're all doing versions of the same job, controlling how much melanin ends up in your skin. It's not like skin color genes are scattered randomly across different biological systems. They're clustered in one specific pathway that evolution can target when UV conditions change. Now compare those 20 skin color genes to the other 19,980 genes in your genome. Those other genes code for your immune system, hundreds of genes determining how you fight off infections, what diseases you're susceptible to, how your body distinguishes self from foreign. They code for your metabolism, how you process nutrients, store fat, regulate blood sugar, respond to different foods. They code for your brain development and function, your cognitive capabilities, personality traits, neurochemistry. They code for your cardiovascular system, your respiratory system, your digestive system, your endocrine system, your reproductive system. They code for every aspect of your physiology and development except skin pigmentation. And here's the crucial point. These genes are remarkably similar across all human populations. The genetic variation that exists in immune genes, metabolic genes, brain genes, and so on is distributed randomly across populations. It doesn't cluster by skin color or traditional racial categories. Let me make this concrete with a specific comparison. Take two individuals. Person A is from Sweden, has pale white skin, blonde hair, and blue eyes. Person B is from Kenya, has very dark brown skin, black hair, and brown eyes. They look dramatically different, obviously. If you saw them standing side by side, you'd immediately categorize them as different races based on appearance. Now sequence their complete genomes, all 3.2 billion base pairs, and compare. You'll find they're genetically identical at about 99.9% of positions. Out of 3.2 billion base pairs, they differ at maybe 3 to 4 million positions. That sounds like a lot, millions of differences, but it's 0.1% of the total. They're 99.9% identical. And here's what's remarkable. If you took those 3 to 4 million differences and asked, how many of these are due to skin color and related visible traits versus everything else, you'd find that maybe a few hundred to a few thousand variants, a tiny fraction, are actually responsible for their visible differences in appearance. The rest of their genetic differences are random variation in genes that have nothing to do with appearance. Person A might have immune gene variants that person B doesn't, but person B might have different metabolic gene variants that person A doesn't, and these differences have nothing to do with their skin color. They're just random variation that exist in all human populations. Now here's where it gets really interesting from a population genetics perspective. In the 1970s, geneticist Richard Lewontin did a groundbreaking analysis of human genetic diversity using the tools available at the time, blood protein variants, basically the only genetic markers we could measure before DNA sequencing. He analysed genetic variation within and between human populations from different continents, and he found something surprising. About 85% of all human genetic variation exists within local populations, not between them. That means if you take 100 people from one village in Africa and measure their genetic variation, you'll find 85% of all the variation that exists in the entire human species. The remaining 15% of variation is what distinguishes populations from different continents. This finding has been replicated numerous times with modern DNA sequencing techniques, and the numbers hold up. Most human genetic diversity, 85 to 90% depending on exactly how you calculate it, is within populations, not between populations. Let's unpack what that means. If you randomly select two people from the same African village, they might differ at, say, 3 million genetic positions. If you randomly select one person from that African village and one person from Europe, they might differ at, say, 3.5 million positions. The difference between within population variation and between population variation is only about 15% more. Most of the genetic variation between any two humans is variation that exists within all populations, not variation that distinguishes populations from each other. This is completely contrary to what racial typology would predict. If races were real biological categories, discrete groups with fundamental genetic differences, you'd expect to see much more variation between racial groups than within them. You'd expect Europeans to be genetically similar to each other and very different from Africans, but that's not what we find. We find that Europeans are just as genetically diverse among themselves as Africans are among themselves, and the genetic differences between a European and an African are only marginally larger than the genetic differences between two Europeans or two Africans. This pattern makes perfect sense when you understand human evolutionary history. Modern humans originated in Africa roughly 300,000 years ago. For the first 200,000 to 250,000 years, all humans lived in Africa. African populations had time to accumulate genetic diversity through mutation and recombination. Then, somewhere around 50,000 to 70,000 years ago, a small subset of the African population, maybe a few thousand individuals, migrated out of Africa. This founder population carried only a fraction of Africa's total genetic diversity with them. They were a sample of the African gene pool, not the complete gene pool. As they spread across Europe, Asia, and eventually the Americas and Oceania, they continued to accumulate new mutations and local adaptations, but they started from a reduced baseline of diversity compared to the African populations they left behind. The result is that African populations today have the highest genetic diversity of any continental population because they've been accumulating diversity the longest. Non-African populations have less diversity because they all descended from that small founder population that left Africa. But the differences in diversity levels are not huge, and the amount of overlap in genetic variation between populations is enormous. Most of the variation in the human species is ancient variation that was already present in Africa before the out-of-Africa migration, and that variation got carried along to other continents by the migrants. Only a small fraction of human genetic variation, the 10 to 15% that distinguishes populations, is recent variation that accumulated after populations split and adapted to local conditions. And here's the punchline that really undermines racial categorization. The genes that control visible traits like skin color, hair texture, and facial features are among the small fraction of genes that do show differences between populations, but they're outliers. They're not representative of the genome as a whole. These visible traits were under strong local selection, skin color optimizing for UV levels, body proportions optimizing for temperature, nose shape optimizing for air conditioning. So the genes controlling these traits show unusual patterns of geographic clustering. But for the vast majority of genes, the ones controlling your immune system, metabolism, brain function, organ development, the variation is distributed randomly and doesn't cluster by traditional racial categories. You can't predict someone's immune gene variants from their skin color. You can't predict their metabolic genes from their facial features. The visible traits we use to define races tell us almost nothing about the underlying genetic variation that actually matters for health, disease susceptibility, or biological function. This is why modern geneticists and anthropologists say that race is a social construct, not a biological reality. It's not that visible physical differences don't exist. Obviously they exist. We can see them, we can measure them, we can identify the genes responsible. The point is that those visible differences don't cluster into discrete categories the way the racial classification systems of the 18th and 19th centuries claimed. Human genetic variation is clinal. It changes gradually across geography. If you walk from sub-Saharan Africa through North Africa, the Middle East, Central Asia, and into Northern Europe, skin color gradually lightens at each step. There's no sharp boundary where black ends and white begins. It's a smooth gradient. The same is true for other traits. Nose shape gradually changes from broad to narrow as you move from hot to cold climates. Body proportions gradually shift from slender to stocky. Hair texture shows geographic gradients. Every trait varies continuously, and different traits show different geographic patterns because they were under different selective pressures. And crucially, different traits don't covary perfectly. Someone can have dark skin but straight hair. Someone can have light skin but tightly curled hair. Someone can have European skull proportions with Asian eye features. Any combination is genetically possible because these traits are controlled by different genes that can be inherited independently. The 19th century racial anthropologists wanted to believe that all physical features clustered together into neat packages. that if someone had African skin, they'd also have African hair, African skull shape, African nose shape, and so on. But genetics shows this simply isn't true. Different traits evolve independently, respond to different selective pressures, and can be mixed and matched in any combination. A person of mixed African and European ancestry isn't some intermediate category between two pure races. They're just a person with a particular combination of genetic variants, some of which are more common in African populations and some more common in European populations. But the categories are human constructs imposed on continuous biological variation, not natural divisions discovered in nature. So what does this mean for how we think about race? It means that race, as conventionally understood, as discrete biological categories with deep genetic differences, doesn't exist. The racial categories we use are social constructions based on a very small number of highly visible traits that were under recent strong selection in response to local environmental conditions. These traits are superficial in both the literal sense, they affect surface features, and the biological sense, they represent a tiny fraction of our genome and don't reflect overall genetic similarity. Using these traits to categorize people into races is like organizing books in a library by the color of their covers. You can do it, and the categories you create will be visually obvious and easy to see, but they won't tell you anything meaningful about the actual content of the books. Skin color tells you about ancestral UV exposure. It doesn't tell you about intelligence, personality, moral character, athletic ability, or any of the other traits that racial ideologies have historically associated with race. Now let's shift gears and talk about what happens when evolution, which spent tens of thousands of years adapting humans to local conditions, collides with modern global migration, which allows people to move anywhere on the planet in less than 24 hours. Because this creates something that biologists call evolutionary mismatch, organisms living in environments their biology isn't optimized for, and we're seeing the consequences play out in real time in the form of predictable health problems. Start with the most dramatic example, light-skinned Europeans in Australia. Australia is a massive island continent sitting mostly between 10 and 40 degrees south latitude, roughly equivalent to the latitude range from the Sahara Desert to southern Europe in the Northern Hemisphere. It gets intense UV exposure year-round, particularly in northern Queensland and the Northern Territory, which are in tropical and subtropical zones. The UV index in Australian summer regularly hits 12 to 14, classified as extreme by World Health Organization standards, and even in winter, much of Australia maintains UV levels that would be considered high in Europe. This is an environment where dark skin would be advantageous for folate protection and melanoma prevention. But Australia was colonised primarily by light-skinned people of British and Irish descent, starting in the late 18th century. These colonists brought genes optimised for the cloudy, low UV conditions of the British Isles, very light skin, poor tanning response, minimal melanin production, and the result, unsurprisingly, has been a skin cancer epidemic. Australia has the highest rate of skin cancer in the world. About 2/3 of Australians will be diagnosed with some form of skin cancer by age 70. Melanoma, the deadliest form of skin cancer, kills more than 1,000 Australians per year, despite a relatively small population of 25 million. The rates are even higher in Tasmania and southern Australia, where British settlement was most concentrated and where the population is predominantly of very pale Northern European descent. This is evolutionary mismatch in its purest form. Light skin evolved in Northern Europe specifically because the benefit of improved vitamin D synthesis in low UV conditions outweighed the cost of increased skin cancer risk, and skin cancer risk is low when UV exposure is minimal anyway. But transplant that same light skin to high UV Australia, and suddenly the cost-benefit calculation flips. You're getting plenty of UV for vitamin D, more than enough really, but you're paying a huge price in skin cancer because your melanin-deficient skin provides minimal protection against the DNA-damaging effects of intense UV. Your skin is trying to solve a problem, vitamin D deficiency, that doesn't exist in this environment while being extremely vulnerable to a problem, UV damage, that does exist. The Australian government has spent decades trying to mitigate this through public health campaigns. Slip, slop, slap. Slip on a shirt, slop on sunscreen, slap on a hat is probably the most successful public health slogan in Australian history. And it works, to a degree. Sunscreen, protective clothing, shade-seeking behaviour, regular skin cancer screenings, These cultural and technological interventions can compensate for the biological mismatch, but they're imperfect solutions. People forget to apply sunscreen, or they apply it incorrectly, or they spend time outdoors without adequate protection. And even with perfect sun protection behaviour, Australians of European descent living in high UV areas have skin cancer rates far higher than what Europeans experience in Europe. The mismatch is real, and it has measurable health consequences. Now flip the scenario. Dark-skinned people of African or South Asian descent living in northern latitudes. These populations evolved dark skin specifically to protect against high UV exposure in tropical and subtropical climates. Their melanin-rich skin is excellent at blocking UV, which is advantageous when you're in Lagos or Mumbai where the UV index is high year-round. But move that same dark skin to London or Toronto or Oslo, and you create the opposite mismatch. You're blocking UV that's already scarce, and you're struggling to synthesize adequate vitamin D even during summer, and during winter, you're getting essentially zero vitamin D from sun exposure. And the data bears this out. Studies consistently show that people of African and South Asian descent living in Northern Europe and Northern North America have high rates of vitamin D deficiency, significantly higher than the local light-skinned populations. One study in the UK found that nearly 50% of people of South Asian descent and 30% of people of African descent had vitamin D deficiency during winter, compared to about 15% of white British people. Similar patterns show up in Scandinavia, Canada, and the northern United States. The darker your skin, the further north you live, the higher your risk of vitamin D deficiency. Now you might think, well, we've solved that problem. We have vitamin D supplements, fortified foods, and medical care. No big deal. And to some extent, that's true. Modern technology does allow us to compensate for evolutionary mismatch. If you're dark-skinned and living in Sweden, you can take a vitamin D supplement daily and maintain adequate levels despite minimal sun-driven synthesis. Problem solved, right? Except it requires awareness, access, and consistent behaviour. You need to know that vitamin D deficiency is a risk. You need access to supplements or fortified foods, which requires either money to buy them or access to public health programs that provide them. And you need to actually take the supplements consistently, which requires health literacy and habit formation. In practice, many people don't do this. They might not be aware of the risk, or they might not have access to supplements, or they might not prioritize it because vitamin D deficiency is often subtle. You don't necessarily feel sick right away. The symptoms, fatigue, bone pain, muscle weakness, increased susceptibility to infections, can be vague and attributed to other causes. By the time severe problems like rickets in children or osteomalacia in adults develop, you've been deficient for a long time. So despite living in a technologically advanced society with access to supplements and fortified foods, we still see health consequences of vitamin D deficiency in dark-skinned populations living at high latitudes. It's a solvable problem, but it's not automatically solved. And there are other examples of evolutionary mismatch beyond just skin colour and UV exposure. Populations adapted to high-altitude environments, like Tibetans and Andean peoples, have genetic adaptations for oxygen-thin air that lowlanders don't have. When lowlanders travel to high altitude, they get altitude sickness, headaches, nausea, reduced physical performance, because their physiology isn't optimized for low oxygen conditions. We can compensate with time for acclimatization and supplemental oxygen, but the mismatch is real. Populations adapted to tropical diseases have different immune gene variants than populations from temperate regions. When they migrate, they might be more susceptible to diseases they didn't encounter in their ancestral environment, or they might have unnecessary immune responses that cause inflammatory disorders. Diet is another huge source of mismatch. Populations from different regions evolved different metabolic adaptations to their traditional diets. Populations with long histories of dairy farming evolved lactose tolerance at high frequencies. Populations without dairy farming didn't. When lactose-intolerant people consume dairy products, they get sick, cramping, diarrhea, digestive distress. Populations from high-starch agricultural diets may have different insulin responses than populations from low-carb hunter-gatherer diets. When everyone starts eating modern industrial diets high in refined carbohydrates and processed foods, some populations may be more prone to metabolic disorders like diabetes than others. The overarching pattern is this. Evolution adapted humans to specific local conditions over thousands of generations. Those adaptations were often quite precise, just enough melanin for local UV conditions, just the right body proportions for local temperature, metabolic responses tuned to local food availability. But modern technology and transportation have allowed humans to move anywhere on the planet within a few days. We can fly from equatorial Africa to Arctic Norway in less than 24 hours, carrying with us bodies optimized for one environment while landing in a completely different environment. Evolution can't keep up with that pace of change. Evolutionary adaptation takes thousands of years. Modern migration happens in hours. The result is billions of people living with some degree of evolutionary mismatch between their biology and their environment. But, and this is important, technology increasingly allows us to compensate for these mismatches. Sunscreen protects light skin in high UV environments. Vitamin D supplements compensate for dark skin in low UV environments. Climate control, heating and air conditioning, buffers us against temperature extremes our bodies might not be optimized for. Dietary modifications and supplements can compensate for metabolic mismatches. Medical interventions can treat or prevent diseases that our immune systems might not handle optimally. In essence, culture and technology are taking over from biological evolution as the primary mechanism by which humans adapt to environmental challenges. This has profound implications for human evolution going forward. For most of human history, populations that couldn't adapt biologically to their local conditions didn't survive or had reduced reproductive success, creating strong selective pressure and driving evolutionary change. But now, populations that are biologically mismatched to their environment can thrive using cultural and technological compensations. This removes or greatly reduces the selective pressure that would otherwise drive evolutionary change. Light-skinned Australians aren't evolving darker skin because sunscreen allows them to survive and reproduce just fine despite their skin cancer risk. Dark-skinned Scandinavians aren't evolving lighter skin because vitamin D supplements solve the vitamin D problem without requiring genetic changes. So what does the future of human skin colour look like in an increasingly interconnected world with global migration, interracial marriages producing children with mixed ancestry, and technology that buffers against environmental selective pressures? This is actually a fascinating question, and the answer is, it's complicated. On one hand, global migration and intermixing are creating populations with increasingly diverse genetic backgrounds. A person might have ancestors from Europe, Africa, Asia, and the Americas, giving them a unique combination of genetic variants for skin color and other traits. Their skin tone might be intermediate between their ancestors' skin tones, or it might lean toward one parent or the other depending on which specific genetic variants they inherited. Over many generations of mixing, you'd expect to see a homogenization effect, populations becoming more similar as genetic variants from different ancestral populations get shuffled and recombined. On the other hand, technology is removing the selective pressure that would otherwise drive skin color to optimize for local UV conditions. If vitamin D supplements and sunscreen allow people to thrive regardless of whether their skin color matches their environment, then there's no fitness advantage to having locally optimized skin color. In the absence of selective pressure, skin color becomes a neutral trait that can drift randomly or be influenced by factors other than UV adaptation. Sexual selection, mate choice based on physical appearance, might become more important than natural selection in determining what happens to skin color frequencies in future generations. If certain skin tones or combinations become fashionable or considered attractive in particular cultures or time periods, those preferences could shift skin color frequencies even without any connection to environmental adaptation. If we project far into the future, thousands or tens of thousands of years, assuming humans continue to live in geographically dispersed populations and technology continues to buffer against environmental pressures, you might see skin color variation, maintained at high levels within populations rather than showing strong geographic patterning the way it does now. Instead of light skin in northern latitudes, dark skin in southern latitudes, you might have diverse skin tones everywhere, with local frequencies determined more by historical migration patterns, cultural preferences, and random drift than by UV. Optimization. The old evolutionary rules that produced the current geographic distribution of skin color would no longer apply because the selective pressures that created those rules would be gone. Alternatively, if populations stay relatively geographically stable over many thousands of years and gradually abandon technological compensations, maybe some catastrophic decline in technology forces people to rely more on their biology again, might see a slow return to local optimization. Light-skinned people living in high UV areas might experience slightly lower fitness due to skin cancer, and over many generations, darker skin alleles might become more common in those populations. Dark-skinned people living in low UV areas might experience slightly lower fitness due to vitamin D-related health problems, and lighter skin alleles might spread. But this would require thousands of years without technological interventions, and would only work if the fitness differences were large enough to drive selection, which in modern contexts with medical care might not be the case. The most realistic scenario is probably some combination. Continued global migration and intermixing creating more genetic diversity within populations, continued technological buffering against environmental selective pressures, making skin colour largely neutral in terms of fitness, and cultural/sexual selection based on aesthetic preferences and social dynamics playing a larger role than natural selection in shaping future skin colour frequencies. The result would be a human population that's more genetically diverse within each region, with less clear geographic patterning of skin colour, and with appearance being shaped more by cultural preferences and random variation than by environmental adaptation. But zooming out to the bigger picture, whether skin colour continues to show geographic patterns or becomes more randomly distributed across populations, one fundamental truth remains. All human skin tones trace back to a common African origin. Every genetic variant that contributes to light skin is a mutation that appeared relatively recently in human history and spread because it solved a vitamin D problem in low UV environments. Every light-skinned person alive today carries in their genome the echoes of dark-skinned African ancestors who lived tens of thousands of years ago. The light skin mutations are recent additions, modifications to the ancestral dark skin blueprint that all humans started with. Let's put this in perspective with a thought experiment. Imagine you could line up all your direct ancestors in a row, starting with you and going back in time, one generation at a time. If you're of European descent, the first several hundred generations would probably be light-skinned Europeans. But keep going back. At some point, maybe 1,000 or 1,500 generations ago, you'd encounter ancestors whose skin was noticeably darker than yours. Keep going. At 2,000 generations ago, about 50,000 years, your ancestors are dark-skinned people living in the Middle East or North Africa, recently out of Africa. Go back to 10,000 generations ago, 250,000 years, and everyone in your ancestral line is dark-skinned and living in Africa. The light skin is new. It's an addition, a modification, a recent adaptation. The foundation is dark skin, African origin, shared with every other human being alive today. And this brings us to what might be the most important point in this entire story. Beneath all the visible variation in skin colour, hair texture, eye colour, facial features, and body proportions that we use to categorise people into groups, we are one species with very recent common ancestry. The most recent common ancestor of all humans alive today lived probably somewhere between 100,000 and 300,000 years ago in Africa. That's recent. That's nothing in evolutionary terms. We are essentially all siblings under the skin, separated by maybe 4,000 to 10,000 generations at most, sharing 99.9% of our DNA, with the 0.1% of variation being mostly superficial adaptations to local climates and random neutral variation that doesn't affect function. Every human population on Earth is part of a continuous family tree with deep African roots. The migrations, the mutations, the local adaptations, these are recent branches on a very young tree. The differences we see are interesting and tell important stories about human adaptation and evolution, but they're not fundamental divisions. They're not markers of separate races or subspecies. They're variations on a theme, different solutions to different environmental challenges, all built on the same basic human blueprint that we all inherited from our African ancestors. Skin colour in particular is a map, not a hierarchy. It tells you where someone's ancestors lived and what UV conditions they adapted to. It doesn't tell you anything about their intelligence, personality, moral worth, capabilities, or essential human value. A person with dark skin optimized for equatorial UV is not inferior or superior to a person with light skin optimized for northern UV. They're just different solutions to different environmental problems. And both are recent modifications to the ancestral African dark skin that all humans originally had. This is why the concept of race, as it's been historically understood and as it continues to be used in many social and political contexts, is fundamentally incompatible with what genetics and evolutionary biology tell us. Race implies discrete categories, fundamental differences, deep divisions. Genetics shows us continuous variation, superficial adaptations, recent divergence, and overwhelming similarity. Race implies hierarchy, with some groups being superior or inferior to others. Evolution shows us only different adaptations to different environments, with no judgments about better or worse, just optimization for specific conditions. Race is a social construct that we've overlaid onto biological variation. The variation is real, the construct is fiction. And understanding this, really understanding it, not just intellectually but viscerally, changes how you see human diversity. When you look at someone whose skin color is very different from yours, you're not seeing a member of a different race. You're seeing a person whose ancestors solved the vitamin D problem differently than your ancestors did, because they lived in a different place with different UV conditions. When you notice variation in eye color, hair color, nose shape, body proportions, you're seeing different populations' responses to different selective pressures, temperature, humidity, altitude, diet, and yes, probably sexual selection and random. Drift too. You're seeing the mosaic of human adaptation to diverse environments across the globe. You're seeing evolution in action, recent and ongoing, producing beautiful variation while maintaining fundamental unity. The story of human skin color is ultimately a story about adaptation, survival, migration, and the incredible flexibility of our species. We spread from Africa to every habitable continent. We figured out how to survive in tropical rainforests and Arctic tundra, scorching deserts and temperate forests, high mountain plateaus and coastal lowlands. And we did it through a combination of biological evolution, changing our skin color, body proportions, metabolic responses, and cultural evolution, developing tools, clothing, shelter, cooking, social organization. We're not the strongest animals or the fastest or the toughest, but we're the most adaptable. We can live anywhere. We can eat anything. We can solve problems through culture when biology can't keep up. That's the human superpower, and skin color is just one small example of it in action. So as we come to the end of this journey through the evolutionary history of human skin color, remember this: skin color is temporary. It's recent. It's superficial. Light skin has only existed for maybe 30,000 years, a blink of an eye in evolutionary time. Before that, for 270,000 years, all humans were dark-skinned. If you go back far enough, everyone's ancestors had dark skin. And if you go forward far enough into the future, assuming humans survive as a species, which is certainly not guaranteed given our current trajectory on climate change, nuclear weapons and various other existential risks, skin color might look completely different than it does today. Maybe technology will advance to the point where skin color becomes totally arbitrary, changeable through genetic modification or synthetic biology. Maybe global mixing will create populations where extreme variation exists everywhere. Maybe we'll colonize other planets with different UV conditions and evolve new skin colors we can't even imagine now. But whatever happens, the underlying truth remains. We're one species, one family, one story. Every human being alive today is part of an unbroken chain of ancestors stretching back 300,000 years to East Africa. We're all related, all connected, all carrying the genetic legacy of those original dark-skinned humans who first developed the capacity for abstract thought, language, art, music, and all the other things that make us human. The skin color variation we see today is just a footnote, a recent edit, a set of local adaptations that evolution scribbled in the margins of the human story. The core text, the 99.9% of our genome that we all share, remains identical across all populations. We are, fundamentally and inescapably, one human family. And that's not just a nice sentiment. That's what the genetics tells us. That's what the evidence shows. That's what the science says. So the next time someone tries to use skin color or other visible traits to argue for fundamental differences between racial groups, for hierarchies based on appearance, for discrimination based on arbitrary physical characteristics, remember what we've learned here. Remember that those visible differences represent 0.1% of the genome. Remember that 85 to 90% of human genetic variation exists within populations, not between them. Remember that the genes controlling appearance were under recent local selection and don't represent overall genetic similarity. Remember that skin color is a map showing ancestral UV conditions, not a marker of intelligence or worth or capability. Remember that we all descend from dark-skinned Africans who lived 300,000 years ago, and every light-skinned person carries mutations that are at most 30,000 years old, which is nothing, which is yesterday, which is brand new in evolutionary terms. Remember that beneath every shade of human skin lies the same human heart, the same human brain, the same human capacity for love, art, science, kindness, cruelty, brilliance, and foolishness. Remember that the differences are interesting and worth studying and tell important stories about adaptation and evolution, but they're not fundamental. Remember that race is a social fiction laid over biological reality, and while the biology is real and fascinating, the racial categories are arbitrary constructions that don't reflect how genetics actually works. And remember, finally, that you are part of this story. Your skin color, whatever it is, tells a story about where your ancestors lived, what problems they faced, how they survived. Whether your skin is dark or light or somewhere in between, it's an evolutionary document, a genetic record of human adaptation and migration written in melanin. It's part of the incredible human heritage of adaptability, creativity, survival, and triumph over environmental challenges. You're carrying in your body the legacy of thousands of generations of humans who figured out how to survive and thrive in environments that would have killed them if they hadn't adapted, through biology, through culture, through technology, through sheer stubborn determination to keep going. That's the story of human skin color. That's what evolution tells us. That's what science reveals. And it's a story worth knowing, worth understanding, worth sharing, because it fundamentally undermines the racist ideologies that have caused so much suffering throughout history and continue to cause suffering today. Understanding the real evolutionary history of human diversity doesn't just give us interesting scientific knowledge, it gives us a powerful tool for combating prejudice, discrimination, and hatred based on arbitrary physical differences. It shows us that we're all one family, all equally human, all carrying the same fundamental genetic inheritance with minor local modifications. And if we can internalize that, really believe it, maybe we can build a world that treats all people with the dignity and respect that our shared human heritage demands. That's my hope anyway. That by understanding where we came from, how we evolved, why we look the way we do, we can move past the superficial differences and recognize the profound similarities that unite us all as members of one species, one family, one story. We're all Africans under the skin. We're all carrying mutations that our ancestors developed to solve local problems. We're all part of the same evolutionary journey. And maybe, just maybe, if we remember that, we can treat each other a little bit better. So with that, we've reached the end of our journey through the evolutionary history of human skin color. We've travelled from Africa to Europe to Asia and back again. We've traced mutations through populations over thousands of years. We've watched natural selection favour light skin in some places and dark skin in others. We've seen how diet, culture and technology interact with biology to shape human adaptation. We've explored the exceptions that prove the rule and the convergent evolution that shows similar problems producing similar solutions through different paths. And we've arrived at this final understanding that human diversity is real, fascinating and worth celebrating, but it doesn't divide us into separate races. It connects us as one human family with recent common ancestry and overwhelming genetic similarity. Thank you for coming on this journey with me. I hope you've learned something, that you found the story as fascinating as I do, and that you'll carry these lessons forward as you think about human diversity, race, and what it means to be human. Now go get some rest. You've earned it after this deep dive into evolutionary biology. Good night and sweet dreams.